Welcome, everyone. My name is Moon Duchin, and I'm the PI of the MGGG Redistricting Lab at Tisch College at Tufts University. And I'm super excited to kick off this Graphs and Networks workshop. Initially, we'd hoped to have this as a small in-person workshop in May. Events may have scrambled our ability to do that just a little bit. And so we've reconfigured this as an online workshop that's open, that's free, that was widely available. And in response, we got, as of this morning, 625 people signed up to come to this. So I'm extremely pleased with the response. What I'm hoping is that the way that we do this workshop can be a little bit of a model for the upside of Zoom conferences. The downside is clear because, you know, in-person networking and communication is such an essential part of, of science and of academia and of kind of building knowledge. So our ability to do that in person isn't there right now, but in exchange, we get a much wider reach. So over the course of the day, we'll have speakers coming to you from all over the country and the world, a few from all other countries. And we'll also try to provide as many as possible opportunities for you to interact. So this webinar has a Q&A feature that we hope that you'll use. And we'll be we have staff on hand from our lab to try to manage that over the day. There's a discussion session at 1 o'clock, and I'd especially like to encourage people to try to come for that. What we'll do at the discussion session is we'll have an array of panelists, including our speakers. And I've asked people to just think of a paper or two that they're excited to tell you about and what they're excited to tell you. At the same time, we'll have a Google Forms link for everyone who's watching to be able to do the same thing. Tell us about a paper that you're excited about. Doesn't matter if you wrote it or you didn't. And we'll make that available also as a way of sort of fostering larger community communication around what's going on in graphs, networks, and their meaningful applications. Okay, to that, let me say, this is an extraordinary time for more than one reason. Obviously, there's a coronavirus pandemic going on that has just scrambled the social life of the world, that has called an unprecedented response from different kinds of scientific communities to think about how to address it and how to understand it. At the same time, there's an epidemic of police violence and a very important moment in American history of an uprising, some are saying the largest in American history, calling attention to the acute problems, insisting that Black Lives Matter, and trying to think in new ways about, again, how scientists can address it, study it, understand it, help reform it. So these two twin crises frame this moment, at least for me and for our lab. And that makes this conference, I think, especially timely. We've got a broad array of people speaking about their new work and their ideas. And I hope speaking to each other across silos. So the conference is intentionally very broadly framed. Graphs and networks, those are two big topics. But what our special hope is to take the people who are thinking about network medicine and the people who are thinking about social networks and the people who are thinking about civic networks, and take some of the ideas, and also the pure mathematicians, the theoretical computer scientists, take some of the ideas from some of these sub-communities and do that proverbial cross-pollination. So I think we've got a terrific lineup of people to do just that. I'll tell you the tiniest bit more about our lab and some of our interests in graphs and networks. So we're called MGGG, Redistricting Lab. That stands for Metric, Geometry, and Gerrymandering Group. And so we're a collective of people who like to think about redistricting. And how is that a graphs and networks problem? Well, for us, it starts with the census data itself. And so this is a graph of Missouri. Here are some refinements. Refinement. What are we looking at here? We're looking at census data. Okay, so these are census units, counties, refined to tracts, refined to block groups to blocks. There are alternative pathways and very complicated sort of interlocking hierarchies in census data. And I've put a link up here, and of course, everything we do will be, all the links and all the slides from today will be available in the materials that we produce after the workshop. But we started to look at this and think about it as a system of graphs and networks. And we haven't found very much that's been done from this point of view before, but we're making available all these dual graphs to census geography that we're building and hoping that people will find interesting applications for them. For us, being able to understand these graphs and their structure is a gateway to not only understanding redistricting, but also solving planning problems, also thinking about differential privacy, the new disclosure avoidance system in the census and the impact that it's going to have. You can do all kinds of remarkable, deeply socially relevant work, but you need this kind of mathematical piece in place in order to enable a lot of the other work that you might want to layer on top. So for me, in thinking about kind of putting this collection of people together, this was a guiding example. Wouldn't it be fun if everybody who had all kinds of remarkable methods being developed in various corners of graphs and networks thought about this as another data set to be played with? Okay, let's all get together and talk. So with that in mind, here's today's schedule. So I think everyone listening has seen the first schedule, and then what you see next to it is our excellent series of 8 lightning talks, mostly from students and a few postdocs. And if you look at the subjects that they'll be talking about, they're extremely wide-ranging. So it's a real pleasure today to be able to serve as a hub for all the folks that are participating and all the folks that are listening to get to know each other. And that is where I'll leave it. Okay, so thanks so much for joining us. Right now it's 9:40. The first talk today happens in 10 minutes by Rediet Abebe, talking about modeling the dynamics of poverty, and she kicks off a really great list of speakers. Okay, so with that, I will leave my screen share up, if I can, like so. And we'll take a 10-minute break until we start, but this is a good time, if anyone has them, to test the Q&A feature, ask questions about the structure of the conference, or anything that you want to do to practice that feature. And otherwise, we will reconvene in 9 minutes with Red's talk. Okay, so it's 9:50. I think people will be sort of joining us gradually over the course of the day. I'd like to get us started with our first 25-minute talk of the day. It is an enormous pleasure to introduce Red Abebe, who is at the Harvard Society of Fellows, doing really interesting work from a computer science departmental perspective on many issues to do with fairness, equity, inclusion. This talk is called Modeling the Dynamics of Poverty. So the way we'll do it is Red will share her slides, and you can, those of you who are watching this in the webinar, can put questions in the Q&A as she talks, but we won't interrupt her during her 25 minutes. We'll take 10 minutes after that to pose her the questions that are in the Q&A. So we hope that you will engage in that way. And for those of you who are panelists, which it'd be great if you are able to turn on your cameras so that Red feels a little bit more like she's talking to live people. And with that, thanks very much, and take it away, Red.
Thank you, Moon. I'm just gonna very quickly confirm first that you can see my slides. So I'm guessing you can see my slides now. Correct?
Yes.
Very good. Okay. And it's not the speaker notes, just the slides. Very good. All right, so I can get started. All right, thank you so much, Moon, and the organizers of this workshop for inviting me. I've been a fan of your lab and the work that you're doing for quite some time, so it's really a huge honor for me to be here. So today I'm going to talk to you about recent work that I've done on modeling the dynamics of poverty, and this is work that is mathematical, but it cuts across computer science and in particular algorithmic work, It focuses on empirical policy work. It focuses on economics. So it's really a multidisciplinary effort that is going to be shown through this project. And you'll notice that the main results that I'll show you have not much of a networked component to them, but a lot of the open questions that are outstanding, some of which I'm working on, very much have a networks component. And I'm hoping that this will be an opportunity for me to start a conversation with folks in this on this call and in this webinar series. So the issue that we'll focus on today is poverty. As you must know, poverty is a problem that's very highly prevalent across the US. For instance, in Boston, which is where I'm based right now, over 20% of the population lives in poverty. And this number and this percentage is actually higher for certain groups. So for older populations, it's really closer to 25% or even 30%. And other groups also are very vulnerable. But despite being such a prevalent issue, poverty is known to be very difficult to measure. So oftentimes what we do is we rely on simple measurements of poverty, like people's income or their wealth, and we use these metrics to make very consequential decisions about what families are going to get what resources. But this sort of stands in stark contrast with the empirical and policy work, which has said repeatedly that these income-only measurements are very inadequate. So if you look at the Poverty Tracker study, which is this massive study that was done out of the Columbia Population Research Center, they talk in their reports and in our conversations with them, they've mentioned that these income-only measurements are very optimistic, and a lot of families that are actually quite vulnerable may be missed if you were only looking at people's income to make decisions about how you're allocating resources. So you might say, okay, we have information about income sometimes, but you're saying that it's not adequate for measuring people's economic welfare. So what exactly is missing? What exactly are the sort of the facets of economic disadvantage that are missing here that would not necessarily be captured by people's income? Well, in this setting, one dimension that we know is very important from the economics and policy literature is the role of income shocks. I think now with this pandemic, I think there's even increased awareness about the role of income shocks. So these income shocks can constitute of a delay in someone's income flow. So maybe someone got fired, or even just they had a delay in their paycheck. It just didn't arrive. Maybe it was supposed to arrive at 9 o'clock and it arrived at 9:30, you know? Or it could be a sort of unexpected expense, right? It could be that maybe they had a medical expense or even a small thing like a parking ticket. And a lot of times, you know, for certain families, maybe a delayed paycheck or a parking ticket, you may not even notice it. But for other families, it can actually start this cycle of economic disadvantage that can be very difficult for people to get out of. So there's actually a lot of work nowadays that shows that many families are just one medical bill away from being in deep poverty that will be very difficult to get out of. So these income shocks, in a way, are able to capture a lot of the different types of disadvantage that families might be facing. And so acting on those may be one way that we can capture some of the facets of disadvantage that may not be adequately accounted for using only income. So there's a lot of work in the empirical space on the role of income shocks on housing and on health and economics. There's a lot of work on optimal taxation theory that's related. I won't get into it, but I do want to emphasize that these shocks can be pretty significant. So you might ask from a sort of a more mathematical perspective, you might say, okay, we are mathematicians and computer scientists, so we know how to design algorithms. How would you design an algorithm that might optimally allocate subsidies that you might give out to families? And how do you do that when you're taking people's experiences with income shocks into account, right? So we're gonna first come up with a model of welfare that's going to incorporate shocks, and then we're going to come up with algorithms that optimally allocate subsidies in the presence of this income shocks. And I'll say that this is joint work with my now I guess former advisor at Cornell, John Kleinberg, and my collaborator, Matt Weinberg, who's at Princeton University. So go Big Red. yes, we have at least one Cornellian here, so good. Very good, so we have our problem. So I'm gonna show you the model. It's a very stylized model, but it's one that's based on the structure of ruin processes. So we'll assume that we have n agents, so agents 1 up to n, and we assume that these agents represent a family that we would like to assist. We see here that the x-axis is going to correspond to time. We'll assume that time runs continuously here. This ends up being actually very crucial for for our ability to make mathematical progress. And on the y-axis, we have a reserve. So this reserve is a sort of measure of how far a family is from kind of falling into poverty, let's say. Right, so we'll assume that now your family has an initial wealth, right? So you can think of this as all the savings they have in their bank account or all their assets combined or something, right? So this is what's indicated by the U sub I for family I. And they also have a net income of C sub I. So this is how much they earn in a given time period minus how much they would typically spend, right? So if there were no issues, this net income C sub I would directly go into their reserve. And so their reserve at time T would be given by their initial reserve, which is their wealth, plus C sub I, which is their net income times T, right? So this is sort of a very simple measurement of how far a family is at any given time T from this kind of measurement of poverty. But we are in a setting where there are shocks that are being experienced by the families. So we model these shocks as a sort of sudden drop in the agent's reserve. So we'll assume that these shocks are now going to arrive at randomly selected discrete time points, T1, T2, and so on. And we'll denote these shocks, or rather the magnitude of these shocks, by S sub I, S sub 1, S sub 2, and so on, right? So at time T sub 1, we have a shock of magnitude S sub 1, which is the one that you see indicated in the plot here that the family is experiencing. So the reserve will decrease by that amount, and then maybe the family keeps going up, and then again they experience another shock, and it keeps going. So we'll say also that the shocks are arriving according to a Poisson process with arrival rate beta sub I. This is going to control how frequently you're experiencing shocks on average. And we'll say that the magnitude of these shocks, the sort of the S sub J's, are drawn from a distribution F sub I. So notice that this arrival rate, the beta sub I, and the distribution of the shocks, the F sub I, are dependent on the family. So you can have a family experiencing frequent shocks, but maybe the magnitude of the shocks are not so bad on average, or maybe you have a family that's experiencing shocks very infrequently, but when they do experience them, maybe the distribution will make it such that these are very deep shocks. Right, so this is sort of family dependent, and you can change it as you would like. So now the reserve is again quite straightforward. Your reserve now at time T is what your reserve would have been if you did not experience any shocks, right? So the first two terms that you see on the right-hand side, minus the magnitude, the sum of the magnitude of the shocks that you've experienced up until that point. So you're just summing all the sort of S sub 1, S sub 2 up until time T, and you subtract that from your reserve, right? So this is a simple measurement of welfare that we have here, but it incorporates not just people's income and their initial wealth, but also the arrival rate of the shocks, how frequently you're experiencing these shocks, and also how deep these shocks can be on average. And as I've mentioned, our objective here is to make sure that agents don't fall below a given threshold. We'll set that to be a 0. We'll assume that if you fall below this threshold of 0, you're going to say that you've experienced ruin. And as a result, you become very susceptible to experiencing eviction, experiencing poor health, and things like that. So the object of interest here is the family's ruin probability, the probability that at any time point T, sort of we're working in infinite horizon, that at any time point they fall below this threshold where your reserve is 0 or less, and as a result become very susceptible to negative life experiences. So our optimization problem will rely on this object of interest, the ruin probability, which is taking into account your income, your initial wealth, arrival rate of the shocks, and the distribution from which the shocks are drawn. And the intervention that we're going to look at is going to be an income subsidy. So we're saying that maybe I have a fixed budget B at each time step, and I can give each agent X sub I of income so that they can pad their income by this amount. And so this sort of, you see on the graph that the slope kind of increases, right? Because you've padded their income by this amount. But we'll say that you're subject to this budget constraint. So the sum of the X sub I that you're giving out cannot be more than the budget that you have, which is B. So this is the intervention we're looking at. And we'll say that we're going to optimize for a min-sum objective. So this objective is going to minimize the expected number of people that would experience ruin, right? So we are considering an income subsidy and a min-sum objective, but there are other objectives that you could look at. There's also other types of interventions that you could look at. We're not going to kind of get into those, but it's important to acknowledge these as important dimensions of kind of decision that we made in this optimization problem. So now we're asking the question, how can you optimally allocate income subsidies to minimize for the expected number of people that experience ruin? And also not just optimally solve this problem if we can, but also we ask, does the solution give you sort of any insight into the nature of welfare beyond what you would have been able to see if you just had, just looked at people's income or something? So I'll show you a sort of a very kind of simple, like an initial case that we worked out. There's more results in the paper if you want to take a look. We looked at the case where the initial wealth of agents is 0, right? So they're starting right at this threshold. Kind of, you can imagine this is like families maybe living paycheck to paycheck, right? So they're starting at that threshold, and we want to minimize the expected number of people that actually fall below this threshold. We'll also assume that agents have positive drift, meaning that the expected change in reserve per unit time is positive. So your income minus the beta sub I times mu sub I is giving you the mean of the distribution. So we're assuming that your income at a given time point minus sort of an expectation how much shock you might experience is actually positive. So on average, you'll be able to kind of get by, but not always. Right, so we'll make these assumptions. And under these assumptions, as it turns out, thanks to probabilists who've done the hard work here, there's actually a simple, if you make an additional very sort of simple assumption, meaning that if we assume that the mean and the variance of the distribution is sort of finite, then, the probabilists have worked out for us that actually there's a sort of simple expression that gives you agents' ruin probability. So this is the beta sub I times mu sub I over your income, right? So this is a simple expression giving you the ruin probability. And so now what we can do is we can just rewrite our objective function. So our objective function, which is phi, the min-sum objective, wants to minimize the expected number of people that experience ruin. And your intervention is, as you can see there, the C sub I plus X sub I, you're giving out income subsidies. So you can rewrite that, as you can see in the second line here, using the expression from the previous slide. So you're trying to minimize this expression. And so what we'll do here is we'll look at the partial derivatives of this function phi with respect to your intervention, the X sub I, and it gives you this sort of partial value that you see on the last line. And we find that by taking the second derivative with respect to the X sub I, you find it's always positive, and therefore this phi is strictly convex. So that gives us hope, right? Because what that says is that in this particular special setting, if you're trying to optimize for using the income subsidy intervention, then actually a sort of greedy algorithm that goes as follows will give you the optimal solution. You're going to order the agents in this greedy algorithm, you're going to order the agents in increasing order of their partial values, right? This is a sort of a priority index. So agent 1 has the most negative partial value and agent 6 has the least negative partial value. Then what you'll do is you'll increase your X sub 1 for agent 1 up until the point where their partial value matches that of agent 2. Then you'll lock in agent 1 and 2 and increase their income subsidies up until the point where their partial values match that of agent 3. And you sort of keep going until maybe you've assisted everyone or maybe you run out of a budget, right? So in this particular case, you helped agent 1, then agent 1 and 2, then agent 1, 2, 3, and 4, because 3 and 4 had the same values, and then you ran out of a budget. So this greedy water filling algorithm gives you the optimal solution in this particular case where you have positive drift and the initial wealth is 0. And what's nice about this is that it's not just that you have this optimal solution, it's also that actually you have a sort of priority index here, right? You're ordering the agents by their income, by these partial values that you see here. But you might ask, well, okay, so you kind of did all this, all this work, and you have this new ordering of agents, and you were able to intervene in that way. But maybe it's the case that this is basically the same as what you would have done if you just ordered the agents by their income, which is what we would do sort of in general policy settings, right? So you might ask, how different can this priority index be? The priority index for our optimal solution, how different can that be from the priority index that would just use agent's income, right? So as it turns out, I can actually give you a very simple example that we won't get into in the interest of time, that basically says that you could, I can give you an example here where if you order the agents from the lowest income to the highest income, that would actually be the reverse of our optimal solution. Our optimal solution would actually say, pick the person that has the highest income, then the second highest income, and so on in this particular setting. So in this way, the agent that actually has the highest income is the most receptive to our intervention, right? So, so we actually find that we can give a gap, a pretty wide gap of root n between our optimal solution and the solution that only uses people's income. We won't get into the detail, but highly encourage looking at the paper. But it's not just this actually that's sort of kind of surprising, right? So this sort of reminds us of the quote that we saw earlier about income-only measurements maybe not fully capturing the disadvantage that families are facing. But it's not just this discrepancy. We also find that, we had used the min-sum objective, but we could have used a min-max objective, which would say that you're trying to minimize the maximum probability that you're seeing, whereas the min-sum one is saying, let's just minimize the expected number of people that experience ruin. And in these settings, again, we can find the optimal solution for both of these objectives that you might have. But in both of these settings, we also, again, find that a very simple example, actually the same one that I kind of flashed through earlier, would give you an instance where the min-sum objective and the min-max objective would be targeting people in the exact reverse ordering. So what this is saying is that depending on what your objective function is, you could be targeting entirely separate sets of families. Again, this actually ends up being true even for the type of objective function. So if you had fixed your min-sum objective, but rather than giving people an income subsidy, you consider giving them an initial wealth subsidy, right? So you just arrive at time zero, give people an initial kind of boost that increases their y-intercept, and then you just walked away rather than the income subsidy, which acts at every time step. So if you had these two different types of interventions, as it turns out, again, they can actually be targeting entirely separate sets of families, right? So what this is sort of saying is that, in this stylized model, under making these kind of very standard assumptions, min-sum and min-max are highly standard objective functions. Income subsidy and wealth subsidy seem like very standard sort of interventions you could consider. And even in these settings, we find that actually there's sort of these very deep societal implications. So the first one about our income, our optimal solution versus income, says the information you're taking in about families really matters, and it can actually kind of tell you to look at one set of family or an entirely disjoint set of families. Your objective function really matters. It can tell you to target one family or a different family. And also the intervention type you're looking at also really matters. And I want to emphasize this point because in a way, math and algorithmic problems are sometimes sort of bemoaned for being sort of cold calculators, right? You're kind of taking in these deep issues like poverty and inequality and injustice, and you're kind of coming up with like mathematical formulations. And in a sense, it can feel like it's sort of removed from what's going on out into the world. But I think that this example is an instance where it actually tells you that how you're formulating these problems dictates how you might understand these problems, and it certainly dictates how we're allocating interventions. And so in a way, this mathematical formulation can be a site where we can have conversations, hard conversations around how we allocate subsidies. Should we be targeting the person that's the most vulnerable, i.e. the min-max objective, or should we be going for sort of on average, we were trying to save as many people from this ruin threshold that we've set as possible, right? So I think this is a sort of this formalism aspect of math can actually be used for advocacy as well. And I think it hasn't been enough. But, you know, all these results that I showed you were sort of for this specialized case. I'm not going to go into the sort of general case in detail in the interest of time, but I'll just kind of flash through the main results, which is that, you know, we assume now that you can have income, arbitrary income and arbitrary wealth. We assume actually that your shocks can be drawn from any distribution. I don't even assume that the distribution has a compact representation. I'll just say, this distribution exists. I'll give you access to it in a sort of black box fashion. That's all I'm going to tell you. And I'll tell you what the mean of the distribution is. And even in that case, and even in the case where we now allow agents to have negative drift, meaning that their ruin probabilities are now 1. And so for a while, you might be kind of giving them income subsidy and their ruin probability will stay 1 because they have negative drift, right? So in this very highly sort of generalized setting, we still find that the optimization problem is harder now. It's actually, you know, it's NP hard because the objective function is not convex. But even in this setting, we were able to show that we can give what's known as an FPTAS, a fully polynomial time approximation scheme, which basically kind of gives you within epsilon of the optimal solution for the min sum objective, right? So this kind of stylized model under this general setting can give you a sort of a near optimal solution using sort of an algorithmic approach here. And in the last couple of minutes that I have, I sort of want to highlight 2 directions that are very networks-based that we didn't get to in this initial paper, but some of which I'm working on and others I'm hoping others will pick up, which is that, you know, we assumed here that people's shocks are just happening to them and that's it. But in reality, we know that shocks are very networked. So, you know, if I got sick, that's certainly going to be a burden for my family and for my close friends and for my colleagues, right? So we know that, you know, a shock happening to one person is not just an impact on them, it's actually an impact on everyone else. So it has this sort of networked component to it. And people have studied this in the context of banks, financial ruin in banks. And so there's some kind of tools and techniques that have been built there that we might be able to use. But the setting when you're thinking about poor families is very different. So we might ask, how do you incorporate the insights that are already out there, but then also insights that we have from exploring poverty to also intervene in ways that are network informed. And the second one, which I have been actually working on, is related to insurance programs that are already out there. So in my home country of Ethiopia, and really a lot of other developing economies, there are these things called saving circles or Roskas, which are made up of a group of individuals that come together, and it sort of serves as an informal financial institution to kind of buffer against shock. So people come together, they put in some amount of money, and they take out money in some fixed order in order to either buffer from shocks that they're experiencing or, you know, future investments that they would like to make. So there's some work in the economics literature that looks at this. We're looking at a set of models here from an algorithmic perspective to understand how different forms of froskas or saving circles can help or can help families kind of get through periods of shocks. And I'll conclude by saying that if you like these style of problems, this sort of interdisciplinary approach to improving access to opportunity for historically underserved communities, an initiative that I co-founded with Kira Goldner and have been co-organizing with Irene Lowe, Ana Andrea Stoica, who's speaking later today, and Francisco Marmolejo. So the 4 of us organized this initiative, and it's an interdisciplinary initiative. Most of our activities are online. Well, now everything is online, but even before, you know, being online was a necessity, a lot of our activities were online. So I highly recommend that you take a look at our work. And if you would like, you can join us by going to md4sg.com. So I hope you'll think about these problems. I hope you'll reach out. I hope you'll join MD4SG. And thank you so much.
Awkward Zoom applause.
Good Zoom applaud. All right.
Okay, thank you so much. So right now we've got panelists, we've got 100 attendees and a lot more people watching on the live stream. So we're just going to try to do questions from folks broadly. So panelists, this is a good time to start with comments, questions, feedback, and then we'll also keep an eye on the Q&A as they're coming in there. I just want to start out with a comment, which is that I really appreciate the critical focus on the objective function, and sort of coming back to an examination of different plausible objective functions and thinking about the impact on the people that you're modeling. I think that that's one of the things that's really exciting about your framing for me.
Yeah.
Okay. Other panelists, do you want to speak up, and then we'll look to the Q&A.
Thank you. I thought that was such a great talk. Really appreciate it. What are some of the ways people try to estimate shock distributions in the real world?
Yeah, very good question. So there's many ways. This is, I mean, I kind of swept this under the rug here, but this is a whole body of work, right? So people who do empirical work go out into the world and they collect this. It takes years. It takes years and years of work to just go around and say, because the shocks, I just sort of called them shocks, but they're actually very diverse, right? It could be a medical shock. It could be a parking ticket. It could be you lost a job. It could be that a relationship failed, right? A lot of times that comes with a sort of financial shock as well. It could be interactions with the criminal justice system. So people go out and measure these. There is, so the poverty tracker study, which I mentioned in passing, has a data that they collected over a period of I think 3 years, maybe even more, that's collecting these types of shocks, but they're very hard to collect. You could imagine that there's maybe computational work to be done here, estimating these from, say, online activity, which is data that's in some ways more readily available. Of course, it comes with a set of biases, so we have to take that with a grain of salt, but you could imagine also that could be one line of work that we should be exploring that's been a bit underexplored.
Very neat, thank you.
Yeah, thank you, Olivia.
Red, here's a question from Mersad in the Q&A. Have you taken into account where these subsidies are coming from? Because on a large scale, this might lead to inflation that affects everyone, especially the low-income families.
Yeah, so that's a really good question. So I'll say that, maybe this question is better posed for an economist, but I'll tell you what I know, which is that a lot of times, actually, we do have very large assistance programs. Say if you're thinking about housing, we do have actually large housing assistance programs. It's just that they are targeted at higher income or kind of middle to higher income families. So if you look at how much as a percentage we've been investing for housing assistance on low-income families, it's been steadily going down to a point where I think it's just completely unacceptable at this point, actually. So I don't think that, taking some of what we used to actually invest in lower income and vulnerable families and putting it back into that community, I don't think that's necessarily going to lead to sort of inflation. I do think that it is important, though, to think about the sort of externalities that shifting things around my pose. The problem that I presented here, though, is kind of like narrowly bracketed in a way. I'm glad you're asking these broad questions, because in a way we're asking, the budget is there, it was already what you were spending, but maybe you weren't spending it in sort of the most efficient way. But I do appreciate that you're asking, okay, like, why are we kind of treating the budget as fixed?
Great. Ushan, you want to handle the next one from Q&A?
I just marked it for Red or you to handle the question. Sorry.
Okay, sure. Oh. So Kate is asking, thanks so much for an awesome example of math to serve historically underserved communities. What are the ways that these results or future ones could be translated into policy, and what kind of engagement is required?
Yeah, very good question. So that's a really hard problem, but one I'm definitely invested in. So right now, what I've been doing is I've been talking to folks at the School of Social Welfare at Berkeley, where I'm joining as faculty, to understand what problems social workers face in practice just when they're out in these communities and trying to assist families. I do think that it's important to not rush to implementing anything. I think it's important to go out and kind of get a very deep understanding and build trust with all these different stakeholders, including the communities, but also, social work researchers and practitioners who've worked with them for a while. Right now, we're also in the process of building an interactive platform that allows you to translate results like the ones that I showed you, but also other sort of machine learning results that allows you to kind of translate that onto a platform so that a social worker can kind of interact with it and see whether they trust the models that we have, whether they trust the allocations that we have, and if they don't, so that we can get a better understanding of why that is. So your question, Kate, I think is basically a whole research interface that is being developed. So I would love to continue this conversation.
Great. I think we have time for a few more. Panelists, anything from you, or we'll go back to the Q&A? All right. So Laksh is asking, first of all, a compliment. Excellent talk. What a flow.
Good. Thank you.
I know a little about these, but I have a question. Are you assuming that the slope stays the same after a shock? This can be small or certain types of shocks, but in many cases, the income can change following a shock. How's that handled?
Very, very good question. So yeah, so we did assume a lot of independencies, right? So one of the things we assumed was the networked aspect, which I hinted at. The other thing is the shocks. We assumed that the shocks are independent from each other. We assume that the shocks are independent from your reserve. We assume that the shocks are independent from your income, right? All these parameters that I mentioned, we basically assume that they're independent, and you make a commitment for the intervention in the beginning, and that's it. What you're asking here is definitely well motivated. We know that shocks, actually there's empirical work that we're doing that shows that shocks are actually very dependent. Once you experience a medical shock, you're now very likely to experience another medical shock. But also when you have low reserve, you become very susceptible to income shocks, right? So the distribution actually can change in response to where you are on the sort of on the y-axis. So what you're asking here is well motivated, mathematically very, very difficult. I think maybe we need more probabilists on these type of problems. I think also we may have to look to maybe less mathematical ways of understanding how these dependencies affect one another. But yeah, so maybe this is like where the computational work can come in. But yes, very, very good question. Don't have many answers for you, but hopefully we're making progress.
Great. There's a question from Ariel Ndange Pufu. Would you like to ask it yourself, Ariel?
Sure. Yeah, I was just going to ask again about some of the details of the shocks and whether you think that there's a difference between receiving a shock at the end of the month, like say the 29th, versus the beginning, like the 2nd, because I've heard some stuff about that, and you know, you model it as kind of a constantly increasing income, but it really does come kind of periodically.
Yep. Very good question. Yeah. So yeah, we smoothed everything out. We're just saying, you know, you have continuous time and it's just smoothed out over that period. And we're hoping that that becomes like an okay enough approximation about what's going on. Absolutely. You're completely right that if you have a big expense, you know, right when you've received your monthly paycheck versus at the end when you're sort of barely getting by, totally different experiences. Also, even things like how old you are when you're experiencing a shock, right? So one of the types of shocks that people look at is interactions with the criminal justice system, and whether you had that before you were 18 or after totally matters, right? So yeah, so we abstracted all of that away. As in a way, this was a sort of a proof of concept, right? We wanted to do the most stylized model that kind of captured the main ingredients that we wanted and abstracted away a lot of the complexities and tried to see, you know, can you actually make sort of mathematical progress here? And the answer is yes. And so now I think we can start to incorporate the types of questions that you're asking. I will say working in the discrete setting we spent like 1.5 years on that, and then had to like throw away our model and our many insights into it, because it's very hard to study rune processes in this kind of discrete way that you're mentioning.
Great. Okay, thanks so much. So there are a number more questions. We'll get those to you afterwards, Red, so that you can respond to people at your leisure. But for now, we'd like to do our 5-minute break before the next talk. So I will put the schedule back up. And note that we start again in just a few minutes with a talk by the inimitable Steve Strogatz. Okay, see you soon. Thank you so much, Red. That was fantastic.
Oh, thank you. Thank you. Excited.
All right. Welcome back, everyone. And now it's my great pleasure to introduce Steve Strogatz in the math department at Cornell, who's someone that I greatly admire in this space. So I'm especially excited that he could join us today. Steve.
Thank you very much, Moon. I guess it's time to share my screen. Let's see. All right. How about that? No? No. This.
Perfect.
Bingo. All right. Okay, well, thanks very much for inviting me, Moon, and welcome everybody. Great to be here with you. I'll be talking briefly, I hope, about this problem of what happens when a contagion spreads on a network and then mutates at some point into some other strain. The question will be how many nodes downstream from that mutation event will be affected typically. So the work was suggested by a person whose name I'm going to pronounce possibly two different ways. So in Danish, we would say Jonas Juul, and in English, we might say Jonas Juul, and he told me I could say it either way. So there he is. Jonas is a graduate student, just finished actually, at University of Copenhagen, and he came to visit us at Cornell last, I guess it was really just last spring, and it was fantastic to have him. And then he's actually going to be joining us next year at Cornell. Well, we'll see. I mean, maybe virtually, or maybe in real life as a postdoc with me and John Kleinberg and Austin Benson. So the problem that I'm going to describe was really suggested by him, and so he should be getting, you know, essentially all the credit for this, but I'm proud to be part of it too. So first, this word contagion, you know, we think of contagion usually in the context of communicable diseases, especially now that we're talking about COVID. But the concept has been generalized in recent years to anything that can spread on a network from peer to peer. So, you know, it could be rumors spreading, or nowadays misinformation, fake news, or even, you know, it doesn't have to be something negative. It could just be a good idea or an innovation, anything that can be shared on a network. Also, as Reddy had mentioned in her talk, there are applications and real world situations where you might have something quite deleterious, like blackouts propagating in the power grid as, you know, maybe one power station pulls itself off the grid, that puts more strain on other power stations, which then have to pull themselves off, or bank failures was the example that Red mentioned earlier. So all kinds of things can represent contagion. And so, as I say, the question that we're going to be interested in here is to think about the problem where a contagion is going to mutate at some point as it spreads. How many nodes will be affected by that downstream? So in the spirit of doing stylized models, like we just heard in the last talk, I'm going to be doing a hyper-stylized model, and you'll be able to think of all kinds of ways that this can be generalized and improved and made more realistic. And I encourage you to do that. I think this opens up a lot of new questions, and we're certainly very far from realistic here. What I'm going to show you is extremely deliberately simplified in the spirit of, you know, trying to do some math. So, all right, so what's the story? Here, we've got some network of nodes. These are the black dots. And later I'll talk about what kinds of networks we're considering. But for now, just take any network connected. And then choose some node to be, like here, this red dot is going to be assumed to be infected. Now, there are three nodes that it's connected to directly, A, B, and C. And so those edges, we're going to assume, are all equally likely candidates for where the infection will spread next. All right, so you draw on all the edges that have one susceptible node and one infected node. They're all taken to be equally likely, and then pick one of them at random and spread the infection. So in this case, at the next time step, it happens to go to B. All right, now let's play this out for a few more steps. So let's suppose that at time 2, maybe this origin node O itself happens to spread the infection again to C. I mean, it could have also been that B spread the infection to one of the nodes it's connected to, but that just didn't happen. Anyway, as time continues, eventually for this extremely simplified model, everybody's going to get infected, right? In the jargon, this is an SI model with infinite transmissibility, susceptible and infected. Nobody recovers Nobody is removed from the population. There's no issue of the probability of transmission. Somebody is going to get it at each time step. All right, so this is an extreme limit. But anyway, there are issues raised by this because, first of all, the network itself could be sort of tricky, like this one is some strange network. But if we want to think about the issue I mentioned of mutation occurring somewhere in the network, and then ask how many people downstream get this mutant form, well, a helpful construction is the following. Let's sort of redraw the history of this epidemic in the form of what I'm going to call an epidemic tree. This is just a way of showing who got the infection from whom. You know, it's just who infected who. So here at time 0, there was only the origin, the seed. At time 1, it passed it to B. At time 2, it passed it to C. And after 8 time units, you can see the sort of the paths of who infected who. Now, this final thing is what I'm going to consider the epidemic tree. It's like a genealogical tree, and you could even think of these higher up nodes as being parents or ancestors of the lower down nodes in the tree. What's sort of interesting is that we have built a tree from a graph that was not itself a tree, right? The original graph was not necessarily a tree. It can have loops. But if you're showing sort of this causal structure of who passed the infection to who, that does create a tree in this simple model. Now, suppose that a mutation event occurs somewhere, like in this example. I'm going to suppose that at this time, B became mutated. You know, in the case you sort of have in mind is maybe it's a more pernicious strain. Doesn't have to be, though. It could just be some variant. But anyway, so suppose B is mutated, and we still have the same epidemic tree. We're going to assume not that like B is more infectious or anything else. We're going to use the same epidemic tree, but just show that all the descendants of B now acquire this mutant form of the infection. And so that's the kind of question we want to look at is, how many descendants are there, given that it happened to occur here at B? But of course, if it had happened at C, C has no descendants. And if it had happened at A has 3 descendants. So the right question is a statistical one. What are the statistics of the number of descendants, given that the mutation could have occurred anywhere, we'll suppose uniformly at random? So here's an example of a big epidemic tree where if the mutation happened to occur at this point marked in red, not too many descendants for that example. On the other hand, if we had a picture like this, where the mutation happened here, all of these nodes will be descendants. You could have a very big avalanche. And so the math question we wanted to look at is, what can we say about the distribution of the number of descendants, depending on the original network? How does it depend on the original contact network for this very simple model of contagion? So you could phrase it this way: given a random node for where the mutation occurs, what's the probability it has D descendants? Okay, well, we just published a paper about this, which if you're curious, we would be thrilled if you would read it. Descendant distributions for the impact of mutant contagion on networks. It's in this brand new journal, Physical Review Research, which is an online open access journal. So just published a few days ago, July 1st. It's also on the archive if you would rather see it there. So here's a little example, sort of everyone's favorite graph to start with, the graph that is barely a graph, you know, where everyone is connected to everyone, the complete graph. And so let me try to walk you through what I'm showing here. First, we ran simulations to see what would happen. So think about how a simulation of this process would take place. You'd start with a seed to get infected. As I say, it then propagates its infection with equal probability to one of its susceptible neighbors. And then that continues on and on. And when the whole thing is done and everybody has been infected, we count up how many descendants are there of each node in the epidemic tree. Right, that would be a descendant distribution for one realization of our stochastic process, where there are all kinds of stochastic choices, right, about which edge do we select to pass on the infection at a given time. So to overcome all that sort of randomness that occurs just from particular realizations, we ran 1,000 simulations of this stochastic process. The network was size 10,000. And then we average all those descendant distributions to show one picture. I don't know, hope that's clear. So what you're seeing here, I mean, just to orient you, as I say, 10,000 nodes, you'll notice this one dot here. This dot is at a value of d of 10 to the fourth. This is if we happen to put the mutation at the node at the very top of the epidemic tree, at the root, everybody will be a descendant of that node. And so, of course, it will have 10 to the fourth descendants. But that's pretty abnormal. And we've normalized things so that this would correspond to a unit of 1 on this scale. So what you're seeing here then for the rest of the data in these dots all piled up is that these correspond to enormous descendant, clusters that are infected. Those are rare, right? Those don't occur very often. Whereas if the mutation occurred near the bottom of the tree, down near one of the twigs, there are a lot of ways that can happen, and then they don't produce very big infected clusters. So this is the picture of the size of these infected clusters as a distribution. And you'll notice that since I'm showing it on log axes, the fact that it looks like it's sort of forming a straight line is indicative of a power law. And there is indeed a power law here. This is falling with a slope of -2. So in fact, for this simple graph, we can work out the exact formula for this average probability distribution for the descendant distribution. Can I ask a dumb old man question while I'm in the middle of this? So as I'm lecturing, I see my PowerPoint presentation, but I also see people's faces on the right side of my screen, and it's covering a formula that I'm trying to show. Are you seeing the formula, or are you seeing the faces of people? So let's.
PD.
We see the formula.
What's that?
Is the formula PD equals 1 over, et cetera?
Yes.
Yeah, we see the formula.
It's not obscured by the Zoom.
That's everyone's own setup controls how they see it.
All right.
You can move the pictures.
Good. I've taken away your faces. Okay, sorry to be 61. All right, so anyway, the dashed line is this analytical formula. I'm not going to go through the calculation, but you're welcome to look at it in the paper. It's not a very hard calculation. And I mean, it's interesting. It's a nice little exercise. But the point being that at large D, it behaves like 1 over D squared. I should also mention that this calculation was done in a different context by Paul Krapivsky and Sid Redner in an old paper in Physical Review E about networks growing by a node copying mechanism, which is essentially an isomorphic problem to what we're doing here with building these epidemic trees from this infection process on a network. Okay, so we have this 1 over D squared tail. And the thing that's interesting and that I want to stress is that that keeps occurring in other examples. Like suppose instead of a complete graph, you look at this infection propagating on a random graph. The classic random graph would be the Erdos-Renyi random graph with, where you have a complete graph, except instead of putting in the edges with certainty, you put them in with probability P. Then, on average, each node will be connected to n-1 times p others. So I'll call that Z, the average degree. That's a very classic vanilla kind of random graph. There's another interesting kind of random graph in which every node has exactly degree Z. So it's a Z regular graph. But the way you should think of it is take a node, give it Z half edges sticking out of it, and think of throwing all those nodes with their half edges in a big bag, and then choose those stubs, those little half edges, and connect them at random to make a Z regular graph, which is otherwise random. So that's called the Z regular configuration model. And so we also simulated our infection process on that kind of a graph for different values of Z. And what I'm showing here is the descendant distribution for 3 examples. The Erdos-Renyi example with a Z of 10 in these regular random graphs with 2 different values of Z. And the axes are normalized in a certain way that all the data fall on top of each other. You have what a physicist would call data collapse. the way we were able to get this data collapse, incidentally with the slope of -2 again, down here in the tail, the way we get this data collapse is by working out the exact formula for the descendant distribution for these cases. It turns out to depend on z in this way with this factor z-1 over z-2. And then this b is actually a beta. This is a beta function of 2 arguments. This beta function, a special function that's related to the gamma function. Anyway, it pops out of the analysis. And the interesting thing is that asymptotically for a large d, oh, okay, wait, I should say one more thing. What's this x tilde? X tilde of z down here in the x-axis is this factor, or this term sitting here that's being added to d. So the formula is telling me how I should normalize the picture. Incidentally, this same factor appears out here in front of the beta function. So if I pull it over in front of PD, that's why I have PD on the vertical axis times this x inverse. So this is the correct way to normalize everything. All the data do fall on this curve. And lo and behold, you again get this d to the -2 scaling, which, by the way, you should notice is a heavy tail, right? I mean, this is a probability distribution which would have both infinite mean and variance if you were interested in that. So we do have a pretty high probability of enormous infected clusters. So the question then arises, I mean, we did several other examples with random graphs and of various types, and they all show this d to the -2 scaling in the tail. And so why? What's causing that? And the answer is pretty simple. It's going to be true generically for any network that is effectively infinite dimensional. Now, when I say infinite dimensional, I mean like in the way that a physicist would talk about a 2-dimensional lattice as being 2-dimensional. These kinds of random graphs are effectively, if you assigned a dimension to them, they would be infinite dimensional in the sense that if you sort of thought about surface to volume ratios, in such a graph, the surface and volume of a blob grow equally fast as you increase the radius of the blob. So think about a sphere, like all the nodes that are hops away from a given node, where r is the radius of this, so to speak, sphere. Then the surface area of the sphere, it would be all the points that are exactly r hops away, and the volume of the ball would be all the nodes that are within r hops of a given point. And so that in random graphs of the type we considered, both the surface and the volume scale in the same way, they grow equally fast. And so in that sense, all these networks are infinite dimensional. And with the kinds of techniques that we use in the paper, we're able to prove that you always get a d to the -2 scaling in the tail. Now, just to underscore that this is a property of the infinite dimensionality, if you just try simulating our infection process on a 2-dimensional square grid with nearest neighbors, you'd get a very different behavior of the descendant distribution. I mean, it behaves in this funny way. I'm showing here for comparison a slope of -2. So honestly, we don't even understand what this curve is. We haven't calculated this analytically. We don't know how to do it. That could be an interesting problem for someone to sort of redo everything we did for random graphs on finite dimensional lattices. We're not up to that, but someone who's good in statistical physics or probability could probably figure it out. It may even be in the literature. We're kind of beginners in this field, so it may already be known, but we didn't know. So anyway, the infinite dimensionality is important, and what's really convenient about that is that lots of real-world graphs are effectively infinite dimensional. For instance, take a social network like this subgraph of Facebook that comes from a big data collection that Yuri Leskovich published and has, in this case, 4,000 nodes, 88,000 edges in it. What we're showing here is if we simulate our infection process on this little piece of Facebook and run it until it has, say, exactly 100 people infected with the mutant form, or 400 or 2,000, whatever, we get data that falls exactly on this kind of curve, though it has some finite size effects at the end, but ignoring those, you get behavior that falls on the analytical prediction that you would get by pretending that the subgraph is just a complete graph, which it's not. But if you pretend that it is, it works. So in that sense, real networks often behave as if they were infinite dimensional. And so let me close with this little point, which is that this theory of ours with its -2 power is borne out in some actual data on something spreading on a network, a kind of contagion, which is not a disease, but the spreading of memes. You know, the kids like to send memes around. When my daughters use memes nowadays, it usually means some kind of image with funny writing on it to make a joke. But in the old days of memes, memes just meant anything that could propagate and mutate, sort of analogously to genes when Richard Dawkins coined the term memes. So memes can evolve. And in the context of social networks, they were looked at by Lotte Adamich and her collaborators. They were interested in the way that memes spread on Facebook, but they were looking at very early memes in the year 2009 and 10 and 11, back when memes were text rather than images. And so they were able to see when these memes mutated because you could see little differences in the text. For instance, you know, sometimes people will either, like in those days, they didn't actually have a share feature on Facebook that was automatic. You had to copy and paste whatever text you thought was worth resharing. And so sometimes people would copy it wrong, or sometimes they would deliberately alter it to make it funnier or stickier. So here's an example of what memes used to look like. This is the appreciation meme that ended up getting 71,000 copies of itself made. It said somewhere right now, a nurse is getting yelled at for being late with pain meds, while holding her bladder because she doesn't have time to pee, starving because she missed her break, being pooped, peed, bled on, and so on and so on. And then, so that was a very popular thing to share back in those days, but 18,000 people shared it differently. They changed it. Somewhere right now, a nurse is getting yelled at for being late with meds, holding their bladder while holding her bladder, because they don't have time to pee, starving, etc. And this poor nurse is being puked on in addition to everything else. So this person, you know, whoever started this variant of the meme felt they had improved it. It was also very widely shared. So Lotte Adamich and her collaborators looked at some of the most widely shared memes and looked at the equivalent of our descendant distribution. And what they found was, when they graphed it on these log-log plots, that the most popularly shared memes were following a line with a slope that turned out to be very close to -2. When they computed the best fitting power law exponent, you can see it as a peak right around 2 for this negative slope here. So there is reason to think that this -2 tail really does occur out in the wild for networks that are effectively infinite dimensional. So I think that is all I have for you. Just to summarize, what we did here was provide theoretical results for descendant distributions on a family of different kinds of graphs, found that lots of them had this d to the -2 dependence, and that's due to the infinite dimensionality of lots of random graphs and other real world kinds of networks. It does seem to be consistent, at least with some of the data that's out there. So I don't know how general it is, but I invite you to think about questions like this if you found them interesting. So thanks to the NSF for supporting us, and I will now stop. Okay, thanks very much.
Thank you, Steve. That was great.
Thank you.
Okay, so as folks who are attending are getting their questions ready for the Q&A, I know you have a couple questions from us on the panel. And so I'll just abuse my position to start by asking. I'm really interested by what you gain and what you lose with the tree representation instead of the full graph. And so, sorry for the siren in the background.
Yeah.
So you could have things appear sort of far apart in the tree because of the pathway of how the infection occurred, even though they were close to each other in the original network. And it seems to me that partly the way this becomes reasonable is because, as you said, it's SI and no R. You don't have people recover, and so you don't have them re-enter the susceptible pool, and maybe things that makes it more reasonable. But I could also imagine that having trees as your objects at the end of the day lets you do more powerful, you prove better theorems. So I just wonder about the balance of, like, trees let us do better math versus trees are really the realistic vehicle for what it is that we want to measure. I was just hoping you could talk a little bit about that.
Really good question. Yeah, very interesting point. So we haven't explored these others. I should say, for the sake of honesty, that this construction of epidemic trees has been out there in many forms, in many branches of science where people think about networks. So, you know, in different fields, they're sometimes called dissemination trees. They can be called causal networks. They're structure of social diffusion. I mean, people have been looking at these in fields from social networks to epidemiology to graph theory. So that construction in itself is not new. Another point about it is that it doesn't always necessarily make a tree. In the context I have here, where if you just have one infected ancestor, you get infected. You know, there are things that now people call complex contagion, as opposed to simple contagion. So a complex contagion would be like, should I stop smoking? You know, maybe I will if one friend of mine stops, but maybe I need all the friends in my neighborhood to stop, or maybe a certain number, a critical threshold number to stop. So for complex contagions that are quite relevant for lots of social phenomena where you need more than a certain threshold of people or nodes before you will actually switch or catch the infection, catch the innovation, there you would not get epidemic trees. You would get graphs that don't have loops. I guess they're acyclic graphs because you can't go backwards. I mean, because there's this forward directionality in time, there's the causality. So you have a directed acyclic graph, but it won't have to be a tree. So anyway, back to your question, Moon. I mean, how much are we losing? Like, you're right, that we're losing network position by showing the epidemic tree. Honestly, I don't know. You're right, it's a good point. I mean, the thing that we found intriguing about looking at the trees is that we feel like they represent a mesoscopic scale in network theory that hasn't been explored very much. There's the micro scale of individual nodes. There's the macro scale that we're used to of giant components in random graphs and things like that. But giant components leave out this causal information of who infected who. And that's at least retained in the tree. But the tree does, you know, the tree loses time, it loses certain aspects of position. So it's a question whether this is a useful abstraction or not. I mean, we think it is, but you're right, it's sacrificing certain things. So remains to be seen if there are better sort of mesoscopic pictures that would sacrifice less, but still be tractable. Don't know.
Great. Jordan, I think you had some thoughts or questions?
Oh, and we were chatting on the chat, but maybe since I was just about to type this, I mean, just to follow up on this question, like, do you literally get it? If I start with some graph and then do some SI model, which is gonna, where a node is exhausted, like once it's been infected, so we don't see it anymore, I guess you'll end up with a spanning tree for the graph. Like that's what your tree will be. And I wonder if we know stuff about what that, I mean, the subject of probability distributions on spanning trees is super interesting. I've learned a lot about it from Moon. And I wonder if we know something about whether that spanning tree is anything like uniform or like what kind of distribution on that very, very interesting set / group / torsor of spanning trees. I had to get that in, Moon, sorry.
I applaud you.
Torsor! Yeah, what we're talking about.
Well, yeah, good point. I mean, I can tell you the referees of our paper and the few iterations that it
wasn't me.
Oh, okay, thank you. Referees were pretty unimpressed with the results. So just, you know, there was the feeling that a lot of this is trivial. And so I wonder if these more sophisticated referees knew something about the kinds of questions you're asking about. That maybe, I mean, the main objection was, we know it's got to be -2 because it's behaving like a stochastic process called the Juul process. The Juul process is a simplified model of something that replicates and can mutate, but assumes kind of fully connected, effectively on a random graph. And it goes back, you know, a long time, it's decades old. So given that, you know, there's a sort of intuition that all infinite dimensional processes of this type will behave like, or that these will all behave like the Juul process, basically. And actually, a lot of Adamich and collaborators knew that, and they explained the -2 with that intuition. We felt like our contribution was to show that intuition is sound by explicitly calculating results of descendant distributions for a few other explicit network families. And it really does work. But, you know, like I say, our referees seem to know that already. So I don't know why they knew it. They never actually, like a referee should tell you, idiot, you could have just looked this up in this paper. No one did that. So I think it might be folklore. Or maybe they were just too lazy to give us the right citations. But I agree with you. It seems like it should be out there.
Jill, question?
Yeah, I was wondering if you looked at all at spatial random graphs or like geometrically constrained or embedded random graphs, like point process based graphs or
Very
something.
good question, right, sure. Did we? I don't remember. It might be in the supplementary information, but I honestly think we didn't. But it's natural, certainly a good thing to do. Yeah, I mean, just to be completely clear, hopefully it's obvious, but you know, as you say, there's a lot of different families of graphs that should be looked at. And as Moon hinted at with mentioning SIR models where you have recovery, or we could think of SIS where after you're infected, you kind of instantly come back to being susceptible. You don't spend any time being recovered. Those are all very natural, different dynamics to look at, and they may affect things. So there, yeah, it feels like there's a good playground here to consider. The other thing is, we only looked at one mutation event. You know, I mean, really what might be happening is that mutations are ongoing all the time. There are variants being created all the time. So you could think of what we did as like the limit of extremely rare mutations, but what about if there's a finite frequency, a non-zero frequency for mutation? So yeah, no, good question about geometric random graphs. That would be very good next thing to look at.
Yeah, I was just thinking because they have different asymptotic dimension properties. And
Yes, good. Thank you.
Here's a question from Takayuki in the audience. Is the result related to the mechanism that makes the degree distribution for the Barabashi-Albert power model, for the Barabashi-Albert model, a power law with exponent -2?
I think it is related in that the way we do the analysis uses rich get richer mechanisms, which underlie the same power law in the Barabashi-Albert work. So you can see there's a rich get richer thing happening here in that if I suppose I'm the mutant, you know, I've got a bunch of descendants who are also now mutated, then every time one of them passes along the infection to someone else, those new descendants also become my descendants. It's actually like, we're familiar with this in the academic world where, you know, if you look at our academic genealogical trees on math, whatever that place is called, the math genealogy site, I'm given credit for all the descendants of my students who now have PhD students. So to the extent that I have a lot of descendants, I get even more when they have descendants. So yes, there are these rich get richer effects through that. And those are very much what's happening in the Barabashi-Albert analysis too.
Andrea, did that cover your question?
Yeah, I think that was very related. I was wondering if you have a model of growth in which you have a power law, then would this kind of reinforce the distribution that you see in the contagion? But I think it's related to that question.
I think we might have an example or two in the paper, in the supplementary information about doing this on scale-free networks of the type you're talking about. And they were actually hard to analyze. We couldn't quite figure out our results were not clear to us what they meant. So I think that's another interesting open problem, to look at graphs, either the original Barabashi-Albert construction or using configuration models with degree distributions that have power laws. Those could be tractable maybe, but we didn't solve them.
Okay, maybe we have time for a few more. Here's a question from Rose in the audience, who's asking how likely it is to be able to use this model predictively. Can you predict the state of the nodes with your mutation model?
Oh, I don't know. I don't see how, because the way the model is, as I say, was structured is that at any given time where the infection goes next was just uniformly random over all possible places it could go next. So I don't know what kind of predictions could be made other than very gross statistical ones, you know, based on doing many realizations. I mean, one thing that's sort of interesting about it, it does give a prediction, if you want, for the typical size of a big mutated component. Given that you have this 1 over d squared, you know, when you integrate d against 1 over d squared, you're going to expect a logarithmically big mutated component because you're kind of integrating 1 over x more or less. So whereas the giant component, the giant infected component will scale with n, this predicts that the giant mutated component is only logarithmically big. So in that sense, it is really mesoscopic again. It's intermediate between the giant and the scale of individual nodes.
Great. Well, it's time to transition, but I'll just make a note that in the looking over the Q&A, quite a number of people were intrigued by what you pointed out about the square lattice and kind of seem to think it's worth exploring other kinds of planar graphs and
Yes,
explorations in that direction, to which I guess you would say, go for it.
definitely. Yeah. Yeah. We don't feel any ownership about this. We're happy to have people solving the problems we didn't know how to solve.
Excellent. Okay, well, let's thank Steve again and take a little break before the next talk at 11:10. Thank you, Steve.
Okay. Thank you. Thank you.
Let's get started back up. So our next speaker and the last speaker of the morning will be Kimberly Glass from Harvard Medical School, whose talk is called Data Integration in Network Medicine. Kimberly.
Excellent. I'm going to go ahead and share my screen, start my slideshow. And then before I get going, I always want to ask, are you guys seeing the actual presentation or are you seeing presenter mode? Sometimes things get switched.
Right now, it's not yet. You haven't hit start present yet, I think.
Oh, it must be delayed because it's presenting on my computer.
I see.
Has it come up yet?
Not quite. Maybe quit and restart the share.
Yeah, I can do that. Okay, can you see my PowerPoint at least?
Yeah, we see the slides and the whole PowerPoint interface.
All right. I started the slideshow. Did it start this time?
Yes, but with your presenter.
Excellent. Perfect. Now I can actually fix this.
Okay.
All right, can you now see the actual presentation? Good, okay. All right, so first off, I'd like to thank the organizers for inviting me to this really fabulous conference. It's an amazing collection of speakers and I feel really honored to be a part of it. Today I'm going to talk about my area of research, which is about data integration in network medicine. And kind of to get started and to give a background onto why this is important, I'd like to talk about what networks can actually teach us about biology and medicine and disease. And I like to illustrate that point with a story. And that's the story of Susan and Jane, who are two young children. They grow up down the street from each other. They play together. They're both happy and healthy children. Over time, they grow up, they get older, they live their lives. Susan likes hamburgers. Jane likes to drink wine. And then, as we all do, they eventually get old and they get sick and they go to the doctor. They have little frowny faces now because they're both sick. And something happens. The doctor gives them the same medication because they both are sick in very similar ways. But what happens is Susan gets better. She responds to the treatment, but Jane doesn't. Jane ends up not responding and she's still sick. How can we actually explain this? Well, one way we can explain this is through what's known as their molecular networks. When Susan and Jane are young, they both have healthy molecular networks. They're different networks because they're different people, but they both function in such a way that they have healthy phenotypes. Then as they grow up, through various environmental factors or genetic factors, these networks change. And they change in such a way that when Susan gets sick, her network can respond to treatment. But when Jane gets sick, that same drug does not help her. And so this is really what network medicine is all about, is how do we use networks to try to understand diseases. And this is a quote adapted by a paper from Laszlo Barabasi in the New England Journal of Medicine in 2007, which states that the study of cellular disease and social networks, which aims to quantify the complex interlinked factors contributing to individual diseases, and that really defines network medicine. And there's a couple key principles to network medicine that really distinguish it from a normal approach to medical analysis. And those are the following, and there are many others, but these are some of the key ones that my research centers around. First off, network medicine takes a holistic rather than a reductionist approach. We don't study single genes or single proteins or even single variants, but really we try to understand the system as a whole. And in particular, we try to look for emergent properties from the entire network, right? We're not looking for individual links and individual connections. We're trying to say, how do changes in the networks actually give rise to different types of diseases, different phenotypes, different manifestations? Network medicine employs systems biology methods. And the key component of network medicine that is most aligned with my area of research is that network medicine often deals with the construction of molecular networks. We don't know these networks a priori. We can't just do a simple test and get them. We actually have to reconstruct them. So to put things into perspective, network medicine really took off because of the following fact. And that is with the in 2001, the cost of generating sequence information for the human genome has fallen. It's fallen drastically. And this follows a number of different technologies. So back in the early 2000s, there was Sanger sequencing, and to sequence one human genome cost in the order of $10 million. No one could go to the lab and just do that. We had a handful of human genomes that we could really try to study. Then around 2007, up until about 2015, we hit the realm of what's called next generation sequencing technologies, where a number of companies developed better, more high throughput approaches to sequencing the human genome. And ever since about 2015, with the introduction of one of the Illumina technologies, we're now in the realm where to sequence one human genome costs about $1,000. For most of us, that means that if we have a debilitating disease, we'll figure out how to get $1,000, go to the doctor, sequence our genome, and the goal is to say, can we look at our genome and figure out what might be causing this disease? So a little bit of background for those of us who aren't used to thinking about biology and how this all works. When we go and we get a human genome sequence, we basically will go, you take a sample, say of blood or of tissue, and this goes into a sequencing machine. And a series of letters come out, the DNA base pair code. And what happens is that if you have 100 people go into the lab and 100 people get their DNA sequenced, you're going to have 99.9% of the same data come out. What makes me and Steve and Moon and Reddy all different is actually a very, very, very small fraction of our DNA. So this becomes a very complex problem very, very quickly. It becomes even more complicated when you think on the issue on the individual person, and that every single cell in our body all shares the exact same DNA, right? But we all know that a heart is not the same as a lung is not the same as a liver is not the same as a brain, and the brain is not the same as a bladder, going through my little cartoon here on the left. So we have to ask the questions, what in the world makes a heart a heart? What makes a liver, right? It's not just the genetic code, there's more to it than that. And so in order to really understand this phenomenon, we have to understand that DNA isn't just a sequence of letters. DNA is packaged together in a very specific way so that certain elements of the DNA that encode important information for biological function can be accessed at different times and in different ways. And so this is just a cartoon showing that there's a physical structure in which how the DNA is packaged, and that gives rise to the differences between these tissues. So DNA is packaged differently in different tissues, but even given that, how do we actually understand the information that's encoded along the DNA? So taking back a step to some introductory biology, introducing some terms so that hopefully you can follow the cool network stuff that I will get to in a minute. The human DNA contains approximately 25,000 genes, and I put in parentheses protein coding genes because they're different types of genes, but the ones we're most interested in generally are protein coding genes. Now, a small subset of those genes contain the information to make a very special type of protein. This protein is called a transcription factor. Now, what happens is transcription factors can actually go and they physically bind to an area of the DNA that is right to the left, called upstream, of a gene. And by binding that DNA, they're able to actually control or regulate the behavior of the downstream gene. And this is called gene regulation. So why study gene regulation? Well, study gene regulation because of biological processes. It's related to that initial story I told you of Susan and Jane, right? What's happening is the information flow through their two molecular networks is different. It's not just about differences in the edges, but differences in how the information and the connections to those edges flows through the network, the idea of biological processes. One important way to model these biological processes is through what is known as a gene regulatory network. And that's the type of network that my research centers around. And a gene regulatory network has a very particular structure. In a gene regulatory network, the nodes are genes and or the proteins they encode. They can be equivalent for each other. Edges are relationships between those genes. And most importantly, those edges are directed and they indicate causality. We want to actually model the processes, how one gene's behavior can influence the behavior of other genes, causing a cascading process. And then finally, why study gene regulation? Because by comparing these networks in different people and in between different types of disease states, we can actually understand differences in the networks, alterations in biological processes that might give rise to these differences. So this seems like a tractable task, but it's actually quite complicated. We can kind of think of a regulatory network as being in a black box where we can't actually directly measure it, but we can measure a bunch of different types of genomic data. And here we can measure different types of omics data, such as epigenetics, gene expression, etc. And what we want to do is we actually want to reverse engineer from this data that we've collected, the underlying regulatory network, right? Because we can't just measure the network directly, we can only measure these outputs. And I put on the right a cartoon. It's a lot like the story of the blind man and the elephant. Every single person in biology are studying a different type of data, and in really it's all looking at the same underlying process. So how can we, as network scientists, actually wrap our head around these complex interactions and what this data represents? And for that, I'm going to walk through some of the very basic mechanisms of gene regulation and show you how we can translate that into a network problem. Well, gene regulation starts with these special type of proteins I mentioned earlier called transcription factors. What happens is these transcription factors do not act in isolation. They actually come together and form what are called protein complexes. And these bind together. These cause protein-protein interactions, which are in a sense a network themselves. You have these three nodes that are all connected to each other in a little triangular graph. These protein complexes then go and they bind upstream of the gene, as I mentioned earlier. These can be captured in what are known as protein-DNA interactions. By doing this, they're able to recruit a special protein called RNA polymerase, which then transcribes a gene, creating what's known as an mRNA product. That is gene expression. So when people talk about a gene being expressed, this is what is occurring. The gene is getting an mRNA product. This is then translated into a protein, and the entire process repeats itself. So what happens is, in general, we actually have three different sources of biological data: protein-protein interactions, gene expression, and protein-DNA interactions. And these all represent the same underlying biological process. So can we use this information to actually build a network model of gene regulation? So over here, I show you how we do this in a network framework. We take three sources of genomic data: the protein-protein interactions, the protein-DNA interactions, and the gene expression data. We basically transform each of those into three network representations: a network between pairs of transcription factors, a network from transcription factors to downstream genes, and a network between pairs of genes by looking at the correlation of genes expression patterns. We can then actually create a multi-layer, multi-tier network from these three networks. Where on the top, we have the connections between the circles or the pairs of transcription factors. In the middle, we have connections from transcription factors to genes. And on the bottom, we have connections between pairs of genes based on shared behavioral patterns of those genes. We then apply a message passing framework to refine these networks. And the reason we do that is biological data is messy, It's noisy, none of it is correct, but by comparing the network structures, we can actually highlight common structures and get to a more complete representation of the system. And we do that through two main steps. One is calculating the responsibility of transcription factors to regulate their genes, and one is to calculate the availability of genes to be regulated by their transcription factors. And we do a message passing approach. And I'll very briefly describe how we do this in our situation. So the first thing we do is we estimate the ability of genes to be regulated by transcription factors by comparing gene expression data with regulatory information. So in this case, consider the node I, which is a circle and a transcription factor, and node J, which is a square and a gene. If we want to ask the question, does node I regulate node J? We can say, well, does node I regulate a lot of the same genes that gene J is highly co-regulated with or co-expressed with? And what we can say is that gene J may be regulated by transcription factor I if it is highly co-regulated with the other targets of that transcription factor. Similarly, we can turn this problem on its head. It's a graph problem, so we can flip it. And we can ask the question, well, should genes J and K be co-regulated? Maybe we missed that in the expression data. Maybe there's all sorts of secondary or tertiary factors that that cause the signal to be hidden. And we can answer that question by saying, well, gene J and gene K may actually be co-regulated if they're both targeted by the same set of transcription factors. And we can pass information back and forth between these two data types or these two networks, refining the structures in both so that they reflect common elements. Similarly, we can take information from our protein-protein interaction data and pass it to our regulatory network. And we can do that as follows. If we want to know if transcription factor I regulates gene J, we can say transcription factor I is more likely to regulate gene J if that transcription factor has a high number of protein interactions with other transcription factors that regulate gene J. Similarly, we can turn the problem on its head and say, well, maybe in our interaction data, we missed a link, right? There's all these problems of spurious and missing links in these data. So maybe two transcription factors should form an interaction that was missed in our biological data. In this case, we can say transcription factor I and transcription factor M may interact if they both target many of the same genes, and we can pass the information back and forth and back and forth. And this creates a framework that we call PANDA. And the way PANDA works is as follows. We start with what we call a transcription factor motif scan, and it's a confusing wording for someone in the network community who's used to thinking of motif differently. But what essentially we're doing is we're looking for patterns of transcription factor in the DNA sequence that occur upstream of the gene. We can use that to create an initial bipartite network from circles to squares or from transcription factors to gene. And this creates an initial regulatory network. We then can create two other networks from our protein interaction data and our gene expression data. We use these to estimate the responsibility and availability, as I described, using a similarity measure that is akin to the Tanimoto similarity. We combine this information together, knowing that we want to merge all the different types of data. And then we flip the question on its head, like I just described. And we say, well, if we know something about the regulatory network, we should know something about how transcription factors work together and how genes are co-regulated. And then we can repeat this process again and again and again until essentially all three layers of the networks converge into something that is consensus. So in general, we've applied this to biological data. And on the right-hand side, I showed the flow of how we normally apply this to biological data. But for this audience, I wanted to highlight that the conceptual framework of PANDA is actually fairly general. PANDA considers two types of nodes and three types of edges, namely transcription factors in genes, and then edges between the pairs of transcription factors, between pairs of genes, and from transcription factors to genes. So in practice, we've used this to construct gene regulatory networks. In principle, it could be applied to any situation in which we have two different types of nodes and three different types of data, and we want to merge those together. So we've applied this to a lot of different biological situations, each of which could be a talk in and of itself. And just to highlight the utility of this approach, I wanted to dig into one particular application. We applied PANDA to understand how gene regulation behaves in different tissues, that kind of initial problem I posed at the very beginning, where we have the same DNA in different tissues, but they all behave very differently. So in that case, we had gene expression data that we collected from the Genotype Tissue Expression Project. And very, very briefly, the Genotype Tissue Expression Project had gene expression data assayed from almost 10,000 different people. It's a lot of different biological samples. And we were able to group these 10,000 gene expression samples into 38 different tissues or tissue sites. Based on this, we could combine co-expression information from each of the 38 tissues with other information about the network structure, such as protein interactions and protein DNA or transcription factor gene interactions. And by doing this, we created 38 tissue-specific networks, namely one network for each tissue. And we analyzed these networks in many different ways. And in one way I wanted to highlight in particular for this audience is we looked at the centrality of these networks. So the first thing we did is we looked at the degree of tissue-specific genes in each of these 38 tissue-specific networks. So at the plot at the top, you can see the 38 tissues aligned from left to right. And you can see that if we look at the degree of genes that are tissue-specific in that given tissue, so for example, taking testes-specific genes in testes, and compare that to the degree of the genes that are not tissue-specific in that network, so all genes in the testes network that are not testes-specific, we can see that tissue-specific genes actually are depleted for regulatory edges. They have a lower degree than non-tissue-specific genes. We then did the exact same thing for the betweenness centrality. We calculate the number of paths to all the tissue-specific genes in their tissue-specific network, and the number of paths to non-tissue-specific genes in those networks, and we looked at the ratio. And we see that tissue-specific genes are actually enriched for regulatory paths. This is really cool, right? Does this mean then that we can actually identify tissue-specific behavior by high betweenness but low degree, basically critical points inside the network? And we quickly learned it's actually more complicated than that. And so to illustrate that, I'm going to kind of turn this data a little bit on its head. So think about this in this way. We have these two graphs where I've looked at each tissue individually and looked at tissue-specific genes and non-tissue-specific genes in that network. I can collapse all this information together and look at the distribution of these values across all tissues. And so that's what these plots here show. The red line is the distribution of the degree of genes that are tissue-specific in a given tissue-specific network. And the black line is the degree of genes that are not tissue-specific in that given tissue network. And what we can observe is as follows. Tissue-specific genes are depleted among network hubs, right? We see that the red line is significantly below the black line for these highly ranked genes, the genes with a high degree. But low-degree genes are not necessarily more likely to be tissue-specific. They're equally likely to be tissue-specific or non-tissue-specific. Similarly, there's a very interesting pattern among betweenness centrality, and that high betweenness genes are just as likely to be tissue-specific as non-tissue-specific. However, non-tissue-specific genes actually tend to be avoided in the regulatory network paths, right? In other words, tissue-specific genes don't necessarily have high betweenness, but they have at least some measurable betweenness. They have a betweenness greater than 0, they're more likely to. So what does this actually mean for biology? Well, it means that tissue-specific regulation does not occur in dense portions of the regulatory network. It doesn't it's not caused by the formation of tissue-specific hubs. Instead, tissue-specific genes are central to the regulatory network on what I would call an intermediate scale, due to the influence of tissue-specific regulatory paths. And finally, when we kind of take a step back and look at this all together, what does this mean? It means that tissue-specific edges are built on an existing regulatory framework that's common to all tissues. And they're built on there in such a way that tissue-specific regulatory access is given to certain genes, namely tissue-specific genes. And so this is a story that I think really exemplifies why it's important to build accurate and informative gene regulatory networks. And I know I only have about 2 to 3 minutes left, but I wanted to spend the last bit of my talk going back a little bit to talk about something we've been doing more recently. You may or may not have noticed, but I started the talk with a little bit of this slide here, saying differences between tissues partly manifest because differences in the structure of how the DNA is packaged together. But then I never used any of this information. This information about how the DNA is packaged is called epigenetic information. And so how does epigenetic information manifest in the structure? Well, it manifests as follows. If we have these transcription factors that normally come together, but the DNA is packaged in such a way that it's wrapped around a nucleosome or a histone, there's actually a physical impediment so that transcription factors cannot bind to DNA, they cannot recruit RNA polymerase, and the gene is not expressed. How is this actually formed in a regulatory network? Well, when we normally build a gene regulatory network, we do so as follows. We look along the DNA, say this black line here, for instances, for patterns where transcription factor might bind the DNA. We then build edges from transcription factors to genes based on instances of that transcription factor being located next to the gene. If we have something about how the DNA is packaged, we know something about whether or not the DNA is out and open, flopping in the wind, so to speak, or whether or not it's tightly packaged and you can't get to it. We can use that to filter our initial gene regulatory network. And in fact, this is all the information we need to try to construct a network. So you can actually isolate the role of the genetic data by initializing some of these other matrices to the identity matrix. How do we add that into a framework such as Panda? We do that as follows. We basically add in the epigenetic information to prune our initial network, and we follow the same message passing procedure. And I'll show just one result from this so that you can get a sense of how well this works. So in this case, we applied this framework to 6 different types of cells, cells from lung cancer, stem cells, cervical cancer, liver cancer, blood cells, and blood cancer. And without getting into all the nuance, you can immediately see that the accuracy of these networks, which is the far right-hand column in all these graphs, is greatly improved by, number one, incorporating epigenetic information, which is the difference between the gray and black and the colored bars, and by adding this message passing procedure where we look for consistent structures in the graph, which is the difference between the pale and the dark bar. And I'll skip this one other conclusion just in the interest of time. I want to make sure that people don't feel too terribly rushed before lunch. So just kind of to summarize, I hope that there's 3 key take-home points that I've really been able to convey today. One is that gene regulatory networks provide a framework for modeling and analyzing biological processes, how genes talk to each other and how information can cascade through a molecular network. Secondly, I hope I've made the point that it's important to effectively integrate multi-omics data, to integrate this large quantity of biological data in order to actually develop a holistic model of biological systems. This data is complex. It's like the blind man and the elephant. No one data type is sufficient for understanding this underlying process, but if you combine it together, you can get a really good sense of what's going on. And finally, analyzing these networks can lead to novel insights in how the system functions. And I hope I illustrated that with our analysis of the different tissues, that analyzing these networks really led us to understand how tissue-specific processes can manifest. And I know I left people off this slide, but I think it's important to put up an acknowledgement slide of the various people who contributed to this work and that are in my group and have helped me with multiple fruitful discussions. So thank you very much, and I welcome any questions.
More awkward Zoom clapping. Thank you so much. That was great. So I think Thomas wants to kick off the question period. And meanwhile, folks, of course, as usual, Q&A is open and we'd love to have your questions. Thomas?
Great. Yeah, can you hear me?
I can.
Great. Thanks so much for the talk, Kimberly. I just had a sort of very broad question, which is, what are the implications for this work for, say, targeting treatment at individuals with different diseases, right? Like, can we solve the Sarah and Jane problem using the kind of things you talked about?
Yeah, that is actually one of the primary goals of my research, is to try to figure out, are there differences in networks that can lead us to either hypothesize new treatments or to figure out who's going to be responsive to a given treatment. So in one of the analyses that I didn't have time to go into today, we actually applied this framework into 2 groups of patients who had ovarian cancer, one of which we knew was responsive to treatment and one which we knew wasn't. And we could actually identify differences in those networks that might lead us to say, well, if we knew your network a priori, we could say that you're going to be responsive to the treatment and you're not. And the goal of that is not just to predict who's going to be responsive, but to say, if you have a molecular network that's not responsive to treatment, is it because we're targeting the wrong part of the network? Are we targeting not a network hub? Or are we targeting a hub that causes some sort of deleterious cascading effect? And can we identify different types of targets in the network? So definitely, yes.
Great.
Yeah, thanks. I think Debbie also had a question.
Can I ask something too?
Of course, Debbie.
I can be. In that curve you showed about the tissue specificity and of the percentiles of the genes, could you maybe talk a bit about how other genes like GWAS, disease-associated genes, or like housekeeping essential genes, where they might fall on that curve?
Yeah, we actually did that analysis. I don't think I saved it. Let me check really quickly. This is why I like keeping slideshows open. Did I put it at the end? I did. I have a slide to answer your question. This is the only extra slide I had. This is a slightly complex analysis, but we actually looked at this exact question, where we looked at genetic variants, GWAS variants, so genetic SNPs that are known to be implicated in disease. And we looked to see whether or not those SNPs are known to affect the expression level of genes, and where those GWAS genes, those QTL-related genes, are located in the network. And what we found was this, and the important thing is to really highlight, let me go to my laser pointer, this row right here, which are GWAS QTL genes in the tissue, and this row right here, which are GWAS QTL genes in the tissue in terms of their degree and their betweenness. And what you can see is those are also outliers, right? That you actually also have this phenomenon of low degree and high betweenness. And it's a really curious thing because they're behaving a lot like these tissue-specific genes, but these GWAS implicated genes are actually depleted for tissue specificity if you look at that direct overlap. So what we're finding is that genes that are important for disease behave a lot like tissue-specific genes without actually being tissue-specific in their expression levels.
And do you think that's got to do with, I guess, the mortality rating or morbidity rating of the gene, you know, like how essential that gene is in this functioning of a cell?
I mean, it may be. If we take it back to the network problem, I think it's because these GWAS implicated genes are actually accessible in the regulatory network framework, right? We don't make the argument that non-tissue specific genes never have any shortest paths through them. They don't all have betweenness of 0. Some do and some don't. So I think what's going on here is these disease-related genes are actually part of the critical network structure in the same way that tissue-specific genes are, and are just critical in a different way, in a way we don't know how to capture with the expression data. So yeah, I think there at some level, essentiality is too strong, but I do think they're important in the network structure in a different way that we don't completely understand yet.
That gets a little close to something that I was curious about. So you're using a network framework and you end up showing that there are some really interesting distinctions to be made using degree and betweenness centrality. And I wonder, you know, those are also sort of 2 of the major network statistics that you start with when you start a network analysis. So I wonder if you tried other network statistics and didn't find meaningful differences, or if you had a kind of principled reason for thinking that these would be the ones that would pick something out for you.
Yeah, well, when we very first did the analysis, we actually focused on 4 centrality measures. We did degree, betweenness, eigenvector centrality, and closeness centrality. And what we found is that every single centrality measure, except for betweenness, basically looked the same as degree, right? They all gave the same basic result, and that these other genes tended to have, tissue-specific genes had low centrality and non-tissue-specific genes had high centrality. And betweenness was really the only one that stood out as kind of different. I do think that there was some merit. I believe that there were some subtle things with closeness centrality that wasn't exactly matching degree. But in general, most of the centrality measures kind of collapsed in on each other and gave us the same story with the exception of betweenness.
Great. Here's a question from Alice in the audience. Of all the ways that one can blindly approach the elephant, why are gene regulatory networks the most useful approach as opposed to some of the others that appeared in the comic on your slide?
First off, I'm very grateful that you said it was the most useful approach, but I'd be naive to say that the other approaches aren't useful themselves. So I think that there's actually multiple useful approaches for approaching the blind man, the elephant problem. I think gene regulatory networks give a very specific insight that other approaches can't give that can be very useful in kind of the question we had earlier about, say, targeting genes for therapy. And the reason gene regulatory networks are distinctive and in some sense more useful than other approaches is they have what's called a mechanistic hypothesis underneath them, right? We actually are hypothesizing that this gene is connected to this gene, is connected to this gene, that there's a cascading effect that we want to model. And so what we can do is if we want to think about therapies and drugs, we probably want to target genes and sections of the network that change only the section of the network that needs to be changed, but not sections of the network that say are healthy and that we want to keep functioning. And gene regulatory networks give us that ability in a way other networks don't. Most other approaches for modeling networks and biological systems tends to do undirected networks. The protein-protein interaction network is generally undirected. Gene co-expression network is generally undirected. And those are the two other main fields of networks. So we don't know how the information is really cascading through the system nearly as neatly. And then the other thing about those other networks is they're often much more correlative. Our network looks very specifically at causality. And of course, it's only an approximation, but having that causal implication lets us make really targeted hypotheses that we can actually follow up and validate in the lab.
Cool. Another question was, is there a framework like this for prokaryotic systems, say to look at antimicrobial resistance?
Ooh. That is a really, really good question. You know, in some sense, I think this same framework could be applied to these systems. Unfortunately, I'm not a biologist, and I hope there's not too many on the call. I can't remember, one of my colleagues looking at tuberculosis, which I think is prokaryotic, I forget. But I think that we could definitely apply this to other smaller systems and different organisms as long as the data can be collected and gain insights into those systems. I think the thing to keep in mind there, and this is true of any sort of biological problem, is that every system has its own set of features and implications about how gene regulation occurs. So for example, this last thing I talked about epigenetics and how chromatin is structured is really important in eukaryotic systems and is very important in humans. You know, you could imagine applying the same framework to something like E. coli, but they don't have that same DNA structure, in which case you would need to emphasize different types of data in the model differently.
Great. Maybe there's a lot of great questions here, and we'll be sure to send you them, but maybe a last one for now. First, Max thanks you for the incredibly interesting talk, and then asks, if you have an isolated node, I imagine that would be the equivalent of a gene not expressing, or the proteins needed to activate it are not present, and it also has no output. Could it be the case that you can somehow introduce a protein into somebody's system in order to activate that isolated gene, where it would begin to produce proteins and in some cases become part of the network and permanently alter the network?
Yeah, definitely. And there are biological technologies that can do exactly that. You know, creating, I believe they're called guide RNAs, where you basically look at the DNA sequence next to a gene and say, what can I construct that will then target this gene and essentially cause it to get turned on? I think this is actually a case though where networks can shine and provide insights, because what happens is the minute you turn on one node, a lot of times there's what I would call features of that node that may be shared with other nodes in the system. And it's often hard to really just target one node. You're often targeting the node and then you have what's called off-target effects where other things get kind of hit as well. And so I think networks allow you not only to understand what might be that critical node that I need to turn on to activate a particular process, but But if I know something about the other nodes in the systems and the shared features, am I going to inadvertently hit these other nodes? And then what's going to be the impact on the network? And we can kind of guide our therapy development that way. I think you're on, yeah.
Thank you again. That was great. And like I said, we'll be getting more of the questions to you later. All right. So if we transition the screen share. All right. I want to thank everyone. This has been a really great morning session. I've been super pleased with how this has come together. And we'll get a slight early start on lunch relative to the schedule. We'll come back at 1 o'clock with a discussion session. And so what you're seeing now on this share is just a link that you can use to a forum, as I mentioned before, where you could, anyone who's listening on the live stream, on the webinar, or the panelists, you can use this link to just tell us about some papers or projects that are happening lately in graphs and networks broadly construed that you think would be of interest to other folks in this community. And we'll share those. But we'll start back up at 1 o'clock with a discussion that starts with some of the speakers and panelists who've already kind of been prompted to think about this question. So let me thank everybody again for a great morning session and hope to see you back at 1 o'clock.
Hello. So thank you very much for checking out this talk. I'm sorry I can't be with you in person, but you can't be with me in person either. In fact, I am participating in this workshop even more virtually than you are, since I'm separated from you by both time and space. This is joint work, as you can see, with several excellent young scientists, namely Katerina DeBacco, Dan Larimore, and Eleanor Power, all of whom were postdocs at the Santa Fe Institute, and who've now gone on to great faculty jobs at Max Planck, University of Colorado Boulder, and the London School of Economics, respectively. So there's a lot of awareness in network theory that traditional network theory often treats networks from whatever field literally as graphs, where between each pair of nodes, either there is a link or there isn't. That's one bit of information about that pair of nodes. And of course, this is a very thin picture of the world. In reality, nodes have locations and content and demographics. Links have lengths and capacities and so on. And so in particular, one thing we can do is embrace the fact that many networks have multiple different kinds of links. So we have different social relationships, marriages, financial relationships, alliances of various kinds. Transportation networks have rail, air, roads, and so on. And as we'll talk about at the end, if different genomes or amino acid sequences are similar, we could still ask which location in the DNA or amino acid sequence makes them similar. So hopefully this gives us a richer picture of networks. Some people call these multi-layer or multiplex networks, and you can think of them as graphs with multiple types of edges, but on the same set of vertices. So the hypothesis behind our work is that every layer of these networks is explained by some kind of common underlying community structure. However, the layers might be very different from each other, and we are not going to limit ourselves to situations where the layers are correlated. It might not be the case that if you have a link of type 1 between you, that makes it more likely to also have a link of type 2. We'll talk about that more in a moment. Rather than asking whether they're literally correlated, we're going to ask more generally whether knowing one layer helps us predict another layer by learning about that underlying community structure. So here's an example of what I mean. This is a classic assortative or homophilic network where we have two communities and we have more links within the communities than between them. Now imagine another layer of the network built on exactly the same communities, but now which is disassortative or heterophilic, with more links between the communities than between them. If we were to naively aggregate both types of links, into a single type and just view this as a graph, we would get something completely messy and uninformative. On the other hand, even though these two types of links are very different and in fact are anti-correlated with each other, knowing about either one will help us predict the other one. So that's the kind of structure that we wanted to model. So, you're probably familiar with the adjacency matrix, where A sub ij is 1 if I and j have a link between them, and 0 if they don't. In a multi-layer network, we're going to have something with 3 indices. It's really a tensor with a row, a column, and a layer alpha, where aij super alpha will be the number of links from I to j in layer alpha, or if you wish, of type alpha. And we can imagine networks with multiple links of a given type between a given pair. If you like, you can think of this as the total weight of all of the links of type alpha from I to j. Now, we're going to use a particular type of model, which is fairly standard in some branches of machine learning. Specifically, we're going to assume that each of these aij alphas is actually Poisson, where it's drawn, where the means of those Poissons are some other tensor mij alpha. And then we're going to look for a certain type of decomposition of M. So let me try to write this out or explain it. It's a little bit different from the standard tensor decompositions that you may have seen. So we're going to have capital K different groups, and then for each vertex I, it is going to participate in group little k, where little k ranges from 1 to big K, by some amount u sub ik. So that's how strongly vertex I participates in group K for the purpose of making outgoing links. Then a vertex J will participate in each group L with some amount v sub jl for the purpose of forming incoming links. Finally, we have some additional parameters which can vary from layer to layer. WKL alpha, this is the density of edges of type alpha from group K to group L. So, just to kind of emphasize what we're doing here, we're assuming that each layer alpha is governed by the same underlying community memberships. The U's and the V's do not depend on alpha, but these matrices W can vary arbitrarily from one layer alpha to another. In particular, it could be that for one alpha, WKL is larger on the diagonal, indicating that that layer is homophilic or assortative. For another alpha, it could be stronger off the diagonal, indicating that that layer is heterophilic or disassortative. Also, the W's do not have to be symmetric, so we're interested explicitly in directed edges, which is why the U's and the V's are not necessarily the same. The way that a vertex participates in the communities might be different for how it forms outgoing links and how it forms incoming links. So this is a type of block model, if you're familiar with the stochastic block model. However, it is a mixed membership model in which the blocks or communities can overlap. To put that differently, the U's and V's allow a vertex I or J to participate simultaneously in different communities to different extents. It is also, this model allows inhomogeneous degree distributions. These U's and V's are not normalized, so if a vertex I has large U's in general, it will tend to have a large out degree. If it has large V's, it will tend to have a large in degree. I already mentioned that we can have different roles for incoming and outgoing links. I think that's a nice thing to think about sometimes in disease networks, for instance, especially sexually transmitted diseases, but also for social networks of other kinds. And finally, as I already said, it allows for arbitrary structure in the various layers. One could be assortative, disassortative. We could have core periphery structure, where one community has many links within it, and then the periphery for that layer only connects to that core, and so on. Now, because I love mathematics, I can't resist telling you something about these tensor factorizations. So let me remind you that a rank 1 matrix is a matrix where the entries are a product of something that depends only on the row with something that depends only on the column. So it's an outer product of two vectors. Aij is U sub I times V sub j. And a rank K matrix is one that can be written with as a sum of K rank 1 matrices. I guess that's rank K or less. And if I give you a matrix and you want to find its rank, we know how to do this using linear algebra. We just look for the number of non-zero eigenvalues, or more generally, the number of non-zero singular values. Moreover, if I have a matrix of perhaps full rank, but I want to find a rank K approximation to it, I can find the closest one where, for instance, closest means minimizing the L2 distance, the sum of the squares of the differences, using the singular value decomposition, where I just keep the top K singular values. So for matrices, we can compute the rank and we can find low rank approximations. On the other hand, for tensors, we don't have any analogy to eigenvalues and eigenvectors. We don't have the same linear algebra toolkit. We can again define a rank 1 tensor as one which is a product of things that depend on the separate indices. Aijk is ui times vj times wk. We can say that a rank K or less tensor is one that can be written as the sum of K of those, but even computing the rank of a tensor turns out to be NP hard. We do not have a polynomial time algorithm for doing it. Moreover, if I want to find a low rank approximation to a tensor, I want to find the rank K tensor which is closest to some observed tensor. Even for minimizing the L2 distance, the best we can do is some kind of iterative algorithm, and this shows up in the work, for instance, of Tammy Kolda. And so even finding good approximations to tensors seems to be hard. Some kind of iterative algorithm which can indeed get stuck at various local optima. So the situation for tensors is quite fascinating, and I mentioned here also that there are particular tensors, like a tensor associated with matrix multiplication, where we do not know the rank of this tensor, and we would love to, because this would tell us something about optimal matrix multiplication algorithms. So tensor rank has a lot of wonderful open questions. Now, what are we going to do? We are actually not going to try to minimize the L2 distance. Instead, we are going to try to maximize the likelihood of this Poisson model that I described before. And this involves something, a classic family of algorithms called expectation maximization, or EM algorithms. If you've been wanting to learn about them, this is a fairly simple example. So these algorithms involve making a guess, which I will call rho ijkl alpha. This is our current estimate of the probability that a given edge, wait for it, from I to j of type alpha in layer alpha is due to I participating in group K and j participating in group L. It's our estimate of the probability that that is why that edge is there. Now, we have to update these estimates, but also, in an alternating or simultaneous way, update our estimates of all the parameters of the model. And doing this, it only takes a few lines to work these out. Please don't be intimidated by these. We have updates for the U's, the V's, the W's, those matrices that tell us how different layers, the densities of edges of different kinds depend on the group memberships, and finally of these probabilities rho. Now, again, these formulas are not that hard to derive, and they're not that hard to code up, and I don't want you to freak out about the number of symbols. Let me point out, for instance, on the upper left, our update equation for U sub ik. Look at the numerator for a moment. It basically says that if for lots of vertices j and lots of layers alpha, if there are many edges, aij alpha from I to j of that type, and if we currently believe that edges of that type are often there because I participates in group K and j participates in some group L, this boosts our estimate of uik, the probability or the extent to which vertex I participates in group K. Okay, so the numerators are fairly intuitive that way, and the denominators are essentially just normalization factors. So these are iterative equations. So what we do is we repeatedly take our current estimate of these things, put them on the right-hand side, and use this to derive on the left-hand side new values for these parameters. So hopefully we reach a fixed point fairly quickly, and you can show that this fixed point is always a local maximum of the likelihood. Indeed, there are typically many local maxima with different likelihoods. So we do this many times from multiple initial conditions, initial guesses of these parameters. Now, I want to point out that even if you are convinced by the fixed point that this algorithm finds, this gives a point estimate of these parameters with no sense of how certain or uncertain this point estimate is. So there are also Bayesian versions of this, like work done by David Bly and collaborators, analogous to their work, where we would attempt to derive some kind of approximate posterior distribution for these parameters rather than just a point estimate. We will assume, whether or not we believe this in our hearts, that the posterior is tightly peaked enough so that the point estimate is itself a fairly good picture of what's going on. Now, what are we going to do with all this? How are we going to tell whether this model makes any sense? Well, we're going to do something standard in statistics and machine learning, namely cross-validation. We are going to hide some of the data, in this case, some of the links from the model. So for instance, if I hide 20% of the links of various kinds, use the other 80% as training data to estimate these parameters, how well can I then fill in those hidden links? And we will measure our accuracy for this link prediction task using a standard measure, which regrettably is called the AUC, which stands for area under the curve. As you know, if you've been hanging out in this field, there are a lot of silly three-letter acronyms like this. So anyway, so what we're going to do then is measure how much telling you about some or most of the links tells you about the other links, including whether telling you about links in one layer helps you predict links in another layer. So, the idea of cross-validation, as you may already know, is that it's often tempting to fit very fancy models with lots of parameters and lots of communities, but a fancier model will often overfit the data, picking up on kind of random noise in the training data, and thus actually doing worse at filling in missing data. So we can also use this type of cross-validation to do things like select the number of communities and how elaborate the model should be. Now, I also want to point out something that for me was a helpful paradigm shift. We don't believe this model is true. This model is not actually how the data is made. So given that the model is not true, it might be useful, but as the old saying goes. But the best model depends on what kind of data is hidden and what we're trying to predict. So for instance, if I hide a random 20% sprinkled throughout all of the network and all of the layers, filling that in is simply a different task than, for instance, if I hide 20% of one of the layers, or if I hide many of the links of 20% of the links. These are different tasks, and the best model for doing well at them might have different parameters. So the best model is application dependent, and it should be. That is a feature, not a bug. So anyway, I wanted to point that out. Okay, now what are we going to do? Well, what we really want to study here is not how well this model works, because that's a question about the model or about our algorithm for fitting the model, which is different from studying the data itself. I can't help but editorialize here. There is a kind of narrow transactional interdisciplinary work where you have data, I have algorithm, we write paper together. Well, that's fine, but when you actually read these papers, I at least often feel that I haven't actually learned very much about the underlying scientific problem. or about the field that the data came from. Instead, mainly what I learned is a fact about the algorithm and a fact about the model. Now, I study algorithms and models, so for me, those are worthwhile facts, but it's different from claiming that you've actually learned something about the underlying system or the underlying scientific problem. So, well, end of sermon, until the next one. So we want to know whether knowing one layer helps predict another layer, another type of link, another type of relationship. And again, as I said, these different layers are not necessarily correlated. Hopefully learning one helps us predict the other by learning something about the underlying community structure, if this model is a good model of the data at all. So again, learning about the links on the left, which are assortative, will help us predict the links on the right, which are disassortative, by helping us learn which community the nodes belong to. Now, let's turn to our actual data. So one of our authors on this paper is Eleanor Power, who's a wonderful anthropologist and who, before her postdoc in Santa Fe, lived in villages in South India for 2 years. And of course, she lived there. She embraced these people's experience. She interviewed them about all sorts of things. And it's worth noting that the network data we're looking at is a very thin, very low bandwidth shadow of all of this lived experience she had during her field work there. But in any case, these networks have 400 nodes and 7,000 edges of various types. And one of the villages consists of 2 separate hamlets or sub-villages that affects its community structure. And she formed these networks by asking them about 12 different relationships. Who would you talk to if you were looking for a job? Who would you ask to babysit your kids? Who would you ask for a small cash loan? And who would you ask for advice about important life questions? So these are some of the relationships that she looked at. Oh, it's raining. Good. So now, of course, there's a lot of social structure here, including the different networks, the different nodes' religions and castes, as well as geographically where they live in the neighborhood, and that shows up in various ways in this community structure. So I also, one more editorial. You know, the great thing about working with Ellie Power was not really the mechanics of the algorithm. It was finding out from her as an anthropologist what were her scientific questions, and how could models like this, how could this type of exercise in statistical inference and machine learning really address the deeper anthropological questions she had. And so we settled on this question of which social relationships are central in the sense that they help predict other social relationships. What are the most important ones? And if you were a social scientist with limited time and resources, which ones would you ask about in order to learn about the society as a whole? So here's what we did with this link prediction problem. L here, that number which is 1, 2, 3, or 12, this is the number of different layers, the number of different types of links that we told the algorithm about, and we then tried to predict various other relationships. And on the y-axis is the AUC, the accuracy of our link prediction. And as you can see, it's fairly intuitive here that this network does have a lot of community structure, and that as we increase the number of layers I tell you about, from 1, 2, 3, up to 12, you do a better job of predicting, say, 20% of hidden links in a given layer. But we then asked, well, when we look at informative small sets of layers, if I'm only going to tell you about 1 or 2 or 3, which layers show up a lot in small sets that help us predict others? And what we found, for instance, that this layer, who do you discuss important issues with? Who do you ask for advice about big life questions? This showed up in many informative small sets of layers. It seems to be quite powerful at predicting other kinds of links, as opposed to, say, looking for work or babysitting. Perhaps those are relationships which are more specific and less predictive of other kinds of relationships. We also did some clustering by asking which layers are kind of similar in these matrices describing how they interact with the various communities. This was not terribly informative, but there were some interesting things where, for instance, who you talk with is often related to who you might borrow small amounts from. Who you ask for work is often fairly close to who you would ask for a larger loan, and so on. So that's kind of interesting. We used principal component analysis for that. So that was fun. Now, we looked at another data set. So Dan Larimore has worked a lot with Caroline Baki at Harvard, who's a fantastic epidemiologist, and they had a data set on malaria genetics. So malaria is a very nasty little beast. A little bit like HIV is constantly changing its outer protein coat. Malaria is constantly changing the proteins that it shows on the outside of the parasite, so that it will be harder for your immune system to identify it and latch onto it and clear it from your system. So they found that particular genes often have many, many variants deliberately on the parasite's part. And then they formed a multi-layer network, or Dan formed this multi-layer network with 9 layers based on which locus, which area of the amino acid sequence was responsible for the similarity between a given pair of variants. So we tried our algorithm on this, and it did very badly. In fact, it did negatively in a sense. If you look at this now, you'll see that the likelihood of link prediction, that our accuracy for link prediction, was fairly high when I only showed you one layer, namely the layer you're trying to predict, except for the 20% that we held out. When we add more layers, our accuracy actually goes down. Well, what's going on? Well, our model is getting confused here because the different layers do not have a consistent community structure. And because it looks for consistent community structure across layers, showing it more layers makes it less accurate. So we included this in our paper. And the referees were not very happy. They were like, why are you telling us this wretched failure of your model? We were saying, but this is interesting. Maybe this shows that the parasite has evolved to not have consistent clustering across these different loci of the amino acid sequence, precisely to somehow make it harder for your immune system to respond. So the joy of negative results, but of course it would be highly unethical to only present results consistent with our model and our algorithm, and to throw away or hide under the rug the data sets where it performed less well. I'm sure that neither you nor your PhD advisor has ever done any such thing. All right, so just to conclude, we have a model, a type of tensor factorization for multi-layer networks that assumes that the layers all rely on some underlying community structure, even if the layers are uncorrelated or even anti-correlated with each other. So they may be very different from each other while at the same time relying on this same latent community structure. Now, this is just one model, and this model leaves out a lot of things. In particular, it leaves out various local rules like triadic closure, triangle formation. You know, if A is B's parent and B is C's parent, then in particular, A is C's grandparent. And that's a type of relationship which a model could know about. It could either learn it from the data or be told it in advance, such as if you have an edge of this of type 1 here and an edge of type 1 there, it makes it more likely to have an edge of type 2 from here to there. So this is an interesting direction to go, and this can be incorporated into our likelihood function, but we have not done that yet. So finally, there's the reference if you want to look it up. Of course, it's also on the preprint archive. And here are our email addresses. We would love to answer any of your questions. And thank you very much for checking out this talk. Have a wonderful day.
Thanks, Bhushan. Okay, everyone, welcome back from lunch. Time for our discussion session, which I'm pretty excited about. So if you saw the screen share over lunch, it had a URL in it, which I will now put in the chat for everyone who's on this call. It is tinyurl.com GN papers. And that's just a form that will ask you kind of tell us about some new papers and projects that you're excited about in graphs and networks broadly construed. And so you can use the form. You can use the Q&A if you're on the webinar. The form is accessible if you're following on the live stream as well. So again, yeah, tinyurl.com/GN papers. And I thought I'd just get us started with some of the folks who are here as panelists, and we'll go around and ask you to tell us what's a project, who's working on it, and why is it exciting. So Tina, how would it be if we start with you? And maybe you can introduce yourself.
I am muted. Okay, I'm no longer muted. Thanks, Moon. I am Tina Elias-Wright. I'm a professor at Northeastern University in computer science and in the Network Science Institute. I'm pleased to be here. I forgot about that tiny URL. I was just feverishly typing stuff in, but I guess I'll just copy the two papers, the links to the two papers in this chat for everyone. And I apologize to the folks who are looking on YouTube. Are coming to us from that. So both of these papers are trying to address the issue that a lot of the work that is out there is on simple graphs. And we are trying to model complicated phenomena, and perhaps we should move away from simple graphs. And what does that mean? So examples include being able to model higher orders in networks, multi-layer networks, simplicial complexes, hypergraphs, so on and so forth. And one of them is by my excellent student, Leo Torres, and Ann Belvins, who's another excellent student at University of Pennsylvania, and Danny Bassett. That's the first link. And the second one is by a consortium of folks in Europe. And that paper is a hefty paper of close to 200 pages, going through different ways of representing phenomena. And one of the reasons I feel like people have shied away, for example, from hypergraphs is because it's not clear what spectra of the hypergraph is. And at least from my background, you know, my day job is graph mining, all right, building models that find patterns in networks and graphs and do predictions and descriptions of what's happening. We rely a lot on the spectrum. And I can say more, but I'll stop here.
Moon,
you're on mute. Okay.
You want to say just a little bit more before we move on to the next person?
Yeah.
I'm going to try to screen share the two papers that you sent.
Oh, excellent. Thank you very much. Yeah, so depending on how, so for example, our paper, the first one talks about how depending on which representation you pick, if you are computing the clustering coefficient, then you'll get very different results for the clustering coefficient. And this is an exciting area. So above and beyond these two papers, for example, Austin Benson, who's at Cornell, has some really nice papers recently in higher order representations of networks. Ingo Schultes has another one. And one of the things is that when you go into the more complex representation of graphs, then that comes with computational costs. And folks like me, we worry about those computational costs because we need them to not only work, but to be scalable. And that also is an issue. But really thinking about what are the assumptions that you are making when you pick a representation, right? And usually, at least, there are some folks who are not as honest about those assumptions. And then when the rubber hits the road, things go haywire, technical terms.
Great. Okay, thanks for getting us started. Red, I think you also had some ideas prepared.
Yes, am I unmuted just to check?
Yes.
Very good. Okay. Yeah. I will share one paper that so it's, in effect, one thing I'm really interested in is the interaction of networks, network formation, processes on social networks, and issues of inequality. So one paper that I'll chat, I mean, keeping the, I guess, the Cornell theme going, one paper that I'll chat is a paper by a sociologist at Cornell, Phyllis Garrett, and Paul DiMaggio, who's at Princeton University. So they're sociologists. And this paper is looking at the effect of network externalities and how that might lead to sort of intergroup inequality. So effectively what this is saying is that if you have things like, taking the AP is something that you want people to be doing potentially, but if a bunch of your friends are taking the AP, then it's easier for you to take it because you can study together, share resources, things like that. And so what they're looking at is effectively how, if you have inequality in your network, right? Let's say that you have sort of a minority majority partition or some other form of inequality, and you have this sort of positive externality that can actually kind of lead to a situation where the inequality gets exasperated because of the networks. And what they're looking at here was really more of like an agent-based modeling style approach. But I do think that there's some interesting, more graph theoretic questions that we could ask on these types of problems. And another paper that I will share, but it might take me a little bit, is also by not mathematicians or computer scientists. So Matt Jackson has a paper on networks and employment, effectively looking at how, so the paper is called Effects of Social Networks on Employment. So this is looking at how you have information about, say, a job that might spread on a network. So let's say that I randomly get information about a job. If I already have a job, then I would pass it on to my neighbors. If I don't have a job, then I might pursue the job myself, right? So you could imagine sort of information kind of being dropped on the network in this way, and then either kind of is utilized by the agent or gets passed on to their neighbors. And so it looks at that sort of process and how that also could lead to sort of inequality. So I think this interface of inequality and networks is something that's been well studied by sociologists and economists, both from a more theoretical and especially from a very empirical perspective. There's like many, many papers I could cite here, but not as much from the math and computer science community. So I think this could be something we could make contributions towards.
Cool. And actually, there's a project of yours that I would love it if you'd say a few words about, because we were talking about it the other day as a potential paper for here, which is about fair division and kind of incorporating a graph and network perspective to fair division problems.
Yeah, exactly. So that's an example. It's tackling at a different problem, but I think it just, again, highlights the need for a more networks approach to the types of questions that we've been asking, which is that when we think about fair division, we have definitions of fairness that we use, like envy-freeness is one that's very popular. It says that once something has been allocated, maybe you don't want anyone to be envious or too envious of anyone else's allocation. And it makes sense as a definition of fairness, but oftentimes these things are applied in these very massive populations where it doesn't make sense to say, don't be envious of literally anyone else in this population, right? So the example I give is that, Oprah earns a lot more money than I do. It doesn't really keep me up at night. But if my office mate was earning a lot more than I do, then maybe that would sort of bother me a little bit more, right? So what that basically says is that these definitions of fairness that we're using, we try to apply them in this very general context, in this very broad population context, but actually we know that the network structure actually significantly impacts how you might perceive the fairness of something. So the fair division paper that I think Moon just chatted is looking at one of our work on fair division via social comparison, so taking into account what would a fairness definition look like when you're taking networks into account, and how does the math change? Also, there ends up being a lot of really interesting graph theory.
Great. Jen, do you want to introduce yourself and say a little bit that you're excited about?
Sure. Hi, I'm Jen Cleland. I'm a professor at the University of Colorado Boulder. I got into this via one of Moon's workshops a few years ago, so I've been involved in some of the math and redistricting applications of these problems. And specifically, I've been working with my colleague Beth Malmskog at Colorado College, and we've both had some students working on problems about trying to analyze redistricting in Colorado. And the basic idea here, that picture that Moon showed at the beginning of the day of Missouri divided into different levels. One way of thinking about redistricting, how do you draw congressional districts or state legislative districts or any of that, is as a graph partition problem. You chunk your geography into units, whether that's census blocks or voting precincts or whatever units you want to build districts out of. And then the problem is, how do you partition the graph into districts subject to whatever are the legal constraints in play? Contiguity is a big one, equal population is a big one. Various states have notions of compactness, preservations of community boundaries, all kinds of things. So the graph has a lot of data associated to it. Like every node can have information about population, about racial makeup, about election results, about whatever you want to know about these geographic units. And that goes into your partitioning problem. So in the legal setting, what's become a really effective way to make the legal case that a particular map has been gerrymandered is to compare it to a large random sample of possible districting plans and to argue that a particular plan is an extreme outlier with regard to some outcomes. And a really big, interesting mathematical problem here is, how do you construct that random sample? What is it, and depending on how you construct it, can you say anything about the probability distribution that you're sampling from on the space of all possibilities? Moon's group has all kinds of really interesting papers about this, and a really important point is that the space of all possibilities is, larger than the number of atoms in the known universe, kind of big in most cases. So the sampling question is really hard. And I can't really claim to be on the forefront of that, but with Beth, we're trying to apply some of the methods that Moon's group and others have developed to redistricting in Colorado. The hardest part here can be data collection and data cleaning and trying to get this graph with all its associated data into reasonably good shape. My colleague Beth had a student who did a really good job of that for Colorado with data from our 2018 election. And so we've been working on analyzing that. We hope to have a preprint ready by the end of the summer. A couple of interesting mathematical things that we've been looking at here is there a way to tweak this sampling algorithm that's been gaining some traction in such a way as to take into account a desire to say reduce the number of counties that are split in districts? And we've been applying an idea that Daryl DeFord, Moon's postdoc, developed. And there's some really interesting aspects coming out, just by sampling and saying, what happens if we run the algorithm with this attempt to constrain it? What happens if we run it without that attempt to constrain it? Not only how does that affect the number of county splits, but how does it affect the partisan seat share? How does it affect the number of competitive districts? And so there's all kinds of interesting things going on that. And the other interesting thing is that Beth has brought in a colleague of hers named Flavia, and I forget her last name, but she's a statistician, and trying to actually do a more rigorous statistical estimate than what's been done before of of how large a sample do you need. So we've been using Markov chain Monte Carlo methods to sample, and actually trying to get some idea of how long do you need to run these chains before you get anything like a representative sample. one of the advantages of the algorithm that Moon's group developed is that just heuristically, it appears to have a much shorter mixing time than some of the methods that had been used earlier, but we're trying to get a little bit of a more quantitative handle on that. So that's what's going on now.
Awesome, thanks, Jen. And I'll post a link to some of this world of Markov chain sampling for redistricting. You can, I will, so that folks know where to go looking for that if they want.
You probably have a better idea than I do of how to cherry pick the best ones, so I'll let you do it.
Okay, great. So let's, Steve and Anna and Kimberly and John want to give you a chance. So let's maybe go in that order. So Steve, I think you had a few you wanted to talk about.
All right, thanks, Moon. Yeah, I posted links to 2 papers on the chat. So one is a paper that I'm involved in and one is not. Let me talk about the one that I'm not involved in first. So that's a paper about the same general topic I discussed this morning about mutant contagion, but it was pointed out to me on Twitter by Sam Scarpino that when he saw our paper, he said, this reminds me of this really cool paper from 2015 by Allison Hill and Gabe Leventhal, Martin Novak, Sebastian Bonhoeffer. So they studied the case where after you become infected, you can go back to being susceptible again after a while. You could recover. And so that's the kind of model that people call SIS. And they're really kind of, I honestly haven't thought about them much, but I think the intuitive picture you should have is like, imagine one infected person in a big network who then starts spreading the disease. People get infected, but then they come back to being susceptible at some probabilistic rate. And so you get this kind of bubbling thing that never stops, where some people are infected, some are susceptible. They're going back and forth between the 2 states. And you let this thing run for a long time till it's sort of in some statistical equilibrium, a kind of quasi-steady state. And then at that point, they subject the system to a mutant that enters somewhere. And they imagine that this mutant form of contagion is more spready, more transmissible. And the surprising result that they find is that, so they're interested in what network structure has to do with what happens in the long run. And the thing that seems surprising to them, and to, at first when you read the paper, it's surprising to the reader, is that the aspects of network structure that make the thing spread very well in the first place, infection spread very well in the first place, like the presence of hubs, let's say very highly connected nodes. What makes the disease spread very well at first makes it hard for the invading new mutant to displace it. And it's in other words, like there's only room for one of us in this town. There's only, once the resident strain of the mutant takes over, it's very hard for it to be displaced for the same reason that it succeeded in the first place. It kind of can keep getting reinfected by its satellite nodes and so on. So anyway, it's hard to summarize a paper in 2 minutes, but you should take a look at it because it shows, the bottom line is that network structure can play a pretty important role in the effect of mutants in contagion in a way that didn't necessarily come out in the talk I gave this morning. I think it's a little stronger in their paper. And also it underscores that the different dynamics can make a difference too. The SIS type of model of an epidemic versus the simple SI model where there's like permanent infection. So I do commend that paper. It is from 2015, but I had never seen it before, and I think it's interesting.
Great.
There was
I don't know if I should talk about the second paper. Maybe for an interest of time, I won't do that. Other people could go.
Okay.
I yield my time.
Anna, you want to go next?
Yes, sure. Hi, everyone. I'm Anna. I'm a PhD student at Columbia, and I work in computer science, more specifically in graph theory. And I'm interested in also the way I can understand inequality in networks, and specifically how different algorithms are perpetuating certain inequalities that come from biased networks. So there's 2 papers that really inspired my work, and I want to share them with you. This is the first one. I'm adding it to the chat, and a second one I'm adding now. And in the first one, there's this paper called Homophily and the Glass Ceiling Effect in Social Networks that's basically generalizing the preferential attachment model with two communities and homophily. So it's adding these extra factor of having, of the fact that people do tend to cluster more with people who are similar to them. And they're doing this analysis to understand exactly how does the degree distribution change. So they have this way of formalizing a notion of inequality in this network. They call it the glass ceiling effect, where you're looking at, if I'm in this network formation model that is scale-free, I have a lot of people who have very small degree, right? And very few who are very popular. But if I have two communities and I'm looking at people's probabilities to get to a high degree as the network grows, you see that one of the communities, if you have a minority community, is always going to be disadvantaged. So in a sense, the fraction of people who can attain a very high degree always goes to zero. And it's not a difficult model, it's just a really interesting effect when you're generalizing to multiple communities. So that really inspired me to think more about, okay, we're looking at social networks and we're looking at some notions of inequality. What exactly what kind of elements are important to understand that? And one of them is this community affiliation of people, and the fact that different communities do behave slightly differently or have different access in your network to increase their degree or to get different opportunities. And the second paper is building up on this paper by looking at what are people's incentives in such models? Is this model even realistic if you take into account people's, like what do people want to get out of this network? So if you think of people wanting to maximize their number of connections, then this kind of networks with preferential attachment, with homophily, is what gets you, is an equilibrium solution. This kind of model gets you to satisfy these people's incentive to grow their connections. So that's another reason for which, I mean, we know all models are not realistic, but it's useful, right? And that's been really helpful for me to think about different notions of inequality in such networks. So I chatted the two papers, and I think that's all I have for them, if anyone wants to go next.
Okay, great. Kimberly?
Yeah, I think I'm up next. I posted two papers in the chat. I'll also very briefly share my screen so I can have them on the screen as I talk about them. So these papers are kind of follow-up to one of the questions that was asked in the Q&A that we didn't get a chance to address live, and I thought it was a really excellent question. It was kind of getting at this notion that ultimately what we'd like to do is we'd like to get to that analogy of Susan and Jane. If one person is sick and doesn't respond to treatment, how do we actually capture their regulatory network? And a lot of what I talked about was how to build a more general regulatory network. So this paper right here, which was published last year in iScience, really a method for how do we reconstruct an individual person or an individual sample specific network. And it really addresses that there's this fundamental problem in the network reconstruction problem in biology, and that a lot of times the data is very noisy, and a lot of times we're looking at these higher order patterns. We think about the notion of gene co-expression, and if you have gene co-expression, two genes may be linked because they're co-expressed, so they're co-regulated, you draw a link between them. But of course, in order to even estimate co-expression from a correlation, you need multiple samples. So if you have 100 people that come into the doctor's office, maybe you can build a network for all 100, but how do you do it for each individual person? So what this paper does here, I'll just put up the graphical abstract really quickly, is it basically says that if you have some sort of reconstruction algorithm that normally creates some sort of aggregate network that captures information across a bunch of people, you can actually interpolate individual person or individual sample specific networks that allows you to have an approximation of the gene regulatory interactions in that individual person. And at a high level, the way that works is you basically can construct a network using all samples and all samples minus one. And you know that the missing sample had some sort of contribution to the large aggregate network. And from that, you can mathematically derive what that individual person or individual samples network is. So this first paper really talked about the methodological development, and I think it's of interest, even just from a mathematical framework. The second paper is a case where we actually applied this method. And in particular, we applied this method to build 8,279 gene regulatory networks using that same tissue-specific data set I talked about before. And it really highlights the strength of the method, where now we're not analyzing one network, or even like we did before, 38 networks. We're analyzing more than 8,000 different networks and saying, what are these subtle differences between different people? In this case, we were looking at sexual dimorphism, or differences between men and women. And kind of the upshot of this paper is that we found differences in the networks that had a lot of interesting features that had to do with disease implications, difference between men and women as far as immune processes. And we know that women tend to have differential amounts of immune-related disorders. But that these differences weren't captured at the node level or at the gene level. So it really, again, highlighted the importance of taking a network approach, and also the importance, kind of getting back to that question that was asked in the Q&A that I thought was really excellent, is like, how do we actually take some of these big data integration methods that are already really challenging and very complex, and how do we kind of distill it back down to what we really want to answer, which is, how does an individual person's network respond to a therapy or a drug, or is manifested in disease? So I posted both of those in the chat and also through the tiny URL. And of course, happy to answer any questions. It's a little bit of a personal plug, but I think that this answers a really fundamental question for network medicine.
Oh, great. How about you, John? You want to introduce yourself?
Hi, I hope everyone can hear me all right. My name's John Urschel. I'm a PhD student at MIT Math. Let's see, so one paper that I'm sort of interested in, it's not so new or recent, and it's a little bit more on the pure end than some of the other things we've been talking about, but this is sort of, I would say, one of my favorite results in math, and it's due to Batson, Spielman, and Sristava. And it's something called twice Ramanujan sparsifiers. I'll share my screen. Can you see this, I assume? Okay, good. So the main thing that's going on here, which I think is just absolutely beautiful as someone who, I don't know, appreciates graph theory and networks, is suppose you have some graph, and let's take a look at its Laplacian matrix, which is a very sort of natural thing to look at if you're concerned about, let's say, partitioning a graph, if you're concerned about solving problems involving, let's say, like electrical networks. Suppose you care about things like finding sort of low energy representations of the graph, like the Laplacian is pretty important. And one of the most fascinating things to me is that in this work, what they managed to show is that no matter how complicated your graph is, no matter how many edges it has, there's an algorithm that they can use to produce a graph that's weighted with a linear number of edges that approximates your original matrix within some constant factor, where the constant depends on the constant in sort of the number of edges you have. But I thought this was just one paper that it's not so recent, but it's very striking and very beautiful from a sort of graph theory network perspective. So that's all I've got for you guys.
Very cool. Jill, I think you had something to share.
Yeah, I just wanted to mention a project I've been thinking about lately. I'm going to talk about my research later, but I figured that nobody was going to talk about applications of networks in hydrology, geology, ecology, and land management. There's, I think, a really interesting network theory problem that land managers have of, if you have a flow network for your land of how water goes from one point to neighboring points, how do you predict whether or not you're going to get a concentrated flow path that's a lot of water coming into one spot that destroys plants and makes it hard for your landscape to sustain life? And I'm going to put a paper in the chat which talks about not just applications in geology, but connectivity in general in network science, which I think there's a lot of work in neuroscience on connectivity and stuff like that. But I think that this is an area of network science that is kind of related to, I think, what Steve was talking about with the, you know, the structure of the network and how it impacts movement around the network. And yeah, I think more people should work on it. So that's all I wanted to say.
So while we're waiting for other papers to come in on the response form or for other panelists to have an idea, this could be a good time to go back to your second idea, Steve, that you wanted to mention.
Oh, all right, that's an unexpected pleasure. Thank you. Okay, yeah, so this is a paper with Alex Townsend at Cornell and Mike Stillman, who does computational algebraic geometry. Alex Townsend is in numerical analysis. And it's a question about a very thoroughly studied model of oscillators that get themselves in sync. People call it the Kuramoto model, after a Japanese statistical physicist, Yoshiki Kuramoto. You don't really need to know what it is if you haven't thought about it before, but it's sort of the simplest canonical model of how things get in sync. And the graph theoretic aspect of it is to ask, if you put an oscillator at each node, they're all identical, they all have the same frequency, they all connect to each other, that is, they connect to the ones that they're adjacent to with unit strength. So it's like as minimal a model as you can have. It's just oscillators on a network. The question is, under what conditions can you guarantee that the only attractor for this will be everyone in sync? Like, you know, the visual would be you have a bunch of fireflies in a tree in Southeast Asia. Under what conditions, as far as who's communicating with who, will this system end up with all the fireflies blinking in unison? And a really cool result was shown about in 2012 by a guy named Richard Taylor, who proved that in any network where each node is connected to more than 93% of the others in the network, under these conditions, it will always end up in sync. I mean, the result was known for the complete graph with 100%. You're connected to everybody, that will synchronize. So Richard Taylor was able to shave that dense graph result down to 93% was enough. And just in recent times using, so people have been talking about spectra of graphs. I'm talking to you, John, and others who have been talking about spectral graph theory. So some recent work in the past 2 years by 2 different groups has shown that the number needs only be 78% if every oscillator, and by the way, I'm not saying anything else about the structure of the network. We're just talking about the minimum degree, you know, that if everyone is connected to at least 78% of the others, it's guaranteed to globally synchronize. On the other hand, with some of my colleagues a long time ago, we showed that you could construct networks where everyone was connected to 68% that would not necessarily synchronize. They could have alternative attractors. They could show waves or something that we call twisted states, where not everyone is oscillating in phase. So I'll just leave you with this question. These numbers, 68 and 78, are not that far apart. And it suggests that there is some number, which my colleagues and I think is 75%, but we don't have a proof. We think that if you have any network where everyone's connected to 75% or more, with the Kuramoto model, with unit strength coupling, et cetera, that will always synchronize. We think that because we constructed an example that almost works. With 75% connectivity, its spectrum has all its eigenvalues in the left half plane, except for 4 exactly 0. It's like on the razor's edge of doing what we want, except for these 0 eigenvalues, and nonlinear effects make our example not work. So it comes close but misses. But we think there must be some way to tweak the problem to find some example that does work. Anyway, so there's a hunt for what is this magic number. So if you like graph theory, and especially spectral graph theory, the dynamics are kept to a minimum here. I think it could be a neat problem, but we need some new idea. So that's what's described in the link I posted.
Okay, yeah, that's great. Let me mention that sort of got me thinking about something I wanted to mention. It's not so much a project as like questions. that I think would be great if people wanted to think about. And then I'll turn it over to Sarah Cannon to make a couple comments. So, you know, earlier in Steve's talk, we heard a little bit about random graphs, heard about Erdos-Renyi random graphs. And I know that's something that a lot of people in this area think about is different randomization models or various kinds of null models that you could use for randomizing a structure that approximates some class of observed structures. And I just want to, you know, with the two hats that I sometimes wear, kind of paying attention to this conversation in group theory and also paying attention to this conversation in like modeling geospatial and political data. Thinking about kind of feedback back and forth. So there's this very classic theory of random graphs and graph theory initiated, folks can correct me, but I think the 40s and 50s maybe. And then of course the realization that these might not be always the right kinds of graph randomization models to reflect properties of certain kinds of networks that we care about. So in group theory, you can do something really similar. So you can build up a model of random groups by starting with generating letters and then creating relations between those letters at random, and that gives you a group, right? And if you do that in kind of the most, I think, one of the most natural and appealing ways, you end up with what's the standard model in random groups. But what does it tell you? It tells you that there's this perfect sharp phase transition that happens at a certain density, above which you have a trivial group, like your group just completely collapsed to 1 or 2 points, and below which you have a hyperbolic group, which is a very special kind of group. Okay, so if they're trivial on this side of the threshold and hyperbolic on the other side of the threshold, you could conclude from that hyperbolic groups are just a whole lot more common than you thought they were before. They're ubiquitous, as some people say. Or you could conclude that you've got the wrong randomization model for groups in the wild, right? And these are the kinds of questions that I find really interesting. There's some cool progress happening in group theory on other models. You know, for instance, some of my collaborators and I tried to think about, well, what if you really wanted to find a billion groups? What if you really wanted to find nilpotent groups? What are some other ways that you could sort of change your randomization model to find the sort of stuff that you want to explore? And then over on the geospatial side, you know, earlier this morning, I was showing you networks of census data. And I think a really great question that I would love folks' ideas about, those graphs, they're kind of mostly planar, not exactly, but mostly. They're mostly triangulated, not exactly, but mostly. They're kind of a pretty interesting class of graphs, and it would be fun to be able to think about how you can characterize these dual graphs that come from observed geography. And if you can come up with randomization models that capture a lot of their characteristic properties. I think there's just a lot of fun graphy questions to ask about these census dual graphs. For instance, here's one. Are you more likely to see a little grid, like a little kind of 3x3 sublattice that looks like a grid? Where are you more likely to see that? More in the countryside where the census tracts are just square plots? Or maybe in a city where the census blocks are like city blocks, right? And so that sort of asks a bigger question, which is, does the graph or the network itself retain information about the human geography? I think that's a really good and question in a productive direction, I hope to think about. Okay, Sarah, want to introduce yourself?
Yes, hi everyone, I'm Sarah Cannon. I'm an assistant professor at Claremont McKenna College in California. And I wanted to talk mainly about some open questions for which I don't have a lot of references because there aren't many. So this is related to what Jean was talking about earlier with redistricting. So this idea of how do you get a good random sample? So we have graphs appearing in this question actually at 2 levels. So if you want to generate a random districting plan for a state, first you have the dual graph of the state, but then you can also look at the graph of districting plans, a graph where each vertex is a districting plan, and they're connected by an edge when there's some way of modifying that plan to get to another one. So this is called the state space or the metagraph, and we want to know things about the properties of this metagraph. For example, if we're doing a random walk on this metagraph to try to get to a random districting plan, how long do we have to do that for? And that's known as the mixing time. And how long that mixing time is a huge open question. So there's lots of work that's been done heuristically to try to see, well, it seems like this is mixing. It seems like we're running these random graphs for long enough, but there are very few theoretical guarantees known. So this is sort of a big open question. There's lots of techniques used in Markov chain analysis, which is my area, but none of the techniques that already exist seem to really apply particularly well to this situation. So it's something that I'd really like to see more people working on and more people thinking about, because it's a hard question, but also a very important one. So it'd be great to be able to get some results, some rigorous results as to how long you have to do these random walks for until you're getting good random samples. And this applies beyond just redistricting as well to all sorts of other problems where you're using random walks or Markov chains to generate random samples. And I will quickly plug one work. So there is some work being done on when you can get good random samples without mixing. So there is some work done by Maria Chikina, Alan Fries, Jonathan Mattingly, and Wesley Pegden about when you don't have mixing, when you can actually still be able to say something conclusive about whether something's an outlier in the state space. And it involves arguing that something's an outlier in its local neighborhood of districting plans and saying that that's actually enough to conclude it's an outlier in some broader sense. So I linked the paper, which is quite technical. If you want a less technical overview of their reports, I'd actually recommend looking at the court filing. So if you look at the court filing that was made about this paper, this is Wes Pegden testified about this in a Pennsylvania court case. I find the court filing actually explained the ideas at a much more understandable level if you just want to kind of get a general sense of what's going on before diving into all the details of the paper. So I put that link there as well.
Let me just add to that, this is kind of for the application for the use case of redistricting, but the math has nothing to do with that. The math really asks, if you have a Markov chain and you don't know that it mixes, what can it tell you anyway? So, I mean, I think this is good for all of you know, to check out. It's a really beautiful theorem, and not just those who care about the redistricting case.
Oh yeah, absolutely.
It's the only example I know of an expert report with a theorem in the appendix. That's pretty cool. Great. Okay. Actually, just there's a question that just came in over the chat that I wanted to pose because it's very relevant to the present moment, which is, let's talk about COVID for a minute. There's so much modeling happening to do with coronavirus, all aspects to do with kind of how should we do surveillance testing and how might the infections spread and what are some predictive models, and so many modeling questions kind of flowing around to do with COVID. And so I'm interested to hear if the panelists have been tracking any that they want to tell folks about. But I want to plug, I don't know if anyone's here from the MIT IDSS group, but IDSS, which stands for something that someone will help me with, an Institute for Data Systems and Society, Data Science and Society, something like that. Got the right kinds of letters in there. At MIT, they're doing a really great collaborative effort to just talk modeling once or twice a week about COVID. And they have a Slack and also a weekly Zoom that's open to everyone in the community, not just MIT. So everyone who wants to join. So when I stop talking, I'll post information about that in the Slack so y'all can follow that. But meanwhile, panelists, anyone want to speak up about COVID modeling of any kind that they're following that they think is interesting? Oh, wow.
Okay. I feel like, yeah, go ahead, Tina.
There's so much work. I mean, between, just for example, in my institution, right, with Sam Scarpino, Alex Vespigiani, and their entire group, with Barabashi, Network Medicine, there's just so much work and it changes day by day. That it requires a more specific question in terms of where we are, what we think, so on and so forth.
Okay, I'll still mention a couple efforts that I think are really quite worthwhile. So there's a good SIR model that's happening around here, which is Rochelle Walensky and her collaborator's name I'm looking up right now, David Paltiel. And that's being used by a lot of groups in the Boston area to try to understand something about the dynamics of predicted dynamics of infection, including exogenous shocks for the campus reopening effort. So that's one that I'd point to. On Red's theme of plugging Cornell at every opportunity, Peter Fraser's group at Cornell is also doing some really high quality modeling, and I think that's another group to look out for that's doing interesting stuff. In that spirit, has anyone, A.B. Flaxman is a computational guy, but also now in a public health department at the University of Washington. So many of you probably remember the University of Washington was one of the really early predictive models to come out and got tons of attention, but they have continued modeling efforts that are really interesting and helpful. So I'll post links to some of these, and if anyone else has other just examples of like high quality work on COVID modeling, I think that would be a valuable thing to share.
I think read anything by Vespignani, basically. I mean, because he understands how complex it is, right? You have meta populations. It's not like you cannot just say, oh, I can do like a simple SIR model. The environment matters. I know Sam Scarpino has also talked about this. But in terms of the modeling of that, and then if people are interested in doing stuff, I know people have been getting like safe graph data to initiate mobility networks to see, okay, if I quarantine this part of the state, what happens, so on and so forth. So there's lots and lots of different things happening.
Anyone else?
Moon, I thought there was a very interesting comment in the chat from Momin Malik that, yeah, hey, about maybe it's gonna be too controversial, but it's about the way social scientists tend to look at network problems and the way natural or physical or biological scientists work at them. I don't know if people want to react to the comment, or Momin, you want to read it for us or say anything?
Yeah, this is a comment on Moon's bringing up what is the right random model for comparing against a baseline. And there's two articles that I like to use, and I do a lot of network science things and read against each other. One from 2009 is from Steve Wargati and colleagues. He's a major figure in social network analysis from the sociology and organizational side. And they write that for social scientists, saying that something doesn't look like a random graph, and so it's a significant finding, is like looking at a pile of materials in a skyscraper and saying, look, they're different. And so they react with bemusement. And I think there's that same reaction, especially among social scientists who are more sophisticated, of saying, okay, a configuration model reproduces the degree distribution, but what about triadic structure? That, you know, this reproduces one particular feature, but that's not what I care about in a network. I care about a specific network with the specific people in it and their specific relationships. Cesar Hidalgo, I think, has a paper that I read as kind of a useful rejoinder to that, which is that sometimes structural things can be explained by, if you just had a random network, the same thing would happen. And then if that's the case, then you need to say, well, that's not actually a finding. And these are some of the useful things, but there definitely needs to be appropriate random models for the given situation. And so I like that comment from Moon a lot, that, hey, if we want to find a random, you know, model to generate abelian groups, you know, we should not be looking at the most natural or obvious random model. If we want to be studying social networks, Erdos-Renyi random graphs are not the best thing for comparing to social networks because they don't look a lot like it. Neither are stochastic block models, which statisticians love because they're so analytically tractable. Even graphons. So I'm really excited about, for those maybe who don't know it, graphons are to networks what density distributions are to histograms. It's the kind of theoretical infinite object that you can make recourse to for inferences, except for graphs. So you could have like a core periphery graphon, you could have a community block structure graphon, but I still see it as something that's far in the future for having a kind of expressive language that's useful for real networks or real graphs. But that said, I think it's enormously useful to be able to say, hey, you know, the fact that there are sociologists with Erdos numbers of 2 is really not that surprising once the graph gets big enough, right? That's something that's very easily explainable by a single tie somewhere between Ove Frank or some sociologist and some mathematician. That'll give every sociologist an Erdos number of 3, 4, 5. So things like that aren't actually substantive findings, but they're just a consequence of certain structural features. That's it for me. I don't know if we want to talk about that more, but those are my observations.
No, I think that's great. Okay, so let's see. I think we have 0 minutes left before it's time for John's talk. So thanks everyone. This is sort of an experiment in whether it's possible to do something that feels like a real discussion in webinar format, and I think it is. So the link is up to the Google form that you can use to talk about work. We're gonna, as I say, distribute it later. So it's a great place for those of you who want to share work that you're doing or work that you're excited about. I'd encourage you to use that link for it. And now it's time to turn the floor over to John Urschel.
Thanks, Moon. Okay, let me just share my screen. Hold on. Is this working? Steve, I was reading your paper with Alex just now. It looks really interesting. So I have to finish later. Let's see. Share, and now hold on. Let me see how I make this into a, how does that look? Does this look reasonable? I can't tell if you can see the bottom or not, and I'm not sure how to make this full screen.
The next page, but it's fatal.
Yeah, I don't actually know how to make this full screen using.
I think it looks great.
It looks great. Oh wait, hold on. Is this? No, but this still doesn't. Let me just play with one little thing.
Try Control L, apparently.
What if I just do this manually?
Beautiful.
Okay, perfect. So what I want to talk about today is spring embeddings of planar graphs. And one thing that I was struck by when we started this sort of virtual conference is Moon showed us a picture, I believe, of Missouri. And this was a triangulation. It was planar. It was two connected, I believe, maybe not. But one sort of thing I want to look at is, given a graph that looks very similar to that, how do you embed this graph in the plane? Okay, so let me start off by telling you a really fascinating result in graph theory. It's something called Tutt spring embedding theorem. I think it's sort of a very beautiful result. It says, suppose you have a planar graph G, and let's just suppose it's 3 connected, which means you need to remove at least 3 vertices from the graph so that the graph becomes disconnected. One thing to know about 3 connected planar graphs is that the concept of a face of this graph actually becomes embedding independent, given that every single face is now an induced cycle, as long as n is at least 4. So what this theorem says is that if you take one of these faces, which you can replace by the term induced cycle, and embed it in R2 as a convex polygon, and then for every single other vertex, you just place it at the mass center of its neighbors, well, then what happens is that you get a planar embedding, and that this planar embedding is actually uniquely determined by the embedding of the outer face. So here's a visual example. So we have a 3 connected graph. Here we choose a face. The face we chose is this 4 cycle on the outside. We embed this in R2. Here we just embedded it as a square. We took every single other vertex and we just put the condition that all other vertices have to be at the mass center of their neighbor. So this gives you a unique solution for all the other vertices. And as you can see visually, this result is planar, and this will work every single time. Now, one thing that might not be immediately obvious that is actually quite nice about this theorem, due to Tutt, who I hope many of you guys know as sort of a very great mathematician, especially in graph theory. One thing to note is that if we call, let's say, gamma the vertices of our outer face, given some embedding of this outer face, Tutt's condition that interior vertices be at the mass center of their neighbors, this actually minimizes something. This minimizes the sum of squared edge lengths, assuming that you fix the embedding of the boundary. So for, like PDE type people, you can think of this almost as like a harmonic extension of sorts. Okay. But there's a natural question which is going to come up, but first let's introduce some notation. So this idea of minimizing sum of squared edge lengths, what's naturally sort of lurking in the background here is the concept of a graph Laplacian, which if you heard the paper I just talked about, you heard me give a brief little spiel about this. This is quite an important matrix that can be used in a lot of applications to tell you something about the graph you're working with. And I just define it via this bilinear form you see in front of you. So given some vector x, you can think of this inner product between x and L applied to x as just telling you the sum of squared edge lengths, where you measure the edge length as the distance between the value at vertex I and the value at vertex j squared. Okay, and in general, you can think of a graph Laplacian in more general terms if it's a symmetric diagonally dominant matrix, off diagonals, non-positive, and you'd like the all ones vector to lie in its null space. Okay, just some notation. For our purposes, let's think about this graph Laplacian in block notation. So we can think about our graph as boundary vertices, which are the vertices corresponding to some induced cycle in our graph, which perhaps actually has some significant importance. For instance, suppose you're given a graph that's, let's say, a triangulation of a finite element mesh, or maybe the graph that Moon showed at the start of our conference. Well, there's a lot of induced cycles, a lot of faces. One of them seems much more natural than all the others, because for instance, in Moon's example, it's a triangulation. All the induced cycles are of length 3, except for this very large outer face. So you should think of this gamma as some very large induced cycle that represents a boundary in some sense. We can write the Laplacian in block notation, where in the top left, this is the chunk corresponding to the interior vertices. The bottom right, this is the chunk corresponding to the boundary vertices. And we can think of this L0 and this L gamma as the Laplacians on the interior vertices and on the boundary vertices. The main question that we're going to sort of get to today and sort of only touch on briefly because of limited time is this theorem is really nice and it tells you something pretty cool. It's telling you how you can embed some sort of planar graph, some sort of triangulation into the plane so that you're somehow minimizing sum of squared edge lengths, so that somehow you're sort of putting your graph at equilibrium. You can think of this physically as taking the boundary vertices, sort of taking like a hammer and nailing them down, putting springs on all the other edges, and then just letting them reach equilibrium. But what this theorem doesn't tell you is where should you place that outer boundary. And so this is something I want to start to dig into a little bit. Using this block notation, one thing that might not be immediately obvious, but you will find, is that the harmonic extension for the interior is given by the above formula. And you can see that this has a unique solution, which actually minimizes the trace of, let's say, X transpose LX, where this X is a n/2 matrix representing the locations of our vertices in the plane. Okay. So just one example of sort of why spring embeddings really matter versus, say, something well-known like a spectral layout is that, if you want to embed a graph in 2 dimensions via something like diffusion mapping, where you take the graph Laplacian, you take the 2 minimal non-trivial eigenvectors, and you just use these 2 things to draw your graph, well, the sad thing is that even if your graph is planar, often the drawing you get from this technique is not. And so, for instance, on the left, what I have is I have some random points on a 3x1 rectangle, a triangulation of this. And on the right, I'm showing you the spectral layout that you get from using the minimal 2 non-trivial eigenvectors, which is a very natural technique that's, really got a lot of, a big body of literature, I'd say. Okay, so we can see why if we want to maintain planarity, somehow this isn't the best way to draw our graph. So sort of an argument for spring embeddings. But as I was saying before, there's not really much guidance on how we should embed the boundary. And so what I'd like to talk about today is sort of what the right choice for this is sort of conceptually, and give some theoretical guarantees as to why this works. So let me just throw out another natural choice and sort of talk about why some of these natural choices don't work. So one choice you might want to take is you say, okay, I understand that the minimal 2 non-trivial eigenvectors of the graph Laplacian produces a drawing which is non-planar. But maybe I just restrict this embedding to the boundary, hope it's planar, and then just do a harmonic extension for everything else. The problem is, in this case, the boundary is actually often not planar and often non-convex, extremely non-convex, for instance, as you can see in this example here, okay? Another choice is to say, well, what if I just take the Laplacian on the boundary and just take the 2 minimal non-trivial eigenvectors of that? Well, the issue is the boundary is just a cycle, and because we have a 3-connected planar graph, it's an induced cycle. So we actually know exactly what that Laplacian is. It's just the Laplacian of a cycle. And so the 2 minimal non-trivial eigenvectors, this is just going to result in an embedding of a regular n-gon, n-gamma, where n-gamma is the number of boundary vertices. And this doesn't really tell us anything about the interior, which is sort of, you know, this is less than desirable in some sense. So let's try to quantify a minimization problem and try to think about solving this thing. So let me represent this mathcal x, let this be the set of all convex planar embeddings of a cycle of some, you know, of some length that satisfies certain normalization conditions. Let's assume that the embedding of this in the plane satisfies the normalization that x gamma transpose x gamma equals the identity matrix, where x gamma is the n gamma by 2 coordinates of these points in the plane. And let's suppose that this is orthogonal to the all ones vector. The reason why we need these normalizations, well, the normalization against the all ones vector stops things from sort of condensing down to a point, and the normalization on x gamma transpose x gamma stops us from sort of restricting to a line. You can think of this similar to conditions for sort of embedding a graph using the minimal non-trivial eigenvectors of the Laplacian. You still have conditions like this, and they're sort of necessary in some sense. So the question is, how do we minimize, let's say, the sum of squared edge lengths such that we make sure that our graph doesn't condense down to a point via this sort of condition? Well, one thing to note is that given a choice of x gamma, the choice of the interior vertices is simply the harmonic extension. And if we just plug in this harmonic extension, we note that this objective function of minimizing the sum of squared edge lengths is actually equivalent to minimizing the trace of the following x gamma transpose times s gamma times x gamma, where s gamma is a Schur complement. So this is a Schur complement of our Laplacian matrix with respect to interior vertices. And so the main thing that this tells you is that if we want to minimize the sum of squared edge lengths subject to this constraint on our boundary, the best choice possible, if it's planar and if it's convex, is actually to just take the 2 minimal non-trivial eigenvectors of this Schur complement. The problem is we have no reason to think a priori that this embedding is going to be planar or that it's going to be convex, let's say. And so this is a major barrier to being able to approximately solve this optimization problem. So as a visual example, just to give you maybe some hope that maybe the Schur complement will give you something pretty and maybe this will sort of work. Here's a graph taken from the Sweet Sparse library, previously called the Florida Matrix Collection, I believe. This is a planar 3-connected graph. Here is a spectral layout, which again is quite beautiful, but is non-planar. And now let's look at the Schur complement based embedding. We see that it sort of really represents the dynamics of the graph. It's a planar embedding. And although the Schur complement embedding is not convex, we see that in this case, Tut spring embedding theorem actually still works. Although if your boundary is non-convex, it's not always guaranteed to work. So this sort of visual example already tells us, well, maybe we are on the right track in some sense. Maybe this is the right matrix to think about in terms of embedding 3 connected planar graphs using, let's say, a Tut spring embedding. Okay. And to start, I just want to note a couple key things about the Schur complement. First of all, this is a graph Laplacian. Second of all, you can think of this Schur complement as the sum of 2 graph Laplacians, namely the sum of the graph Laplacian on the boundary, plus another Laplacian, which is a weighted Laplacian, which in some sense represents the dynamics of the interior vertices. And the last thing I want you to note, which I sort of already mentioned, is you should think of this, this semi-norm induced by this Schur complement as sort of telling you the energy of the harmonic extension of some sort of function on the boundary. Okay. Just so that you sort of connect this to sort of concepts in PDE theory, because this is going to show up and be used in sort of showing that this Schur complement actually behaves relatively nicely. Okay. One thing that we were able to show in this work is that if you have a graph, a planar 3-connected graph, which has some certain amount of structure, let's say your planar 3-connected graph is a finite element mesh of some convex region or near convex region. Suppose it came from some application which really originated in the plane so that it does have some natural planar structure, then we can actually mathematically quantify the behavior of the Schur complement and show that the Schur complement is actually spectrally equivalent to the boundary Laplacian to the 1/2 power, showing that it represents the dynamics of the interior, but that it has enough structure that in some sense you can expect sort of low energy vectors with respect to the Schur complement to somehow have structure very similar to what you would expect to the sort of structured boundary Laplacian to the 1/2 power. And to give you some intuition as to why this type of spectral equivalence might be true, I want to just sort of briefly introduce a really, really useful result from PDE theory. So suppose you have some domain in RD, and let's look at H1 of omega, this Sobolev space of square integrable functions with a square integral gradient. So you have sort of a norm on the space, you can define a norm on the boundary, and sort of a famous sort of result from elliptic PDE theory, which is really important, which, okay, I don't expect you to sort of follow all the sort of finer details of this, but the main idea here is that there exist results in elliptic PDE theory which relate functions on the boundary of some elliptic domain and the energy of those to the harmonic extension. And so showing that this Schur complement that we care about, showing that this is spectrally equivalent to just the boundary Laplacian to the 1/2 power is actually closely related to proving a discrete version of this result from elliptic PDE theory, where of course we need to get rid of L2 terms and look at energy only terms. So for instance, suppose we can prove a discrete version of a trace theorem for these energy semi-norms, namely, for our Schur complement, suppose we can show that this is spectrally equivalent to, let's say, this Laplacian L tilde, which I define to be a discrete version of the boundary semi-norm from elliptic PDE theory. Then to show that this desired result, you just have to show that the boundary Laplacian to the 1/2 power is spectrally equivalent to this semi-norm I've described, which you can sort of do pretty easily just using some calculus and basic tricks. And so, in fact, the type of result you can get is you can say, suppose you have some graph G, you fix a boundary gamma, which we can suppose is very big, and suppose that all the other induced cycles of your graph are not too large. If it's a triangulation, then this would be 3. If this planar spring embedding satisfies certain niceness conditions, meaning, let's say the convex hull of the boundary vertices are not too thin, and all of the edge lengths of your embedding, say, are within a constant of each other, and your angles are not too thin, then you can actually show that you have spectral equivalence between the Schur complement and the boundary Laplacian to the 1/2 power. This is more or less telling you that if you have a graph which embeds well in the plane in a very natural way, then you'll have the spectral equivalence. Now, given this sort of theoretical result telling you that this boundary Laplacian to the 1/2 power is spectrally equivalent to the Schur complement, this inspires a very simple sort of rough algorithm to try to draw planar 3 connected graphs in the plane. One very simple thing you can do is you take the Schur complement, compute the 2 minimal eigenpairs. First of all, if this embedding is planar and convex, just by looking at the objective function, we're done. If it's not, you can use an initial guess, which is either taking this sort of Schur complement based embedding and making it convex, or just using a regular polygon, and you can just iteratively smooth this using the Schur complement. The key thing here is that the spectral equivalence, which I've just shown you, implies that you can always produce an initial guess that gives you a value of your objective function, which is within some constant factor of the optimum. Okay. Now, before I finish, I want to make a couple sort of obligatory messages about sort of dealing with a Schur complement. And okay, I'm sort of I'm a numerical sort of linear algebra person at heart, so you'll have to excuse me, but I want to sort of mention a couple technical details about how you should use things in practice. So in general, the Schur complement of anything is a dense matrix because it involves the inversion of a large matrix, especially in this application, because you're dealing with boundary vertices, which, okay, if n is the order of the graph, your boundary vertices is usually like n to the power 1/2. And so the interior vertices are really, it's about n vertices, more or less, minus some small amount. And so you would invert a very, very large matrix, which, okay, this isn't as bad as like using like the inverse operation on a matrix in MATLAB as opposed to backslash, but it's still pretty bad. And so what you should do instead is you can actually apply a Schur complement just by solving a linear system for y, and then simply using this solution y to compute S gamma of x. So this is the way you should do this rather than actually inverting a matrix. And therefore, applying the Schur complement is actually not nearly as expensive as you would think, because it's roughly like a O of n log n procedure if you have like an O of n log n solver. The same thing for the inverse of the Schur complement. It actually takes the same amount of sort of computational time, which sort of tells you that if you really want to sort of take an initial guess and try to improve what you get, you should really use the inverse rather than, let's say, some sort of shifted power method, because the inverse is sort of just as cheap as the original matrix. So that's something worth noting. Here's another visual example. So here's a triangulation on circle, triangulation on a 3x1 rectangle, spectral layouts. Both of these things are non-planar, non-convex. The spectral layout is harder to see, but the boundary, like it mushrooms, it sort of goes out and then back in. And the Schur complement layout, which is planar in both cases and sort of represents the dynamics that's going on in these graphs. I want to say thank you to the MGGG redistricting lab and Moon for having me. Here's the associated preprint, which you can find on arXiv. If you look at the paper itself, you'll find that there's a lot of technical details, which I really could not get into because it's only a 25-minute talk, especially around being able to prove spectral equivalence and proving discrete versions of these trace theorems, which is actually a non-trivial endeavor. So thank you for listening to my talk, and let me know if you have any questions.
Thanks, John. Really cool stuff. Okay, so maybe Jordan, do you want to get us started?
Yeah, I was curious, John, as I watched, what would happen if you tried to do this same kind of thing, but your graph wasn't actually planar? Is there some chance you would actually sort of get a good low crossing embedding, or would you just get trash and the thing would die?
My experience is you usually get trash unless it's very close to planar. Like, think about it. If you take something that's planar and let's say 3 connected and you just add 1 edge, you can imagine that the impact that just adding 1 edge or a constant number of edges has is that it really doesn't change too much globally. It might change some things locally in a place, but I would say it's robust to graphs which are very close to planar.
You know, when you say that, it reminds me a little bit of Steve Strogatz's stuff, that somehow if you take a graph that's very geometric, like embeddable in a plane, you don't have to throw in too many long edges before it, so to speak, sort of forgets that it was supposed to be embedded in a plane. If you throw in a very few, it sort of still remembers well enough to have an embedding where you don't have too many crossings. But I wonder if there's a similar thresholding with like how many long edges, so to speak, or just otherwise non-geometric edges you can put in before you just like break your ability to embed in this way.
Yeah, it's a interesting sort of just general broad question, because sort of this concept of planar graphs that really have some sort of geometry tied to them really allow you to do powerful things. And it's a really interesting question. How far do you have to veer from this structure before, you know, like these nice things that you usually can do just start breaking down? And that's a deep question, I feel.
So I feel like this is a little bit related to something that I've been thinking about lately, but have decided it's just really hard, which is, suppose you start with, you know, an embedding of points in the plane and knowledge of adjacency.
Yes.
And you know that the graph that describes is a planar graph abstractly.
Okay.
But when you draw them as straight line edges, you get crossings.
Okay.
Right, so in other words, you're handed a non-planar embedding of a graph you know to be planar.
Mm-hmm.
It sort of seems like, so what you're doing, which is sort of making these edges, minimizing these edge lengths, is somehow spiritually connected but different to the problem of like moving the vertices a little bit so that you can have a nice planar embedding. So perturbing locations by as little as possible so that you get a planar embedding. Does that make sense? Do you see what I'm saying?
Yeah, it does make sense. Although I have to say, one weird thing that I really came to realize is that, okay, suppose you just want to minimize, let's say, squared edge length, like sum of squared edge length, then oftentimes for things that like are very nice and well-structured planar graphs, the optimum looks very far from that. Not even close in many, many instances. And so it's really interesting to me, because the difference between sort of just taking that approach and taking a more structured approach, which says we are going to fix some sort of boundary to make sure that we at least have a planar structure. And now we try to do sort of like a harmonic extension. It's like a completely different world. And it's that's something that's a really, I'm not sure I fully understand it. I have to say, but it's a really interesting phenomena, I would say. That somehow this concept of really needing to sort of fix the overall structure first and then sort of dealing with things locally somehow is like important. Yeah.
Great. Any other questions from the panel? Questions from the audience? Questions for John about related stuff? All right. Well then, let's all thank John again. Thank you, John. And we will resume at 2:30 with our first collection of lightning talks. So, see you then. Okay, so the way we're gonna do the lightning talks is I've compiled slides from our lightning speakers into one slideshow. And I will be trying to share that. Oops. So what I would ask is for the speakers to let me know when you need your next slide. It's not a perfect system, but I think it's probably better than having lots of different screen shares. Okay, so again, the plan is we're gonna have 4 talks in this lightning talks block, and then a break, and then 4 talks in the second lightning talks block. And I believe that everyone who's giving one is already a panelist. So let me start the screen share. Okay, and then ask Jill if you're ready to start.
Yeah, I'm ready.
Oh, okay, hang on. Yeah, I was having this bug earlier with my screen share. Give me a moment. Great. Okay, and Jill, take it away.
Great. I'm going to be talking about data analysis in the space of phylogenetic trees. Thanks. And I'm going to start in the upper left-hand corner here. A phylogenetic tree is a weighted leaf-labeled tree that encodes pairwise dissimilarity relationships between a set of organisms or species. So between 2 leaves, which are kind of the only nodes in the tree that we really care about, the intrinsic path distance in the tree, the length of that path gives you the dissimilarity between those organisms. So traditionally, phylogenetic trees come from data that are formed via an evolutionary branching process. But it doesn't have to be actual evolution. Anything that is formed in this branching kind of way can often be encoded as a phylogenetic tree. So a phylogenetic tree, once you have it, can be represented as a point in phylogenetic tree space. So in 2001, Valera, Holmes, and Boatman wrote this big paper defining phylogenetic tree space, which is a big combinatorially complicated space that parametrizes the set of all dissimilarity relationships that are trees between a fixed set of leaves. So for every unweighted graph shape, you have a positive Euclidean cube. And within that cube, the vector of edge weights gives you a point that represents your tree. So as you move around in the space, you're continuously deforming one tree into another. And if you assemble all of these cubes together, identifying trees that are the same along the boundary, then you get, for 5-leaf trees, this space in the bottom left-hand corner, which is even worse than it looks. I've suppressed 5 dimensions, and these letters are identifications of the rays of the cone. So this looks terrible, but it has some really nice statistical properties. Specifically, between any 2 trees, there's a unique geodesic. So the length of that shortest path can be used to define a distance between different trees. And the midpoint of that path can be used as a kind of average of the two trees. So if you have a larger point cloud, you can define a Fauché mean, and this allows you to say things about sets of like possibly very different inferred phylogenetic relationships between the same set of species. So I work on geometric properties of this space. My paper about to come out shows the isometry group and the volumes of small neighborhoods. And this slide refers to some work that I did in 2019 with Megan Owen. We looked at dimensionality reduction techniques on sets of trees. There's maybe a very obvious dimensionality reduction technique, which is you have a set of n organisms, let's only care about some of them, and use the same dissimilarity distance on them. So there's I have a little cartoon here of the graph reduction technique to get from one to the other. And what we did is to construct a linear program and show some combinatorial results that allow us to take the pre-image of this dimensionality reduction map and construct the space of all trees with lots of leaves that contain a particular subset of tree-shaped information. So that's my time. And if you have more questions about it, hit me up.
Awesome. Thank you. That was amazingly 3 minutes on the dot. Okay, so folks, I just want to say, if you do have questions, it'd be great if you just use the Q&A or the chat and throw some questions in now, but we're going to go through all the talks and then take questions as a group. Okay, so next up is Ana Rios with a metabolic network of a circular economy for plastic disposals in Mexico. Ana, are you ready?
Yeah, I'm ready.
Great.
Okay, thank you. Okay, first of all, what's the main problem with plastic? Most of the plastic in economic is almost in the 80% of all the sectors in all the economy. But the main plastic in plastic waste is the packaging plastic. Okay, why? Because it represents almost 50% of all plastic. No. So what are some of the solutions that literature suggests? For example, one of these is circular economy as solution. Okay, some countries like China and some European countries have used some public politics applying this circular economy. And also some big corporation like Coca-Cola, mostly for the bottles, has already applied this way of thinking. What is circular economy in a big sense? Okay, so let's stop thinking about this linear economy or of use. Use and then disposal. Circular economy says that we have to close some loops. Also says that all the waste is also has value for reuses. So what is the proposal here? First of all, let's start with a system thinking. So the first thing that I do was in my research was like to think about a metabolic network that have the social system, the economic system, and of course the environmental the system. After analyzing this network, I realized I make a matter flux analysis applying an agent-based model with NetLogo. So the next, please. So, okay, here is the metabolic network. And I would like to share this small video. So can you click on the link?
Yeah, no, that won't work live, but people will be able to click on it later.
Okay. So what this what this show is how the model works in this metabolic network of matter flux analysis. And what we found is that circular economy, it is not necessary, it is not enough for plastic waste because it have a lot of limits, such as technological limits, and also about infrastructure limits, and especially in case of Mexico. So that's it. I think my time's over.
Perfect. Okay, thank you so much. Okay, next up is Ali Morgan. Ali, are you ready?
Yep.
All right, great.
Hi, my name's Allie. I'm a PhD candidate at CU Boulder, and the project I'm going to be talking about today is faculty hiring and the spread of scientific ideas. Next slide. Great. So the sort of motivation for this work is that one way in which ideas spread throughout academia, but probably other sort of employment situations too, is by hiring. You study a technique and then you continue that technique where you take a faculty job. And there's a great example of this with Feynman diagrams. They are these kind of diagrams showing what happens when subatomic particles interact. And a group of postdocs at Princeton developed this technique, and then those postdocs took jobs at different institutions. On the left here, I'm showing what these diagrams look like at Rochester, Chicago, and Oxford. So this really is a transmission of an idea by hiring, where there was sort of a new technological development, and it continued at these institutions by researchers carrying them. I want to combine with this idea the fact, or the finding, that there's this dramatic inequality in PhD production in faculty hiring. So about 20% of institutions populate about 80% of faculty jobs. There's a next slide here. Yeah. So the approach that we're going to use is we're going to simulate the spread of ideas in this network on the faculty hiring network by varying which university is generating an idea and the quality of that idea. So I'm using this SI model that's very familiar from Steve Strogatz's talk earlier, but in my model, I allow transmission across these edges just once, and there's no probability for a retransmission. Basically, an idea was carried from one institution to another, or it wasn't. Great, so the plot I'm going to show you has a lot of detail, so I like to kind of break it down. On the horizontal axis is the prestige of a university. So this is where in this network did an idea start from. And because it's a ranking, the most prestigious universities lie on the left of this plot with like rank 1. And on the horizontal axis, we're measuring how many universities adopt an idea at the end of a simulation of this epidemic on this network. So a single dot here represents the average of about 10,000 simulations where I've started an idea at a particular university with a particular quality. And in the colors, I'm going to vary, I'm going to show what happens if you vary the quality of these ideas. So in the purple line here, these are the lowest quality ideas. If you click one more, yeah. So you see for the lowest quality ideas, they spread throughout the network much farther if they're coming from the top 50 universities than if they're coming from the bottom universities. And this is the case for the same quality ideas. Yeah, sorry, I have a lot of transitions. In red are the best quality ideas. So these are the highest quality ideas. And you see that regardless of kind of where they start in this network, they can reach a lot of it. And then in the middle, we've got sort of these medium quality ideas, which we think the system is sort of structurally disallowing their spread. I think my time is up, but there's one more slide with just some takeaways that you can read.
Do you want to tell us in a sentence or two?
Sure. So we just used this simple epidemic spreading model to show that ideas in academia spread by hiring, and that the structure of this network can privilege elite institutions. If we think that science like incentivizes incremental low quality ideas, then this will result in a system where the prestigious researchers are really visible. Importantly, we're assuming that quality of an idea and where it starts in this network are independent. And it'd be kind of hard to test. It's actually really hard to establish the quality of an idea. So this would be a good thing to think about.
That sounds right.
Yeah.
Okay, Samin.
So hello everyone, my name is Samin Aref. I'm from Max Planck Institute for Demographic Research in Germany, and I'm going to talk to you about analyzing sign networks of political collaboration. So if we look at the fraction of bills that are passed into law in the US Congress, we see a general decline in the both chambers. So both in House of Representatives and the Senate, bill passage rate has declined. And our research question is why Congress is so ineffective at passing legislations. So next slide, please. So in order to answer this question, we use networks of positive and negative collaboration ties between legislators. So in these networks, node colors represent the party affiliation, red for Republican, blue for Democrat, and the colors on the edges represent the type of edge. Green edges represent a significant level of collaboration, and orange edges represent a significant lack of collaboration. So we can partition the nodes of these networks into two groups such that the number of negative edges within the groups and positive edges between the groups are minimized. Using these optimal partitions, we can get a sense of the structure of the network. So now if you focus on the colors on the nodes in this visualization, you would see that in more recent years, there are more nodes of the same color grouped together, and all nodes of the other color are in the other group. This means that Republicans are collaborating with Republicans, Democrats with the Democrats, and avoiding each other. And this is the increase in partisanship. If you focus on the colors on the edges, you would see that these two groups or coalitions, if you will, are becoming more cohesive. So there are more green edges within the groups in more recent years, and there are more orange edges between the two groups in recent years. This shows the increase in polarization. And these two changes that I briefly mentioned are two aspects of the increase in partisan polarization. Now that we get a sense of what's happening with the structure of the network over time, we can use a structural equation model to test the relationship between bill passage rate that has been declining over time and the partisanship of these coalitions. And using this model, we actually see that if it was not for the increase in partisanship of coalitions, the Congress would have been even less effective at passing legislations. So this seems a bit counterintuitive, but if you would like to know more, please feel free to check the open access article linked in the QR code. Also, our code and data are publicly available, and I'm happy to answer any questions you may have. Thank you very much. And thank you, Moon, for giving me the opportunity.
Great. All right, so I will briefly stop the share so that it's easier for me to see if questions have been coming in. So I see some raised hands. So maybe I'll ask if panelists want to get us started with questions while I'm trying to find the questions from the attendees. Does anyone? If not, I'm happy to ask lots. I found those to be really provocative talks in a great way. Really lots of great things to think about. So I'll just start with the one that's closest to my math home, my happy math place, which is Jill talking about this cube complex of phylogenetic trees. I'd never seen that before, but of course, Votman et al. Do cube complexes for working with right-angled Darton groups and outer automorphism groups of free groups. So it's back to group theory for me. But so there's, of course, it raises the obvious question. Do you know anything about the curvature of these complexes? Sorry, that's the obvious question if you're a group theorist.
Yeah, they're cat zero, which is what allows the geodesixia.
Cool.
That was the main finding of the 2001 paper.
Is that easy or hard?
Somewhere in the middle, I think. They're using the link of the cone point, and I think it takes a bit of work for them to show that it's a flag complex, but then once they do that, it's cat zero.
Okay, so a couple questions have started coming in. Kate's asking for Allison, and I guess you all can see, speakers, you can see the questions coming in on Q&A, so feel free to just field them. But I was wondering about this too. Allison, can you talk about what was your proxy for idea quality?
Yeah, so this is, in that SI model, there's this notion of transmissibility. So I'm using that transmissibility as a proxy for idea quality here.
And is that citation? Like, what's the transmission?
Hiring. So, yeah, so it's as if, you know, two individuals start out with the same transmissibility idea or quality of idea, and they move somewhere, and that's the vector of transmission. This network.
Also, if folks don't know it, Ali was making reference to this fantastic book by Dave Kaiser. I mean, I assume you were when you're talking about Feynman diagrams. So there's a really classic book in the science, technology, and society literature called Drawing Theories Apart, in which Dave Kaiser tracks Feynman diagrams all over the world and tries to understand the kind of tacit knowledge that comes with how people draw what they draw. Highly recommend.
Yeah, it's really cool.
Thomas, want to unmute yourself and ask your question? Oh, okay, apparently not. Okay, Samin, how do you define collaboration? So it's sort of a similar question to what we were asking Ali about how you sort of draw the edges. What is a collaboration? What is a non-collaboration for the purposes of your model?
Yeah, so they come from bill co-sponsorship data. So we know how many bills are jointly co-sponsored by every pair of legislators. So let's say that you're a legislator, I'm a legislator, and we have co-sponsored 100 bills together in a session of Senate. Now the question is whether this 100 is too many or too few, or just something that is expected by chance. So we compare this number against a null model, and we create one null model for every pair of legislators. And then too many collaborations would be something that is across all the topics, and we consider it as a significant sign of collaboration. And the opposite would be a significant sign of avoidance, if you will. So we have positive and negative edges.
Following up on that, I've seen other studies that do that as well, that look at co-sponsorship as an adjacency. Just qualitatively, how good of a job do you think that does of capturing collaboration in a more kind of vernacular sense?
So, well, I think if the number of co-sponsored bills are used, I don't think that would do a good job, because there would be many factors. There could be some people who are just into co-sponsoring regardless of the content, and some people, some legislators who are absent all the time. So we need to control for these factors, and using the null model I mentioned, it's called the stochastic degree sequence model. We account for all of these parameters, and then what remains would be the collaboration ties that is, I mean, rather consistent with what we know. So I don't know that much about politics in the US, but I know that, for example, Susan Collins is Republican, but she collaborates rather more than expected with Democrats. So that would be one edge, one positive edge that we would see, for example, between Republicans and Democrats in recent years.
But maybe not enough to keep her seat. We'll have to see how that goes. Okay, a couple more questions. So Ali, can you talk about the gender and sex attributes that relate to your study?
Yeah, so this paper actually didn't really investigate this, but two other papers from our group talk about how they find that women on average place lower in this network. So women are placing at lower ranked institutions. And so the effect that we're seeing is that lower ranked institutions can't propagate their ideas as far. And so if women are placing lower, that would sort of impact that, mediate that. So I can speak to that. Then there's lots of other cool papers in this space. So I'm happy to send you more.
Okay, maybe you could put some in the chat.
Yeah.
In the form that we talked about. Okay, so last call for questions for any of the speakers. Right, and I will, as soon as I figure out the easiest way to do it, I'll make sure that Anna's video link is posted so that everybody can play around with that in real time. Okay, so it's time for a break. We have a 20-minute break now, and we'll be back at 3:15 Eastern time with the second round of lightning talks. So thank you so much to the 4 lightning presenters. I thought that went really well, especially with me pressing the buttons, and yeah, could have been meltdown in 12 different ways. So thanks again, and everyone, see you back in 20 minutes. Okay, let's get restarted. Janaki, are you here?
Yeah.
Ready to go?
Yeah.
All right. Carrie?
Can we leave the first slide until I say?
Say it again?
Please leave the first slide on until I say go.
Sure.
Yeah, thanks. Okay. Hi, everyone. Let's go back to the... Yeah. Thanks. Hi, everyone. Let's get started. Brain is an immensely complex system. Much of its complexity arises due to the nonlinear interaction between its components, which are neurons, which are connected to each other through synapses. Neurons could either be excitatory or inhibitory depending on the type of synapse they form. If an excitatory neuron is active, it activates its neighbors, but if an inhibitory neuron fires, it suppresses the activity of its neighbors. Functioning of the healthy brain is crucially dependent on the intricate balance between the excitatory and the inhibitory interactions between the neurons, which is called excitation inhibition balance, or the EI balance. So the question is, what exactly is the role of modularity or network topology in maintaining this EI balance, in particular modularity? Next slide. On the left, you see is a schematic of the modular network, which has excitatory and inhibitory neurons shown in blue and red color. Dense connections within each modules and the sparse connectivity between the modules is shown in the adjacency matrix below. We can see that as you change R, one can go from a completely isolated modules at R equal to 0 to that of a homogeneous network at R equal to 1. So what we do is we take a large network of neurons, and by varying the modularity R and the fraction of inhibitory neurons, we try to see if the network produces sustained activity or if the activity just dies out. So in the top panel, you can see 2 individual neuronal time series which I have shown. We have the entire result is summarized in the surface plot, which you can see below. The x-axis is the fraction of inhibitory neurons, and the y-axis is the modularity R. Even for a homogeneous network at R equal to 1, for this you have to see the plane which is like projected. You can see that there is a narrow range of fraction of inhibitory neurons for which the system shows sustained activity even for a homogeneous network. This range gets broader and broader as we make the network modular or decrease R. You can see how this dark region broadens as you move along the y-axis while decreasing R. So the take-home message here is that modularity broadens the excitation inhibition balance, thereby maintaining the system robust. This, I think, could be one of the evolutionary advantages of modular topology, which is seen across all brain networks at various scales. Next slide, please. The next question we are interested in is, where exactly do this modularity come from? Neuronal networks in general are highly plastic. Not just the networks affect the dynamics, but the dynamics also shape the network itself. One such mechanism is spike timing dependent plasticity, a variant of Hebb's rule. The schematic in a simplified manner is shown on the left panel. It says that if the presynaptic neuron fires before the postsynaptic neuron, the connection between them strengthens, and if the postsynaptic neuron fires before the presynaptic, the connection between them weakens. So we start with a randomly connected homogeneous network, say the initial connection, And we see that spike timing dependent plasticity results in the emergence of modularity. You can see the final figure. So the take home message from here is the network along with the dynamics and learning results in modularity. Thank you.
Great, thanks. Okay, Pepe, ready?
Yeah. Hi, everyone. My name is Pepe, and I'm a PhD student at U Chicago. And the working title of my work is Cooperation in Small Worlds, Society, State, and the Structure of Social Networks. Next slide, please. So my motivation for this work is this ongoing puzzle in the development economics literature concerning generalized versus localized norms of cooperation. Namely, why do individuals in some societies cooperate with a broad scope of their co-citizens, while individuals in others seem to reserve cooperation to their kin and kith, that is family and friends. So my ongoing work aims to explain this by modeling a prisoner's dilemma link deletion game with N agents on a Watts-Strogatz small worlds graph. So a shout out to Professor Strogatz in the audience. So for those of you who don't know, this is a random small worlds graph. N agents are ordered on a ring lattice in a circle, and then each agent is connected to K immediate neighbors, K over 2 on each side. Then with probability P between 0 and 1, we rewire each link uniformly at random in the circle. So in my setup, P serves as a proxy for the scope of cooperation. Lower P means more local cooperation, and higher P means more generalized or global cooperation. Another advantage of this random graph is that I can model increasing and concave benefits of long distance cooperation measured by the distance between the nodes on the ring lattice. So the intuition behind this efficiency that I also model is you can think of more like long distance trade, or people get to specialize, larger markets, and etc. The two different strategies in the prisoner's dilemma game that I'm focusing on, one is some cooperative links are contractually non-defectable. This is what I call the state-enforced cooperation. And the second one is one in which defector nodes are punished by neighbors of victims who were harmed by the defector nodes by cutting the ties if they exist. And this is what I call the society-enforced cooperation. Next slide, please. In my simulations, I start with an initial random graph defined by a specific P and K, and then random nodes are drawn to decide whether or not to defect on a cooperative link, given the game strategies in which they play. And then this is repeated until no nodes defect, resulting in G infinity, that is some sort of like stable network. And then I see which links are left, and I calculate social welfare. Results suggest that in the state-enforced prisoner's dilemma game, higher P yields higher social welfare, and thus this long distance efficiency is captured. However, in the socially enforced PD game, higher P weakens the ability of communal enforcement to deter defections, and cooperative networks collapse. That is, usually G infinity is empty and we have zero welfare. And I think this sort of implies the stability efficiency tension that is common in many game zone networks. And I think it introduces a new perspective to a standing puzzle in the development economics literature. Right now, I'm trying to refine the model and also working with Facebook's Global Social Connectedness Index to empirically test some of the implications of my simulations. So that's it for me. Stay tuned for more, and thank you.
Cool, thanks. Okay, Juniper, ready to
Hi,
go?
hi everybody. Yeah, so I'm going to be presenting a preprint that we put up a couple weeks ago, which you can see on the archive. I have the link there, on distributed consent and its impact on privacy and observability in social networks. You can see my awesome list of co-authors there. Next slide. So really the punchline of this project is if data is distributed across individuals, so should our consent. And personal data is actually not discrete on online social networks. A single user who consents to allow access to their own profile or their own personal data can in turn expose a lot of personal data about their network neighbors. And for us, this really calls into question the boundary of personal data online. And in the traditional individual consent model that we're currently, which general world is currently using, they really only ask one individual for access, which doesn't really work here if we kind of have responsibility for many people's data. And in this work, we introduced a model that we're calling distributed consent, where individuals and groups can coordinate by giving consent that's conditional on that of their network connections. I'm sure you have heard about this from your friends or have experienced this, but your friends can install a lot of stupid apps on their computers, and this can put you at risk if you're one of their network connections. But I think what's a little bit more interesting is that even your friends' friends can install a bunch of stupid apps on their computer, and that can also put you at risk. So that's something that we wanted to consider in our model. And so this is a very simple model. So what we did is suggest a new security setting for online social platforms where you can only share information with network neighbors who share the same kind of like taste for privacy that you have. And so people who probably don't share a bunch of data with third-party apps. Next slide. Okay. So we made a really simple model using an anonymized Facebook 100 data set that looks at the impacts of distributed consent on the observability of social networks. And what we found was that at a relatively low adoption rate, it would allow for macroscopic subsets of the online network to preserve their connectivity, but more importantly, also increase their privacy. So this is a pretty easy to implement setting that could, possibly go on something like Facebook, which would allow the users to remain on the platform, but sort of give them an increased security. And one of the things that I find is like incredibly interesting, I come from a social science background, is really introducing the concept of distributed consent to users. And I think that this could be a potential avenue for them to understand that giving access to your own data means that you're actually giving access to your network neighbors' data. And in future work, I'd really like to see how this sort of affects online user behavior if this kind of thing was implemented. In my own mind, I can imagine like if this happened yet tomorrow or something, and I went on and changed my Facebook setting, I think like the first thing I would do would be to call my mom and be like, hey mom, if you want to see pictures of my cats anymore, you should change your setting too so you can see all of my stuff. So it would be really interesting to take this further and see if this kind of like taste for privacy could be a contagion on the network. So that's very simple. I didn't go into detail of the model. I just want to say and end with just say that this is not a silver bullet by any means. This is a really simple model. Data privacy is an incredibly complex issue that has many different levels. And I think that it needs to be considered very thoughtfully and ethically. And I'm really looking forward to continuing this work and collaborating with this really cool multidisciplinary group. So if you have any questions, check out our paper. And thank you so much for having us here. Thank you, Moon, so much.
Thank me. Okay, Rebecca, ready to go?
Yes.
All right.
Thank you. Well, thank you very much. It's a pleasure to share with you a promising application area for cascade processes that model the change of a network structure in response to a perturbation, for instance, a shock. And we focus specifically on international crop trade networks. Next slide, please. Thank you. So what we observe is a network that tells for 3 specific crops. Those are the main traded crops worldwide. And we observe a network from one country, where countries are nodes, and one country imports a certain amount of quantity of this crop to another country. And we observe how much that is within a certain year. And this allows us to construct those networks that you see on the left. So specifically for corn, rice, and wheat in 2013. And now the main question that we ask is, what is if something goes wrong? So for instance, what is if you have harvest losses due to a weather anomaly? Or what happens if you have a pandemic and farmers are not able to distribute all their foods or all their harvest? So the question is now, what happens now to the rest of the network? Next slide, please. Thank you. So ideally, we would have a network formation model. So that would tell us, okay, country A to D produce this much. And from this, we can predict now the specific network. And this would also tell us how, if you change the production, for instance, of a country, how this affects the whole network. The problem is that this is a far too hard problem. So it depends on all kinds of unobserved quantities like subsidies, trade agreements, taxes. Even the harvest times can have a huge impact on the prices that farmers face, the speculation, the product quality, etc., etc. So this is a too hard problem. And the main idea is not to simplify the problem, but only modeling the change of network structure. So we don't want to get a model for the full network, but just how it changes in response to a shock. And we propose a cascade process that's a bit different from the epidemic models that were discussed so far. So this would be a threshold model, specifically with a specific load redistribution mechanism. And this tells us, and this gives a country the opportunity to respond to a shock by reducing its own exports. So let's say a country produces less, then it reduces its exports and keeps the proportions of trades fixed as it had this in the beginning. Then the importing countries now have less than they want. So in reaction, they reduce their own exports to keep more in their country and so on. And we can now follow this cascade process till the end. And this allows us now to construct networks of the form that you see here down on the left. Those are networks of higher order import dependence or trade dependence. So if you start in a country, this means that you shock this country and then you follow a cascade process till the end. And in the end, some of the countries in the network have less than they wanted. So when the cascade process stops. And when you follow a link here in this network, it tells us which countries face which kind of loss. And what is interesting now about those networks, we also have links here, even though we didn't observe any of those in the original trade network that we had before. So this informs us about indirect dependencies that can be surprising for countries. And we believe it's important to also consider those kind of indirect dependencies in policy decisions. So thank you very much for having.
Excellent, thank you to our lightning. So I'll put this slide back up so you can remember who gave what talk and ask people if they have questions. I'll stop my share so I can see. Panelists, do you want to get us started with some questions? Okay.
I have a question. Hi, Rebecca. Thank you for your talk. That was super interesting to think about the network changes and how can we relate that to crop. I'm wondering, like, what are some of the modeling or the models that you're looking at when you're looking at networks? Are you looking at data sets or like the graph themselves that come from data sets? Or are you looking at, or how do you think about their to model this and to like generalize it perhaps, or yeah?
Yes, so it depends a bit. So for this specific project, we take those networks from publicly available data. So we construct them based on trade data that is made available by the Food and Agriculture Organization of the United Nations, so the FAO. That's FAOs.org, if that's pronounced correctly. So we really observe those networks. Of course, we have uncertainties about this, right? And it also makes sense, for instance, to do robustness checks of the model. So what happens, if we change some of the links a bit, because this data also has its pitfalls, of course, but mainly we assume that we know the network in this case. I've also done work on this specific type of process where we just where we basically assume that we have configuration models and random graphs, and we solve then the analytics, and then we basically can describe the evolution of those cascade processes and do some analytics based on those random graphs. But yeah, that's not for, not when you have the network given. And then this wouldn't say a lot anymore about international food trade necessarily.
Awesome, thank you.
Thank you. Thanks. It's a great question.
I had a question about the connection topology in the brain, that talk. So you seem to have this sliding scale of modularity from low to high. And I was wondering, like, what parameters are being held constant while you're sliding that? Is the sort of density or the number of edges in the network, is that staying constant?
You should also definitely get your kid on the call.
Yes, my collaborator is also on the call.
So Janaki, can you take that question?
Is she still there?
Yeah, can you see my slide?
Yeah, do you want me to go back to your slides?
Yeah. So if I understand correctly, you want to know what are the constants which I have used in my simulations?
Yeah, I'm kind of interested in like your three, so you've got those three heat maps, A, B, and C at the bottom. So some things are changing, but what is sort of being held constant between these networks?
So you have this average degree as a constant. And then you vary this modularity parameter. So this is very similar to a watchdog edge network, just that you have within module and outside module connections. If you're talking about this adjacency matrix, so all we have constant in our entire simulation is the average degree.
And is it known if sort of increasing the average degree has an effect on the sort of activation time?
Okay, so we found that too high average degree can actually lead to loss of activity. So we have fixed that average degree, which works for us. So you can't have too high a degree and you can't have too low a degree. So you have that critical degree where the activity can spread in the network.
Thanks.
Okay, I think we have maybe time for one more question. So let's maybe I'll pose these two questions that came in over Q&A generally. Okay, Kate asks, Rebecca, where did you get the crop trade data for the model? Do you have intuitions about how the change of network structure relates to the network formation? And then Nick asks, maybe a general question, for models that attempt to represent structures like Rebecca's international trade model, it seems that one bit of tension is that these models may be used for policy formation, but a lot of social advocacy pushes for these systems to be entirely reconsidered, not just tweaked. How much do folks think these types of counterfactual structures, think about these types of counterfactual structures when doing this type of research? Specifically in international food trade, would counterfactually modeling countries with more diversified crop production, as advocated by food justice organizations, be part of this type of research?
Can I answer maybe? Okay, perfect. So those are two really great questions. I'm happy to post the link to the data set I will post it in the chat. So for the question where this data comes from, and also for an intuition, what are so this is really a huge literature that tries to think about those kind of processes and what kind of properties of the network influence the, for instance, the spreading of cascades. Maybe to answer the first question more into this area. So definitely the density of the network is really important for the question how well the cascade can spread. It's also the amount of load, so the whole production that is available and how it is distributed. Those kind of issues make a big difference. Something that we completely disregard though in this model are the price dynamics, which are also quite important, because what we also observed for instance, in the 2008-2009 food crisis, so food price crisis, that even if you have enough production, you can still run into problems just because people get scared, and you have this kind of dynamics that they try to so they actually enforce export restrictions because they're scared that they cannot feed the population. This then leads to increasing prices, and so on, and then you get this kind of cascade process that just jumps up. So the prices increase just even though enough would be there to distribute. So those kind of effects also. So there are many also external factors that play a big role when it comes to, let's say, to judging the state of the, let's say, the state of the economy and the food production. To come to the more broader questions about if you want to completely rethink the entire, let's say, this entire economy and how food production should work, and also especially the diversifying the production, for instance, that you don't depend only on those three crops. Yes, that's a big question that I cannot answer, and that is also not. But I would like to mention one part also in this model. what I find interesting. It also depends a lot on what we actually consider as problematic and what we, so let's say those cascade processes were mainly meant here, for instance, to show you indirect dependencies. However, it's completely unclear if this is actually a bad thing, because an ongoing cascade might also, let's say, if we have a strong network structure, so let's say something like a complete network, and usually people would say, especially considering SII spreading processes or something like this, you think, oh my God, the complete network is the worst case, everything, because everything can spread and, you don't have any chance. But on the other side, it's also the case that is the best risk diversification that you can think of. So all the countries share the burden of producing, and in case that something goes wrong, this also means that they're able, based on this infrastructure, they are able to, let's say, to ship a good that is produced in one country to another one because it's needed there. And so you also have compensation strategies.
So this is great detail. I also just want to zoom out and boost the signal on a broader question, which is to think about modeling that's descriptive and sort of how that can tie you to current practices and small change when sometimes you'd like to be thinking about bigger change. And I think that could be a really great question for a lot of the other folks who've been talking to think about in their models. I know it's something that we think about a lot when we do redistricting. Sometimes you model all the different ways that you can redistrict and you come to the conclusion, don't use districts, bad system for what you're right? So I really appreciate the broader question about the various ways that we can come up with excellent models of what we have now or what's very similar to what we have now. And sometimes it blocks the way for other kinds of bigger questions.
Yeah, that's true. Okay. Maybe can I add one part on that? Because what I think what is also important then, sorry.
Maybe just really briefly. Yeah.
Yes, very briefly. It might also be important then to think about the transition period. So if you want to, if you want to create a completely new system, you also need to start from somewhere. And sometimes, even though your objective is much, much better than the way before, the way there can be painful. So
this is something that comes up in political philosophy, where the transition itself is something that you need to examine. Absolutely. Okay, so that was I think a terrific way to end the session. We're a little behind time. Yes, revolution. So I think we should turn it over now to Anna. And so forego a break, and Anna will, of course, give you a couple more minutes of padding at the end, and then try to have a little break before we turn to our last talk of the day. So after Anna, a short break before we hand it over to Tina to finish us off. So Anna, you should be able to share your screen now and take it away.
All right, I'll share my screen. Thank you so much, Moon. And thank you, Moon and the organizers, for inviting me. I'm really honored to be here and to present. It's been such a wonderful workshop so far. I feel like I learned a lot, and I'm gonna go home and read all the papers that everyone shared. And all right, let me present. Let me know if everything is visible and all right. Perfect. So today I wanted to talk about a subject that we've already discussed a little bit: inequality in networks, and more specifically how biased networks can lead to graph algorithms also reinforcing certain these biases as well. And I'm going to focus on two main topics, on influence maximization, and if we have any time, I suspect we might not, but I'll try to touch on recommendation as well. So, all right, to get started with that, when we work with network data, as you all know, we work with people's connections, and it includes, beyond people's connection, it includes people demographics or communities that they are a part of. And that includes the fact that people are a part of different communities, they connect in different ways, and that reflects some of the inequalities that we see in the real world, especially for disadvantaged groups or minority groups. So when we apply algorithms that work with such data, we can end up with a biased outcome. And one of the first questions that I wanna try to answer is, how do we even define what a biased outcome is? How can we even start to formalize that? And that really depends on the application that you're looking at. So if you're looking at recommendation, for example, to try to recommend people to form new connections between each other, or to recommend content, it really matters who gets recommendation and who doesn't, right? So who is able to continue their connections in the future and who is kind of left out of this loop. If you're looking at issues like how does information diffuse in a network related to the problem of contagion that people have talked before as well, this question relates as well to who gets left out of a loop and what kind of patterns of inequality do you see there in terms of people, but also in terms of communities. So as I said, I'm going to focus on the social influence maximization problem to begin with, which relates to how information diffuses in a network and what are some of the issues there. And I want to look at some of the models that are really helpful in trying in understanding where does inequality come from and how can we deal with that, looking mostly at like community-based inequality between different groups. So, social influence relates a lot to the way information propagates through the social network, highly related to the contagion problem. And it has many applications from like everything that we see online from our friends to the different technologies that we hear about, opportunities as well as job prospects, to a big field is in running marketing promotions, in doing targeted advertisement, and probably even more important in public health issues. And these are two topics that are quite different and require different kind of thinking in this problem, right? So when you run a marketing promotions, you really aim to run a relatively small campaign in order to target a population that is really interested in your product, to find that subset that will be interested in what you have to say. But in public health issues, there is a different question. It's a question of managing to get the information needed to as many people as possible. So running a large campaign in which question of like bias or fairness or who gets this information are way more acute. And this is the problem that I want to tackle in this presentation or in this talk. And of course, it has ramifications from what our recent discussion on COVID and the way different governments run information campaigns, and people learn about the healthcare guidelines, and also in other fields. So people have studied this problem in the way, for example, you can give people different financial opportunities. This is a paper on how microfinancing loans diffuse within rural communities in India, and it's trying to leverage the connections that people have between each other to really get more people to apply for these. And they do focus on women specifically to get this information too. So they look at this community-based strategy. And of course, in other topics related to health, other people have looked at how to raise awareness about HIV among the homeless youth, again, targeting an underserved community in trying to get this information to as many people as possible and seeing what are the gaps we have to reach between what we do in research and how this actually works. I'm going to talk mostly about, so this work is mostly focused on theory. There is some data that we work on, but I want to talk about mostly our graph modeling assumptions and why sometimes they can be helpful. So to begin that, to formalize the problem, you basically, in social influence, you would start with a network of people who are connected to each other. And the purpose is the following. You want to select a subset who are your early adopters. They're the first people who you give this information to, in a sense, the seed set. And from this set, these people are going to send this information to their friends, who are going to send it to their friends as well, and this process cascades. And in the end of the day, you get a subpopulation who receive this information, and that's your outreach. And the goal is to maximize that. So the question is, how do you pick these early adopters in a way that maximizes your outreach? If you pick people who are not connected to anyone, they're not going to spread that information to anyone else. If you pick people who are very popular or very central, that may be more helpful. And many of the heuristics look at that, like how do you identify people who are very central or very popular in a network? And of course, the more people you pick, the better it is, but oftentimes you have a budget. You can't really give information to everyone freely. You start with this set just because you have, it's expensive to give it to too many people in the beginning. And you hope that you rely on their network connections for this information to spread. So algorithms that look at these measures of centrality, whether it's people's degree or distance, or look at paths, random walks that people have between each others, oftentimes tend to reinforce the patterns of inequality we see in networks. People who are already in an advantageous position just tend to be even more advantaged. And there's a recent line of work that looks exactly at that, at exactly how this pattern is being reinforced. especially looking at greedy algorithms that are very efficient. They're shown to perform close to optimal, and they're the ones who usually ignore the labels, simply relying on the network connections to spread information. And they're prone to reinforce this bias in terms of where, what communities receive this information and what communities don't. So based on that, people have proposed different diversity interventions, and oftentimes they look at diversity interventions that try to reestablish some of that lost parity between different demographics or different communities at the level of the outreach. And they're looking to pose that as a constraint in the optimization function that's based on these greedy algorithms. Greedy algorithms are great for that. They are expensive and they have to assume full network information. And this kind of work shows that there is this like fairness efficiency trade-off. So the more fair you want to be to people, the more you want to spread this information more representative groups, the more actually you're going to lose in the number of people that your information reaches. So the outreach that I mentioned earlier. So that's an issue. But in this work, I want to talk about a different approach and how that is not necessarily the case depending on how you tackle this problem. And in reality, we're looking at networks that are partially known. It's very hard to run a greedy algorithms on very large scale data. So we're focusing on centrality measures such as degree or other statistics that you have from the network. You can have distance centrality and so on. But degree is a good one. And it does not perform bad when in certain networks, especially when you have a low probability of transmission, it's shown to actually be quite close to greedy. But so what we do is we use this, for example, these metrics to try to add these diversity interventions for the early adopter set and to hope that that will reverberate throughout your network. And the intuition behind us is that if you're tapping into inactive communities, in these groups that are already not central, you're actually getting, you can get more than just being, than not taking diversity into account at all, because these communities have not received this information to begin with. So it actually can help you increase your outreach. And this is a way to formalize that. So people have been looking at also previously as this way of spreading influence in a way that's doesn't have an overlapping effect. So if you have people who like, if a person is in your initial seed set and another person is, and they have the same subset of common friends, well, they don't have that much influence altogether. You better choose someone who's more far apart, who can basically cover a different community. And that's the intuition behind it. So this is formalized in a recent paper with my advisor, Augustine Chantreau, and our collaborator, Jessie Shinihan. And in this paper, this is the vision behind that this kind of bias can be a sign of inefficiency. And beyond the many benefits that diversity has, it also brings us this different idea that it does not have to come at a cost of efficiency that we see in some other works. So how do we think about this? When you choose your early adopters, like classical works don't look at demographics, don't look at community affiliation. They ignore labels and they already take into account this community structure, right? So everyone kind of looks the same, but based on the connections that they have or these proxies, such as degrees, you can end up reinforcing this bias that I talked about before. If, on the other hand, you are aware of the labels and you try to add these diversity interventions or to try to change your early adopter set to be more representative of your general population, that's something that will be helpful for us to be able to be more fair in the outreach as well. So when I say parity, I simply mean that the demographics of your set, of your early adopters in this case, just have to represent the demographics in general, right? And the same thing would go for the outreach as well. All right, so with this in mind, this is the problem formulation, right? We start with a network of partial information, you have degree, you choose your early adopter set based on a measure of this measure of centrality, you try to be strategic to add this diversity intervention, and you hope to get this to reverberate in your outreach as well. And the main idea that I want to talk about for this is like, what kind of models would that work for, right? So if you think about a model in which in which people is a disassociative network in which people connect more with opposite people, that doesn't really sound right. Like it's not really like intuitive that in your outreach you're gonna have the same demographics you started with. But oftentimes that is not the case in most of the online networks that we see. We see that people are quite homophilic. They do tend to connect more with people who are similar in terms of demographics or interests, and they do tend to have this strong community structure. And that is something that we can formalize in a model to try to understand this and to see exactly how this, where this bias come from. So I mentioned this in the discussion as well. This is a model that is based on previous works that really inspired me to think about this problem as well. It's a preferential attachment model. So you start, it's a growing model in which every node is either blue or red. And imagine that you have a minority group of red nodes. And at each point in time, a new node comes in, and it will connect with an existing node with a probability proportional to their degree. And that's how you get the rich get richer effect, also called the preferential attachment model. And beyond that, you also have a homophily parameter. So if people have different labels, then that connection will be accepted with a certain probability. That leads to these groups being, like in this case, these two groups being more connected within than across to each other. And these are two important factors that kind of replicate some of the patterns we see in our networks, especially in online networks. One reason is that people do, there's been extensive works in sociology showing that people do indeed connect more to each other, like Birds of a Feather paper, that's been very seminal in that. And the fact that people do tend to connect with to a preferential attachment model, that creates this power law degree distribution in which a few people are very popular and most of the people just don't have that many connections. What is interesting about this model is that, as I mentioned, it kind of generalizes this, the classic preferential attachment model to show that these two communities are both gonna have a degree distribution that's a power law, and more than that, their coefficient is gonna be different. That is really telling because it shows, it formalizes a kind of inequality that's beyond just looking at average degree or average around the community as well. Why? Because if you look at, for example, top K nodes, if you look at top nodes of degree at least K, then of course their number is gonna be, like as the network increases, their number is gonna go to infinity as well, but the fraction of minority over majority nodes is just gonna go to 0. So as your network increases, among top very popular people, you're never gonna see a minority node. And that is one effect that this model really brings up. And it's something that we see online. We've seen this effect in Twitter networks. We've seen this effect in citation network as well, in DBLP. And there's been several studies that look at that. And that's one way to think about how to formalize it and to work with this effect. So the paper that I mentioned before by Avin et al. Calls this a tail glass ceiling effect, because the minority node can never get to a certain degree, to a very high degree. It's just a glass ceiling that cannot break. And that is through this model as well. So what does that mean for us? It means that if you choose nodes based on their degree, that's gonna be biased. You're really not gonna have that many minority nodes. Wherever you're gonna use degree, not only in social influence, but also in recommendation, this is a central point. That's also that can be biased as well, but we'll see if I have time to talk about that. So coming back to our social influence problem, if you're looking to choose a set of early adopters, your seed set, that in an agnostic way, and you're not looking at degree, you're only looking at degree, you're not looking at community affiliation, that's gonna be biased, right? But oftentimes these are the metrics that we work with. Now, the two interventions that we can look at is the following. You can have a parity seeding, let's call it so, in which you keep the same budget, the same number of nodes in your early adopter set, but you want to add a number of nodes from the minority, in this case, the red community, in order to get the same statistics in your early adopters as you have in your general population, to achieve this like statistical parity in your early adopter set. What does that mean? It means you have to add a few nodes who are red, who have a lower degree than before, and you have to get fewer nodes who are blue, for the minority group, the majority group, who now have a higher degree. So you have different thresholds for these two communities, and it's a strict condition. You can also think about something in between, we can call it diversity seeding, which is something that goes in between agnostic seeding and parity seeding. So it's a relaxed condition on this formulation. So the seed set is going to not going to have strictly statistical parity, but still it can have more of the minority nodes. All right, so with this in mind, how are these helpful? How do these actually perform? What we get from this model is the following, is that both diversity and parity can lead to fairer outreach, meaning that, yes, indeed, if you choose your early adopter set to have a better statistical parity ratio, that actually reverberates in your outreach as well. And that is intuitive. That is intuitive because from the model that we use, since people are homophilic, that kind of people who are similar or from the same community are going to connect more with each other, right? The part that is not necessarily intuitive is that both of them, both diversity and parity seeding, can actually get you more nodes than the agnostic one. The reason it's not necessarily intuitive is because you added nodes who have lower degree. Now, you didn't add the ones who have the highest degree in your network, but yet even those with lower degree can actually make up for that loss and add you in the end a higher number of your nodes in outreach. You manage to reach more people than otherwise. That doesn't happen for all cases, but we're able to actually get a condition for which on the size of your campaign, like how big the seed set size needs to be in order to do this. And we want to see if this is like realistic or not. We want to see if this is actually something useful. But what we get at a high level is that if you have a small campaign, you have a small seed set, agnostic seeding is going to do the best. If you're trying to be fair, you're going to lose some nodes in the outreach. You actually don't lose that much from our data set, but you do lose some. If you have a large campaign, if your budget is high enough that you can have a seed set that's quite large, then parity seeding is going to perform the best. Parity seeding is going to perform better than agnostic. And when you have a medium campaign, so when you have something in between of a budget, diversity seeding will be performing better than agnostic. And diversity usually performs better. It's always going to get you more nodes than parity just because it's a relaxed version of it. But I want to show you one graph of how that actually looks like. So given our three heuristics, again, how do they actually perform in getting us into influencing in a network? All right, I think I'm okay with time. So let's look at this network. This network is the following. On the x-axis is the minority fraction of a network with two communities, around 50,000 nodes and some homophily factor. And this basically simulates the real data that we got from a couple of sources, Instagram and DBLP to begin with. So on the left-hand side, the leftmost point is 0.10. That simply means you have a very unequal network. 10% is the red nodes, the minority, 90% is the majority. And as you move to the right, you get to more and more equal networks, where at 0.45, you have mostly equal networks. So 45% is the minority in red and 55% is the majority in blue. On the y-axis is your seed set size, the size of your campaign that I mentioned before that is important. So the colors that I'm plotting here is an instance of this network for a seed set size colored by which heuristic is actually best. So the orange region shows you the region for which not looking at community affiliation actually gets you a better outreach. You get more nodes if you don't if you don't have any diversity intervention. But at some point, as your seed set size increases, we move towards the blue region. And the blue region is where diversity actually performs better. Not only is more fair, which we know from before, but it actually sorry, I'm getting heavy rain, so you might hear that as well. But it also gets you a bigger outreach. So this blue line is the phase transition that you see between agnostic performing better and diversity performing better. And as you can see, it's monotonic. So as the networks become more equal, you need fewer and fewer seeds in your seed set size in order for diversity to become better than a non-diverse way of choosing your seed set. So for very like almost equal subnetworks, you only need very few seeds, up to a few tens, if I remember right, but to actually for diversity to become better. But if you have a very unequal network, you need quite a few. You need about like 12,000 seeds in order for that to become better. So at some point where if you have a really, really large campaign and you're moving up on the y-axis, you get to the purple region. And the purple region is where parity actually performs better. And parity, if you remember, it's simply the heuristics in which you have a strict parity condition on your early adopter set. And it's a strict one, so of course it's not gonna perform as well. But still, at some point, it actually is able to perform better than a non-diverse way, than the agnostic one. The last part that's interesting is the fact that the phase transition between these two is not monotonic. So the more seeds you have, the more equal your network is, at some point, the more seeds you need in order for parity to become better. And that is because as your network is more equal, your minority group is actually less and less disadvantaged. There's more nodes with higher degree in that setting. And the minority community has already heard about the influence that you want to give to them. So it becomes much harder to actually compensate for that and to have a true proportion, a true representation of this minority group in your early adopter set. So that's one way in which we can formalize this, and it really tells you cases in which like diversity can be really beneficial, and tell you exactly the cases in which, well, it's beneficial, but perhaps it's not really the most efficient thing to do. I'm not going to show, I'm not showing the graph in which with the true outreach with seeing how many you get, but for the lack of time, I just wanted to mention that even the differences between this and outreach, they're not that big. Even in the orange region where agnostic performs the best, you don't actually lose that many nodes. And that is something that is encouraging given the fact that for diversity and parity, you're really kind of like cutting a lot of nodes who are like very central and replacing them with those that may not seem that central, but just are able to tap into communities that you haven't really reached yet. So they actually have a better way of spreading influence. So that is the intuition behind it. And this model is useful because it allows us to actually compute and estimate the size of the cascade for each community, and to make this analysis. What I've showed you before is a theoretical analysis, and to test this on a real data, and to see that it actually works. We get the exact same results for the real data as well. All right, I think I have a few more minutes, so I just want to go.
Well, you can certainly, but also that'll cut into the questions a little bit. So.
Okay, then I'll take one more minute to finish up the idea that this kind of model was really helpful to look at recommendation as well. And when you look at recommendation, for example, friends of friends, we're able to look at, to see the fact that these can actually make, reinforce this inequality and make it actually worse. So, sorry, I'm gonna skip this really quickly, but if you're comparing this model to a model with added recommendation, we're able to also show exactly how the degree distribution changes and actually gets more unequal between the two groups, between minority and majority. So this is again another case where like you're looking at the objective is your degree and how your degree changes. And to see exactly what the gap is between these two communities. So, all right. There are many open questions. What if you have differential homophily between the two groups? There's some results there that I might skip on that, but there are many other questions to look at this. And I just want to finish on that note that if you're looking at algorithms that are actually, that you think are neutral and they're using your network, may reinforce this inequality through the proxies that you have in your connections. And being aware of network structure can be helpful, not only to be, in a sense, more equitable, but also sometimes it kind of eliminates this trade-off that sometimes we do have in our minds between being more fair and being more efficient. But that's all I had, so thank you, and I'll take questions now.
Okay, thanks. I thought that was super interesting. So folks, please, panelists, speak up if you have questions. Attendees, drop questions in the Q&A. Really interested to hear what people want to ask. And I will get us started. So I was really curious as I was watching, particularly in the later parts as you start to develop the findings. Have you tried this, how close have you gotten to real data with, with the work that you've done here?
Yeah, that's a good question. So we work with data that was real. So we got this data from Instagram, like a big scrape of people's likes and comments, which gets you like communities and their true connections, and the data from citation network from the BLP. And what we do with that, the data is real. What we do with it is to like simulate the diffusion process on it. We don't have a data in which we know the diffusion process and we can see exactly how it works. So that's how real we got with the data.
There's a question in the chat. What is the level of homophily in that graph? I'm not sure which graph, Vlad, you mean.
In the simulated data, perhaps?
The one
oh yeah, that one. So in the simulated data, we have this graph, right? In which we simulate the level of homophily. I think it's, so homophily is basically a probability that when I come into a network, and I try to connect, I choose a node. If it's a different color, I reject that connection with a probability of 0.10, I think, or like, no, 0. Yeah, I think it gets quite homophilic. I accept it with a probability of 0.20. Yeah, that's right, sorry.
0.13, you was on your slide. I think 0.13 something was on your slide.
Oh yeah. All right, thank you. So 0.13, I accept that connection with a probability of 0.13, which makes the graph quite homophilic. And that graph actually simulates the data set that we have, in which I think that's the data that we have from the BLP.
Great, and then there's a request to sort of reiterate the distinction between agnostic and parity.
Yeah, so to reiterate that, simply when you're looking at an agnostic algorithm, it's simply like it ignores demographics, community. It simply looks at degree. That's it. That's all it chooses by. It chooses like top 10 people by their degree. So if you're looking at another algorithm that chooses by that has parity, in that algorithm, it actually tries to add more of the minority group by degree, also in the order of degree, in order to get that. In your group, if you have 10% minority in total, you want 10% minority in your early adopter set as well. So the early adopter set simply is representative of your general data.
Great, and then this might be the last question we have time for. Nick, who says, first of all, that your talk was so cool, also asks, I'm not sure if this is modeled, but do you consider how different messages resonate with different communities? When thinking about efficiency versus equity, it seems that to message to a diverse demographic, you may need to craft multiple messages, which might eat up the budget. Would this decrease efficiency by increasing your budget?
Yeah, that's a super interesting question. So I have not seen that much works that look at differentiated influence. So usually you're looking at one network and you kind of assume it's the same probability for everyone to accept that message. But if you have different probabilities for different communities, then you might have to do that. And actually, if you're looking at two different communities separately and you're crafting a message for those communities, then you don't actually have that much inequality, right? You're just treating each community completely independently. It's actually when you're trying to have a unifying message is when you get more inequality, because that's when the two communities actually compete with each other to get the message the first to each other. I hope that made sense, but yeah, it's a great question.
Okay, great. Well, let's thank Anna again. And then we have a short break, so just 5 minutes. And at 4:20 Eastern time, we will come back for the last talk of the day, which is Tina Eliassi-Rad. So thanks to everyone. It's been a great day. I'm really enjoying it. and we'll see you in 5. All right, so it's 4:20. I don't know if this is a feature of Zoom conferences or just a today fluke, but I think we've hit our time marks better in this conference than any other I have ever participated in. So I'm a little bit pleased about that. And so it's a pleasure to introduce the last talk of today's conference, which is Tina Eliassi-Rad, who's going to talk to us about the stability of democracies. Thanks, Tina.
Thank you, Moon. Let me move this out. Too many windows on Zoom when you are sharing. So thank you so much for inviting me. And when Moon first asked me to speak, I gave her 2 options and she picked this one. This was work that was shepherded by Carolyn Wiesner, who is at Bristol. She's a physicist and a mathematician. And she brought together an awesome group of philosophers, economists, social scientists, mathematicians, computer scientists, etc., to think about democracy from a complex systems perspective. But after I heard the talks today, I've been on since the morning, I actually think the other paper is more suitable. So I'm going to talk about the other paper, which is actually a paper that is near and dear to my heart, in part because I got compliments on it from a physicist, a computer scientist, and a social scientist. That rarely has happened to me. So when Barabashi, Kleinberg, and Michael Macy like it, then you're probably onto something. So I'm going to talk to you guys about this. This is work with Mangesh Gupta, who was my student at the time. The problem is as follows. You have a bipartite network. You are given people, and people attend events, and you want to measure tie strength between pairs of individuals. In fact, the majority of networks that we see in real world are bipartite, and then we project them into unipartite. So the assumption for this particular problem of people attending events and measuring tie strength between each pair of individuals is that attendance at mutual events implies an implicit weighted social network between the people. Now, the motivation for this, as I was saying, there are lots of networks that are bipartite. If you ever work on a co-authorship network, it's a bipartite network. It was a bipartite network. You just did A transpose, A being the adjacency matrix of authors' papers, multiplied by paper authors. Or if you're working on a Facebook friendship network, that can suffer from a low signal to noise ratio because people have different friending schemes. My husband friends everybody. Any friend request that comes to him, he accepts. And so the challenge is to detect which of the links in the unipartite graph are important. And our goal for the rest of this talk is to figure out this implicit weighted social network from people's participation in mutual events. And so the tie strength is a measure of ranking on the edges, either all the edges in the network. In terms of Tina's tie strength to Brandon is the highest in this network versus a ranking on a set of neighbors of, for example, Tina. And a common example of tie strength is common neighbor, right? So it measures the total number of common events that a pair of individuals went to, or the number of common papers that 2 people wrote. Here's a picture of the weighted implicit social network of Macbeth, where the people are the characters in Macbeth and the events are the scenes in Macbeth, and the bipartite network connects a character to a scene if that character was in that scene. And you're getting this network by sending every pair of nodes to this function where it looks at the common scenes that they were in, and it says, well, how many people were in that scene? Then it does it 1 over the number of people in that scene, and then it sums up over all the common events that these guys were in. And it seems reasonable, right? If you've read Macbeth, Lady Macbeth and Macbeth, their tie is very strong. So the problem is everybody and their mother has a measure of tie strength. And as I'm speaking to you now, there are probably 10 other papers who are being put up on arXiv about a tie strength measure. And what are you to do? So which one should you choose? There's absolutely no guidance out there in terms of which one to choose. So the roadmap is to try to come up with an axiomatic approach where you sit down and you think about what properties you want a tie strength measure to have, and then say, okay, if a tie strength measure satisfies these axioms, can I have a characterization theorem? Where if Joe comes up with a new tie strength measure that satisfies these axioms, then I can write Joe's tie strength measure with the same characters as others who satisfy this axiom. And then I'll give some classification of prior measures, experiments, and some quick summary. So the running examples as follows. You have these people who are attending these events. So you have a bipartite graph. And what you really want is this implicit weighted social network. But as I will show, there are no set of axioms that can get you there. And that was one of the negative results in this paper. So what happens is you can come up with a set of axioms that will give you a partial order, but not a total order. And I won't spill the beans yet why that is. But for example, here, A, B, and C, D will have the highest tie strength among all the pairs that you can get. A, B are intimate, and C, D have attended more events than others. So we have 8 axioms. We have 8 of them because we needed them all to prove the characterization theorem, and I'll quickly go through them. The first one is isomorphism. I like graphs a lot. I don't like labels on graphs. I don't like content. Computer scientists typically like content on graphs. So the tie strength between 2 nodes is independent of the labels that they have. So I don't know that Tina is married to Brandon. And so for this little running example, B, C, B, D, D, E, and C, E, they will all have the same tie strength because they all attended one party where there were 3 people there. The next is baseline. I would like to be able to normalize the output of this tie strength function. One is that if there are absolutely no events, then the tie strength between each pair is 0. And the other one is that if there are only 2 people and a single event, P, that they attended, then their tie strength is at most 1. And this gives me some upper bound in terms of how much tie strength can be generated in a single event between 2 people. Then there are the axioms of frequency and intimacy. So frequency will create, all other things being equal, the more events 2 people attend, the stronger their tie. And this is actually from social psychology. We bastardize it a little bit. In social psychology, frequency is not enough. It has to be that I also have a good time with you, and not that like I saw you 100 times. But we're just saying if the more events you attend with somebody, the stronger your tie is with them. The other one is intimacy. So the smaller events will create stronger ties. The reason being that I can give all my attention to you, as opposed to if I'm in a big room with 100 people, I won't be able to give all my attention to you. In fact, it's because of that that in our running example, A, B, and C, D have the highest tie strength in this small example, because A, B are intimate and C, D have gone to frequent events. Then there's popularity, which is larger events will create more ties. So if you have 2 events and one of them has more people attending than the other one, then there will be more ties generated by the larger event. And it's not that the ties generated are going to be stronger, but the more total tie is going to be generated. The next 2 are conditional independence of people and events, but basically says that the tie strength for a person to other people does not depend on the events that they didn't attend. I don't know why Bob didn't come to my party, right? And I'm not going to do any kind of inference that way. I'm just going to try to measure Bob's tie strength with every other individual based on the events that Bob decided to attend. And then the increase in the tie strength that you're going to get for a pair of individuals for a particular event is due to the events that they have attended previously and this particular event. Again, I don't care that U has 100 friends and V has 2,000 friends and 50 of them met a lot. I know that if U and V have never met, then the tie strength is going to be low. And so this should give you a sense that basically what it is there's this history, this graph history G of 2 people who have met before, and there's a tie strength associated with that. So G here is the history that they have, and then there's a new event P that they both attended. And what's going to happen is you're going to have this monotonically increasing function that takes the previous tie strength, this new tie strength, and puts them together for you.
And the last axiom is submodularity, which is a bit of a misnomer, but the name stuck, which says that the marginal increase in tie strength between you and me due to a particular event is at most the tie strength that you and I could have gotten from that event, right? And so basically, if there was a particular graph G beforehand, and now there is a new single event Q, then the tie strength that you and I can get from that event Q is greater than or equal to the difference between what we had before minus what we had before plus Q minus what we had before. And so given these axioms, if you give me any bipartite network, I should be able to come up with this partial order. I will come up with a partial order for you and give you explanations based on the axioms. And so to us, these axioms seem fairly intuitive, but several of the measures that are in the literature break these axioms. And one of the problems is that there are no axioms sufficient to uniquely identify a measure of tie strength. And that's why there's a cottage industry of tie strength measures. And one reason is this inherent tension between frequency and intimacy. So let me give you two scenarios. Mary and Susan go to 2 parties and they're the only people there. Mary, Susan, and Jane go to 3 parties and they're the only people there. In which scenario is Mary's tie to Susan stronger? So however way your tie strength breaks that is what the key is. And that's why there's a cottage industry of how you break the intimacy versus frequency when you care about, okay, how strong is Tina's connection to Brandon? And if Brandon buys an iPhone, should I sell an iPhone to Tina, or should I show an ad to Tina, for example, for that? So our axioms are equivalent to a natural partial order on the set of the strength of ties. And it's pertinent to ranking. So we care about ordinal ranking, not numerical ranking. And when you pick a particular tie strength measure, what you're doing is you're taking our partial order and picking a linear extension for it. And that linear extension, the choice of that linear extension is not obvious, and details are in the paper. And so as I promised, there's going to be a characterization theorem. I'm just going to put it up there. I'm obviously not going to talk about it. Is that if you give me a tie strength function that satisfies our axioms, then I can break it up into 2 functions, h and g. The function h is a monotonically decreasing function that will tell me how much tie strength I get by being in the same event with you. And the function g is a monotonically increasing submodular function. And so let's look at some of the tie strength measures that are out there and see if they satisfy our axioms, and I should be able to break them up into this G and H. And so if you look at the tie strength measures that are out there, there's a whole bunch that are non-self-referential, like common neighbor, Jacquard, which is similar to common neighbor, it just normalizes for how social 2 people are, Adamovich-Adar, delta, and linear, where the tie strength increases with the number of events. And the tie strength is 1 over some simple function of the event size of how many people were at that party. We added a max tie strength function where the tie strength does not increase with the number of events. For each common event that I am attending with you, I get a tie strength, and then I take the maximum of those tie strengths. Then there's a whole bunch of the self-referential tie strengths. This group probably knows about the CATS measure, where you're looking at the number of paths between 2 people, and then you're discounting the paths based on their length exponentially. And then there are random walk with restarts. This is just personalized page rank. There's SimRank that came out of Jennifer Whittam's group at Stanford, where you are measuring my tie strength with you based on the tie strength of our neighbors. And then we added this new tie strength called proportional, where my tie strength increases as a number of events that I attend. And then people spend time proportional to their tie strength at a particular party. So these are the measures that do satisfy our 8 axioms. So common neighbor, delta, Adamovich-Adar, linear, and max. And as I promised, I can break them up into G and H. So common neighbor is just the summation over the tie strength for each event that you're getting. And for each event, it's just a constant number. It's just that you and I attended an event, binary, yes or no. Delta is 1 over n choose 2. Adam Ichadar is 1 over log n here being the number of people that were in the event, that particular event that you and I both attended. Linear is just 1 over n for h, and then max is also 1 over n, but the aggregation function g is the maximum tie that you and I have had over the years in the common events that we attended. And then of the tie strength measures that don't satisfy all the axioms, there are these Jaccard index cats, a lot of the self-referential ones, because they don't satisfy the conditional independence of the events. That for example, their guilt by association is extremely strong, right? So they say, oh, I don't care that Bob and Tina have never been in a mutual party. They have a lot of mutual friends that were in those parties. So they must have some strength of tie. So we looked at a bunch of data sets. We also had a huge data set from Washington Post when they had a social reader. I haven't put them in here. Some of these are the Shakespearean plays. Mangish, who at the time was a student, really liked Shakespeare, so we were looking at Shakespeare. For those of you who don't know, Southern Women just tracks 18 Southern women over time. They attended 14 different events. And then the MIT Bluetooth reality mining data was out of Sandy Palin's lab at MIT, and then the famed Enron email data set. So one of the things that we looked at was the number of ties that are not resolved by the partial order, right? So if the partial order that the axioms are giving have a lot of ties that are not resolved, then that is no good, right? So one of the things that we see is that the number of, or the percentage of tie pairs that cannot be resolved is rather small. And you may say, why are the tie pairs so large, given that your graphs were relatively small in terms of the number of people? It's because you're doing the tie and the pair. So it's n choose 2 and then 2 from that. So one of the takeaway points is that the axioms that we came up with not only allow us to prove a characterization theorem, but also they don't, their partial orderness is not very large. The other one that we looked at was the conflicts between our axioms and functions that don't satisfy the axioms. Those are mostly the self-referential ones. So we have the Jaccard index, which is again common neighbor, but normalized by how social the two people are, and temporal proportional, where people spend time proportional to the tie strength in a particular party. So if I'm your best friend, I'm gonna hang around until late night. So, so here what we wanted to know was the number of conflicts between the partial order and the tie strength functions that don't satisfy the axioms. And again, we see that the numbers the percentages are small, that there are not that many conflicts between the partial order that we're getting and the self-referential functions that usually are computationally very expensive. Now you may ask, well, maybe this is because there's a lot of tie strengths that are at 0, and that's partially true, but there are tie strength functions that don't set a tie strength of 0 between you and me because we have friends that attended common events. But we looked at our data sets, we excluded the tie pairs. This is just gonna change the denominator when you're computing the percentages. And what we saw is that the percentage of the conflicts goes up, but very little. So here I'm showing the data sets. On the y-axis, you're seeing the percentage of conflict. This is for Jaccard. The blue is not excluding the tie strengths that were 0. The red is excluding them. So the tie strength conflicts goes up. Again, you want the number of conflicts to be low, but it's not that much. And again, the highest number on the y-axis here is 14%. This is for temporal proportional. The highest number of percentage conflicts is 7%. So it's not going up by much. So the second takeaway is that the percentage of conflicts between our axioms and the tie strength functions that don't satisfy our axioms are small. So if I put the two takeaways for you together, is that if your application is ranking, ordinal ranking, then just pick the most computationally efficient tie strength measure, like common neighbor, which is what computer scientists were doing when they did AA transpose, where A is the adjacency matrix. It's just that they didn't know why that was the right thing to do. And common neighbor is extremely computationally fast than doing SIMRank or CATS measure or so on and so forth. So to summarize, I presented an axiomatic approach to the problem of inferring implicit social networks by measuring tie strength, right? So you start with a bipartite network and you want to be able to infer the implicit weighted social network. There are very few axiomatic work on graph measures. Here are a few that I have listed: one on trust-based recommendation, one on PageRank, one on information theoretic measure of similarity. I know people tried to do it for link prediction, which is a popular task on networks and graphs, and they could not come up with an axiomatic approach, and they came up with a theoretical justification based on mapping nodes into a latent space. And so you guys are a bunch of very smart people. Perhaps you'll look at axiomatic approaches for the different measures that one proposes. On that note, thank you, and I'm happy to take questions. And I see that I'm finished in 20 minutes, which means we can have happy hour sooner.
Great, thank you.
Thank you.
All right, would like to get us started with questions for Tina.
So I see some questions in the chat.
Yeah, this is, I was sort of storing questions there for later.
I see.
I can also ask a question. I don't know if you covered this already, but a lot of what I do is also related to bipartite and unipartite network and the relationship between them. So I found this really fascinating. I was wondering if you ever had a situation where you have a bipartite network and you already kind of know what the unipartite network should look like, and you're able to try to infer that unipartite network and then validate that somehow and figure out like what measure actually does the best job. Have you explored that at all?
I actually haven't. In fact, that was something we were really looking to have, where, for example, you have people rating movies, and then on the flip side, you have like a social network of people of saying actually like how much I trust you. So we never really had that, which was unfortunate. But if I had that, then that would be so that would be relatively easy to check to see whether you're getting the right one and you're inferring the right unipartite graph. And if you don't, then if you have the ground truth and you've inferred this unipartite graph, you can learn another matrix to multiply the adjacency matrix you got to transform it to the other one that you want, right? It's a little hack, there's a post-processing hack, but that's a really good question. And actually on the network medicine side, for example, if I may riff off a little bit, we're working, like many other groups, we're working on like which drugs or natural compounds will bind to, let's say, COVID, right? And so those are all bipartite. And one of the things is that like the tie strength between the protein, like the protein that's representing the drug and the gene, and like whether that tie strength is the way biologists think. And talking to biologists, like, no, we don't think about like tie strength between this drug or natural compound and this gene, right? We think more in terms of like the contrast, like this is more likely to bind to this than that. And that will require a whole other representation. And that's why like this notion of how am I going to represent these relations in something beyond a simple graph is very interesting.
Yeah. No, I found your work absolutely fascinating. I think it's really cool to think about these things. So.
I'm also a huge fan of this approach. I've done a bunch of thinking about the kind of axiomatic approach in a social choice setting where, you know, you can prove all these nice impossibility theorems once you have certain axioms, and then you ask yourself how you feel about those axioms.
Yeah.
Well, that was really interesting when you were introducing your axioms and you said, well, I need these 8 for my theorem.
Yeah.
I get that. But as you were going through them, I felt that little flag go up for your independence axioms in particular, where I was like, I'm not sure how much I demand these actually.
Yeah, in fact, that's where the true graph and network people like just go haywire. You're like, no network effects? Like, what do you mean? Like, you're taking my network effects away from me. Like, you know, and I think a lot of it had to do with like the motivation of like where it came from. right? So if, for example, you're going to use this in terms of guilt by association, then perhaps I don't want to go with, oh, yeah, well, Tina and Bob weren't in the same event, but they have mutual friends that were, right? So it really depends on the motivation, because if I'm going to use guilt by association to give a loan, for example, or all that other kind of jazz, right? Arrest somebody, call somebody a terrorist, then maybe I don't want to do that. But I can definitely see that there would be applications where you're like, no, I really care about these network effects, right? So,
well,
good point.
Especially, you know, because you make the observation at the end of the day that your partial order is nearly a total order, right? And that even when you compare to the tie strength notions that don't meet all your axioms, things aren't so different. It makes you wonder if there's some like completely other set of either axioms or just a non-axiomatic approach that would reveal something, you know, quite different.
Yeah, perhaps. The thing that we focused the most on was this intimacy versus frequency. And again, it had to do with the motivation of like guilt by association that we were looking at, the initial assumption. But there was like so much more that can be done just on this assumption of like time, right? How do you deal with time? We're not good with it. I mean, by and large, computer scientists are not good with time, right? You want it fast or you want it good? You want it fast. I'm going to discretize it for you. And don't tell me how to discretize it. It's Monday, Tuesday, Wednesday, Thursday, Friday, right? It's kind of like that. So there's lots of different things. And this is, again, why as a group, I think we should think more about how we represent things. Like I've been talking with biologists, like, it's just biology is so difficult. I know this group knows about it, but like you make these assumptions and they're like, no, we can't make that assumption. Like, what are you talking about? Just because like they bind it before, like in this other, no. So yeah, but yeah, depends on the motivation for the network effects, whether you really care about them or not.
Sure. Other questions from folks?
I have a question about like you mentioned how for you have a partial order on these, and how would you transition to a total order, or what are some applications in which you would have to do that?
So usually people want a total order, right? Like a partial order is not good enough for them, right? So if I say, like, if you look at like the CS rankings of schools, right? They usually put MIT, Stanford, Berkeley, and Carnegie Mellon all in the same set. And people are like, oh, you know, some people are okay with it, some people are not okay with it, right? And so that's where you have to break, right? And the linear extension is really how you're going to treat the intimacy versus frequency. Which one is more important to you? And so whether two people are more intimate says that you should break it one way versus another, or whether because they saw each other more often, or whether you have content and you know they saw each other a lot and they were positive experiences because somehow you had a sociologist go around and take surveys and collect that data for you. That like, but that's basically what happens to try to break this partial order. And for example, the excellent work in hiring, right? Sometimes people try to break the departments in terms of their ranking, in terms of where the students go, right? And like how many of them are able to get top jobs in top schools, and then you break up the ordering of like Carnegie Mellon, CMU, CMU, MIT, Berkeley, and so on and so forth.
Yeah, Tina, because of the intimacy and frequency of your ties to certain philosophers, are aware that there's some really interesting conversation happening in the philosophy community right now about department rankings and totally different axiom systems for how you should do it. So it reminded me of that a little bit, which I think might be a fun thing to look at.
Yeah.
Momin, did you have a comment?
No, I was just sharing a reference. I'm not sure if I saw it, but I've also seen Ulrich Brandes, it's probably slightly different, the work, present on axiomatic approaches to centrality measures and trying to unify them all. And he's also coming from very much a pure math angle, so that might be useful.
Yeah, yeah, that's great. Yeah, there's also one other one, Lemon Eguklu, who looked at axiomatic approach for resiliency of networks, but a lot of them don't have a characterization theorem. And maybe it's my proximity to a logician, but if you don't have a characterization theorem, it's like, you know, sort of you have yours, I got mine kind of a thing. But I'll have to, I know about this work, I have to revisit it. Thank you.
Actually, one other question. I'm just not sure how well known this is in this community. So this is sort of maybe a question for everybody, but one other really interesting piece of work on axioms and sort of what to do when your axioms don't get you quite where you want to go. Do people know about Eric Maskin's work on social choice and getting past impossibility theorems? This might be interesting for you, Tina, and for others on the call who like to think about these kinds of questions. So famously, of course, in the 50s, Ken Arrow showed that you put down a few desiderata for your election system and you can't do it, right? The only fair system is dictatorship or something, depending on how you phrase the theorem. Okay, you know, that's been a very important result that's been inspirational in a lot of other fields where that's been kind of the theme. You put down some axioms, you show an impossibility theorem or an equivalence theorem or a characterization theorem and so on. So Maskin, who's an economist at Harvard, has a few collaborative projects that I've just found super provocative in the last few years or decades. Where he says, okay, so no voting system satisfies all the axioms that you want, but what if we just sort of think about the space of possibilities measured theoretically and we ask, are there systems that work well on a big or interesting set? And I just recommend these papers. If I can find one quickly, I'll drop it in the chat. But it's pretty cool because he's able to prove a kind of domination theorem where he said, okay, you thought all election systems were equally bad, but there's actually one that's like provably better than anything else. Because if you can find an open set on which all the axioms are satisfied, my election system works on that too, and a bigger set.
Nice.
Yeah, it's just to sort of push the envelope on what you can do once your axioms lead you to impossibility. It's just I'm not sure that you really want to embrace his view of a continuum of voters, okay? When we're talking about realism in our models. But I think it's a really interesting place to go thinking about the dead ends that we come to with various kinds of axiomatic approaches.
Yeah, I like that. I like that very much. That, you know, yes, it's not universal, but you know, look at how much it can cover.
Yeah, I think that's the way to go. Yeah. Okay, last call for questions, comments. And Tina, you broke my heart with the stability of democracies.
I'm sorry.
No,
it's just, I was listening to the talks. I'm like, no, because that's more of a complex systems thing. Right. So, you know, another time over wine, I'll tell you about that work.
Cool. Okay, so I just want to thank everybody, especially those who've been with us all day. It's been a really cool day, but a long day. So thanks everyone. And I want to say, even though you've been hearing a lot from me, there are a lot of people organized this, and I particularly want to shout out to Liz Kopecki and Bhushan Suwal, who were kind of phenomenal in helping pull this off once we had to transition to online and do all the complicated things that involved. So thank you so much to all the
thank you.
Thanks to the lightning speakers, thanks to the organizers, and thanks to everyone who attended. Last thing I'll say before saying goodbye. So we're leaving that link up, tinyurl.com/gnpapers. And I really want to encourage you to just take your time, but go post there, because that's a mechanism that's supposed to kind of simulate the in-person sharing of papers and projects and ideas. So we're gonna take a little bit of time, a couple days, to grab the recording from this, put it together, take Chris Moore's talk about multi-layer networks and insert it back into that recording. And so I hope you'll be able to check that out. And at that time, it'd be really fun to share everybody's list of cool things to look at. Okay, so bye for now. Thanks for joining. Have a great day, everybody.
Bye, be safe, everyone. Take care.